In this video, we'll learn about function overloading. In C++, we can have functions with different parameter lists that have the same name. For example, I may have many ways to display information to the screen depending on what I want to display. So rather than having many functions with different names such as displayChar, displayInt, displaydouble, and so forth, we can have a single name display, and then implement a version of the function for each type of parameter. Then we just let the compiler figure out which function to use based on the function call arguments and the defined function parameters. It sounds more complicated than it is, and we'll see an example in the next slide that'll show you just how simple it is. This is a great use of abstraction, since as a developer, all I need to think is display and pass in whatever information I need. I don't have to keep track of dozens of different function names. In software engineering, we have a principle called polymorphism, which means many forms for the same concept. This is an example of polymorphism. Let's see what overloaded functions look like. In this example, we have two functions that are both called add numbers. The first function expects two integers, and the second function expects two doubles. I'm only showing the function prototypes in this slide, but we actually have to implement both functions. I'll do that in the next slide. Notice that in main, I'm calling both functions, but I don't have to think about different names. I just want to add two numbers. If I call add numbers with two integers, then the int version of the function is called. If I call add numbers with two doubles, then the double version of the function is called. In this slide, I'm providing the function definitions for the add numbers functions that we prototyped in the previous slide. It's important to understand that we must implement all of the overloaded versions. Notice that the code for these two functions is nearly identical except for the types. C++ has a feature called function templates that allow us to just write one generic version of the add numbers function, and it will take care of providing the correct version when called. Function templates are a little bit more advanced topic, and we'll discuss it when we talk about the standard template library. Let's take a look at another example. In this example, I'll only show the function prototypes, but remember that you'd have to implement all of these. I have 5 functions named display. The parameter lists for these functions must be different so the compiler can tell them apart. Once these functions are implemented, I can call display and pass in my data. The compiler will check the type of the argument in the function and match it to one of the available overloaded display functions. If it can't match it, or if it can't convert the argument to one that matches, then we get a compiler error. There is one restriction to function overloading. The return type is not considered when the compiler is trying to determine which function to call. So here we have two overloaded functions, both called getValue, and both expect no parameters. The only difference is that one returns an integer and the other a double. This will produce a compiler error, since the only difference is the return type. Consider the output statement at the bottom of the slide. Which function would the compiler call? It could call either, and that's the problem. It won't guess, so it'll produce a compiler error. Overloading functions is used extensively in object-oriented design, and we'll see it again when we design our own C++ object-oriented classes. I'm in the CodeLite IDE in the Section 11 workspace, and I'm in the Function Overloading project. Here I just want to go through some examples of overloading a function. Remember, overloading a function simply means using the same name for various forms of that same function. In this case, it's print. And what I want to do is I want to overload print to work with different types. So you can see some of the function prototypes here. In this case, I've got an int version of print. So if I pass in an integer to print, it'll use this version of the function, one that expects a double, one that expects a C++ string object, one that expects two C++ string objects, and the last one expects a vector of string objects. Okay? Remember, we have to implement each one of these, and that's what I'm doing here. I'm just saying printing int, printing double, so that we know which one's being called. So in the case of print int, it simply says printing integer and it displays the number. For double, it's doing the same thing, string, and so forth. Okay, and then for the vector version, it's just iterating through the vector and printing out all the strings in the vector. So let's see how this works. In this first case, I'm simply calling print and I'm passing in 100. Now 100 is an integer, so I expect that this integer version of print is the one that's going to be called, and it'll say printing int. Okay, so let's give that a try. printing int 100, exactly what we expected. In this version, I'm passing in a character. Now, characters are always promoted to integers. So in this case, it's going to call the same function, the one that expects an integer, but it's not going to print out the character A. It's going to print out 65, which is the ASCII code for A. Remember, it's using integers here. So let's run that. And there you see it says printing integer, and it's printing the 65. In this case, I'll comment both of these out. In this case, we're going to use the double version, which is this version right up here. Print expecting a double, and it's just going to say printing double and display the number that was passed in. So in the first example, I'm passing in 123.5. No problem, 123.5 is a double, so that should match perfectly. However, in the second example, that F right there makes this a float, not a double. So in this case, I'm passing a float to the function, but there is no overloaded function that expects a float. So what the compiler does is it will promote the float to a double. It'll match that function and call it. So both these statements will use that same function. Okay, let's run that. And you can see here 123.5, and in this case 123.3. Okay, so what about C-style strings? Let me uncomment that out. And remember, we've got a version of print right here that expects a string object, and it simply prints out that string object. However, I'm not passing in a string object here. I'm passing in a C-style string, an array of characters. That does not match that function prototype. But the C++ compiler knows how to convert a C-style string, right, an array of characters, to a C++ string object. So it will use that conversion, and it'll pass in the literal, make it an object, and then we're going to display the object. So if we run it, you'll see printing string, C-style string. Okay, exactly what we expect. Once you understand how the conversions work, it all makes a lot of sense. In this next example, I'm declaring right here S to be a string object. This is not a C-style string. This is a C++ style string object. And I'm passing it into print. That's going to match exactly, and it'll print out C++ string. All right. In this print statement here, we're passing in a C-style string and a string object. Okay, both. Now we've got a version of a print function right that expects two string objects. Well, no problem, right? We'll convert the first argument to a string object and then pass the second one as well. So in this case, when I run it, you'll see that that same printing two strings method is called with a C-style string and a C++ string. Okay, pretty cool. And then the last one is this vector. Here I'm creating a vector called Three Stooges, which is a vector of string objects, and we've got Larry, Moe, and Curly in there. And I'm calling the print function and passing in Three Stooges. So it's going to match this one right here that expects a vector of strings. And I'm just going to iterate through there and print out the Three Stooges name. So the three strings in that particular vector. Okay, so I'll run it. And there you go, printing vector of strings, Larry, Moe, and Curly. So you can see how nice it is to be able to overload functions. The nice part about it isn't so much all the code that I've written. That's not that great. The nice part about it is once the code is written, I can just think print. So if I'm solving an application, I'm printing, print. I'm printing everywhere. I'm not doing, I don't have to do print int and print string and so forth. I'm just thinking print, which is what abstraction is all about. Now, there's some couple of things you need to worry about when you're overloading functions. Be careful when you overload functions and you use default arguments. Okay, I'll show you why. Here's an example of the print with the integer version. I could certainly default this to 100, let's say. So if I don't supply the argument to the print function, it's going to default to 100. And let's test that out. We'll do it right up here. Okay, so at this point now, we should get 100 here and then 100 on the next line as well, right? So let's run that, and you can see there's the 100. That's the default argument right there. That makes sense. But what about if we didn't do that, and we did it down here in the print double? Let's say that we want to default this one to 125.5. Now, when I call print here, it will default to 125.5 because it's up here, right there. That's the one that's going to match, right? So there's the 125.5, and the double version gets called. Again, it makes sense. Where you run into trouble is when you do both. Let's say you do something like that. Now you're really in trouble because the compiler can't figure out which one to use. Again, look at the print call right here. It says print, but it doesn't supply any type information. So now the compiler can choose either one because they both match. And it's not going to choose either. It's going to give you a compiler error. And when I run it, it'll say something about an ambiguous call right here. Error, call of overloaded, print is ambiguous. So whenever you use overloaded functions with default arguments, you've got to be a little careful. So let me get rid of that, and I'll set those back up to the way they were. Okay, so that covers overloaded functions. We're going to see overloaded functions a lot when we talk about object orientation, and when we create our own classes. We want to have different ways to initialize our classes. You saw that with the vector class and the string class, all the different ways that we can create those objects. Well, that's all based on overloading functions. In this video, we'll learn about passing arrays to C++ functions. We can pass arrays into functions by providing the square brackets in the parameter information. So in this case, we can have a function named printArray that expects an array of integers and returns nothing. The idea is that this function iterates through the array and displays the array values. Pretty handy function, right? But arrays are different in C++. Remember that an array name evaluates to the address or location in memory of the first element of the array. In other words, the beginning of the array. So what's being passed into the function is not a copy of the entire array, but only the address of the first element of the array. That means that the function has no idea how many elements are in the array, so the programmer doesn't know how many times to iterate. So when we pass arrays to functions, we also need to pass in the size of the array so that we now know how many times to iterate. Let me show you an example. In this example, you can see that both the function prototype and the function definition have square brackets after the formal parameter name. This tells the compiler that the function expects an array of integers in this case. So far, so good. Then in main, I have an array of 5 integers called myNumbers, and it's been initialized to the integers 1 through 5. So I call the printArray function and pass in the array myNumbers. All good so far. Now I execute the printArray function, but I have no idea how many times I need to iterate. Since the array name has no size information, I'm stuck. If the array has a sentinel value, like a C-style string, then I can iterate until I see that sentinel value. But in this case, the myNumbers array has no such sentinel value. There's no way I can write this function body in a way that it will work with any array of integers. So the solution is to pass in the size of the array to the function as well. Let's do that next. Now we've added a size parameter to both the function prototype and the function definition. In the main, when I call the function, I pass in myNumbers and the size of the array, which is 5 in this case. Now when I execute the body of the printArray function, I know the location of the array, which is the array name, and I know how many elements are in the array. I can easily write a for loop now that iterates through the array and displays every integer. This looks great, but there is one potential gotcha that you need to be aware of. Since we're passing into the function the location of the actual array that was declared in main, that means that we can modify that actual array from within the function. This could be useful in the case of a function like zeroArray that we can call whenever we want to zero out all the elements in an array. However, in the printArray function, we don't want to modify the array. If we do, it's probably an unintentional error. We'll see how to protect ourselves from this kind of error in the next slide. But first, let's see how we could write a useful function like zeroArray. In this case, the zeroArray function receives the location of the array and the size of the array. We could simply iterate through the array and set each array element to 0. Notice that when we print the array in main after we call zeroArray, all the array elements are now 0. So let's get back to see what we can do to have the compiler help us so we don't change an array we don't want to. We can define function parameters as const parameters. This tells the compiler that these parameters are read-only within the function body. Any attempt to modify them will result in a compiler error. So in this case, notice that we included the const keyword right before the array parameter declaration. That's it. Now if I try to modify any array element, as I do in the assignment statement, a compiler error will occur. Depending on your compiler, the error message will say something like error trying to assign to a read-only value. The idea of passing the location of a variable to a function instead of the value of a variable is fundamental in understanding the next topic we'll talk about, It's called pass by reference. Before we talk about pass by reference, I want to be sure that you really understand the whole idea of passing arrays to functions. So I'm in the IDE and I'm in the section 11 workspace, the arrays and functions project. And let me show you what I've got here. Let's start at the main. I've got a real simple array here, array of integers called my scores, and I've initialized it to 198, 90, 86, and 84, right? 5 integers. Now what I want to do is I want to call a function called printArray, and I want to pass into that function the array and the size of the array, as we saw before. Perfect. That should print out 198, 90, 86, and 84. Now I've got a function called setArray, and what this function will do is it'll set every value of that array to 100. So when I come back, it'll print out 105 times, so that will actually modify the array. So let's see what these functions look like. They're pretty straightforward. There are the function prototypes. That's the function prototype for printArray. It expects an array of integers and the size of the array. The setArray function expects an array of integers, the size of the array, and the value that we want to set each one of those elements to. All right, so let's look at the printArray. And I put const here because it's something that we need to think about whenever we write functions that work with arrays. So let's look at this. What do we do here? Well, we iterate. We iterate for I equal to 0 while I is less than size. That's the idiom that we do all the time when we're working with arrays. And we're incrementing by 1. And then all I'm doing is I'm outputting array sub I. So I'm going to go from array sub 0, array sub 1, array sub 2, all the way to array sub 4 in this case. And I'm going to print out each one of those integers. Then I'm just going to print a new line at the end. That will print out 100, 98, 90, 86, and 84. Perfect. So that's that line right here. Then I'm going to call setArray, and I'm going to pass in, again, the array, the 5, which is the size, and 100. In this case, rather than doing any outputting, what I want to do is I want to loop through that array again. So the same loop from I equals 0, I less than size by 1. What I want to do at each iteration of the loop is I want to set ARR sub I, right? The ith element of that array to the value that was passed in. So in this case, I'm modifying all 5 of the array integers to 100. Then I'm printing it again. So what I expect from this program is the first print array statement is going to print 198, 90, 86, and 84. Then the last print array statement here is going to print 5 100s. Okay, so let's run this and then we'll walk through this in detail so you can see exactly what's going on. There you go, 100, 98, 90, 86, 84, and then 500s, exactly what we expected. So let's walk through this. Let's start with the printArray function first. And my main has that array right here called my scores. And I'm going to draw this visually so you can see exactly what's going on. There's my scores. It's an array of 5 integers. Okay, and I'll put them in here, 100, 98, 90, 86, and 84. The value of the name of an array is the location of that first element in the array. So let's say that that integer 100 here is at location 2000. And I'm just making that up. It could be any location. But that's 2000. So whenever the C++ compiler sees an array name, this is what it's going at. In this case, my scores will evaluate to 2000. Okay, perfect. So now I'm going to call printArray right here. This is what's going on. So now I'm in my printArray function. And printArray has several local variables. It's got array, it's got size, and it's got this I right there. Let's just worry about the array and the size variables right now. So there's my ARR, I'll just call it array, and here's my size. When the function is called, the values are copied. So my scores is 2000. It's not the entire array. It's 2000. So 2000 gets copied over here. Size is the 5. So size gets the 5. Right. Now I start looping. And the first thing I do is it says, basically I is 0, right? So what I'm going to do is I'm going to see out ARR sub 0. Well, what does that mean? That means the first integer in the array. Well, where's the array? Right here. That's that guy right there. So you can see that this print array function is referring to the actual array in main. Because the array was never copied. Instead, the address of the array was passed in. It's going to go through each one of these through the loop. It's going to print out ARR sub 1, which is that guy right there, 98. So it's going to display them all. Okay, that makes sense? I hope so. So again, this will print out right here. It'll display 100, 98, just like we saw, 90, 86, and 84. Now let's look at this function call right here. I still have my scores array, and it's still the same. I haven't changed it. And let me put those numbers back in here. I'll put 100 in here, 98, 90, 86, and 84. Right? Now I call setArray. Well, setArray is over here. And it's got same idea, right? It's got the ARR variable, the size, and the value. So it's got ARR, it's got size, and it's got value. Let's again assume that this is address 2000 right here. That's that name. So in this case, I'm passing in the 2000, I'm passing in 5 for size, and I'm passing in the 100 for the value. And then I'm looping. And notice that loop. Every time in the loop, this is what I'm doing right here. So the first time through, I'm saying ARR sub 0 is value, which is 100. It's always going to be 100. Well, where is ARR sub 0? It's at 2000. So what I just did was I just came in here and put 100 in here. Then I'm going to increment I, and it becomes ARR sub 1 equals 100. So this guy is over here. I just got rid of that one. And what I'm doing is I'm initializing the entire array to whatever value was passed in, which is 100 in this case. Right? When this function is finished, it's gone. And what I'm left with is the updated array. So this will print out 5 100s, as you saw. Okay, so hopefully that makes sense. It's a real different from pass by value, but when you think about it, it is still doing pass by value because it's copying the value of 2000, right? It's not copying the entire array, but it's copying 2000, which is what my scores defaults to. That's its value. All right, so one last thing. We really don't want to be able to change that array in the print array. Okay. Let's say that we did something like this. Something really silly. We could say ARR sub 0 is 10,000. Or you know what? Let's do 50,000, just so we can really see the difference. Okay. This is probably a bug. Okay. Print functions don't tend to change anything. They just display information. But let's just say that we've got some bug in our code. Now, right here, I'll call print array again. And I'll call it exactly the same with my scores and 5. So look what happened here. I called print array here. It printed out the 500s, but then it changed one of them, the first one, to 50,000. And then I'm calling it again. So I'm expecting to see that first, there it is. You see it? That first array element right there just got changed to 50,000. How do I prevent that? A real easy way to prevent that is to come up to your print array function right here and say that this is a constant array. And I can do the same thing in the definition. Now, if you try to compile this, there's the error. Assignment of read-only location ARR. So in other words, this function now, print array, cannot change array. That's really what we want. So we can comment that out, and now we'll run just fine. Okay, notice that's exactly what we want. So when you're writing functions, and they're passing around objects, especially arrays and vectors and things like that, especially when we talk about pass by reference in the next section, you've got to be really aware of what can change what. And if you do have access to the actual and you don't want to change it, const is the way to go. Okay, and we'll talk more about that when we talk about pass by reference. So far, we've seen that when we pass a parameter into a function, the default is pass by value. That means a copy of the actual parameter is made. We also saw that when we pass an array into a function, we don't make a copy. Instead, we use the location of the array, which means we can change it from within the function. Well, sometimes we want to be able to change an actual parameter from within a function. As we saw with arrays, this is achieved by passing in the location of the actual parameter. We can do this in C++ for any variable type, not just arrays, by using reference parameters. Reference parameters create an alias, so now the formal parameter in the function is an alias to the actual parameter. No copy is made. When you change the formal parameter, you're changing the actual parameter. This is called pass by reference, and it's really easy to achieve in C++ by using the ampersand symbol in the parameter list. Let's see an example. In this example, we have a function named scaleNumber. Notice that the parameter list to the function is not an int named num. It's a reference to an int named num. That's what the ampersand does. So now when we use num in the function body, we're referencing the actual parameter. Let's walk through this. In main, we declare an integer number and initialize it to 1000. Then we call the scaleNumber function and pass in the actual parameter number. We now transfer control to the scaleNumber function. Since the formal parameter in the scaleNumber function is a reference parameter, this means that num is an alias for number. If we change num, we're changing number. Behind the scenes, the location of number is being passed into the function. So the code in scaleNumber checks to see if the number is greater than 100. In this case, it is. It's 1000. So we set num to 100, and the function completes. When we return to main and display number, it will display 100. Pass by reference can be super useful for several reasons. First, it allows us to change an actual parameter if we need to. Second, we don't make a copy of the parameter, which could be large and take time. But we have to be aware of potentially unwanted changes. Let's see how we could swap two numbers using pass by reference. In this example, we're writing a function that swaps the values of the two integers passed into it. Take a look at main. X is 10 and Y is 20. X and Y are first displayed and we get 10, 20, just as we expect. Then we call swap and pass in X, Y. Then we display X and Y again. Now they're 20 and 10. We swap them. Look at the function definition and notice that both A and B are reference parameters. So when I call this function with X and Y, A and B become aliases to X and Y respectively. In the body of the function, I set temp to A, then A to B, and then B to temp. And we've swapped the two values that were passed into us. What do you think would happen if we didn't use pass by reference and we used pass by value? Well, the actuals would be copied, so we would swap the copies in the function and then return. When we get back to main, the actuals haven't changed since we were working with copies. Let's talk a bit about how parameters are passed into functions. Let's see what happens when we pass in a vector object to a function. In this case, I have a function called print, and it expects a vector of integers. Notice that in this case, we're using pass by value. Inside the print function, I simply use a range-based for loop and display the vector elements. Pretty easy. But there's one issue with this code. That is, we're using pass by value. So we're making a complete copy of the vector object in the function. So the formal parameter v will be a copy of the actual parameter data in this case. In order to make a copy, we need to allocate storage and copy values over. If the vector is very large, we could run into performance and storage issues. So why don't we use pass by reference instead, so we can avoid the copy? Let's do it. Notice that now I'm using pass by reference since I've declared the formal parameter v as a reference parameter using the ampersand. The output of this program is exactly the same as before, but we avoid the storage and copy overhead of pass by value. But there is one issue. Since I'm using pass by reference, the print function could change the value of the vector. It could even erase the entire vector. This is probably not a good idea. So let's tell the compiler that this is a constant reference. So now I've added the const keyword to the parameter. Now I've told the compiler to use pass by constant reference. So if I try to make any changes to the formal parameter v in the function, I will get a compiler error. This is really the best of both worlds since we're more efficiently passing information to the function, but we're still ensuring that the function can't change the data by mistake. Let's head over to the IDE and see this in action. Okay, so now I'm in the IDE and I'm in the Section 11 workspace in the Pass by Reference project. This is the same project that we used when we did Pass by Value. The only thing I've changed is I've made the parameters reference parameters now. So you can see the way I did that was just by including that ampersand. Now these are the same function prototypes. I've just named the functions passed by ref1 rather than passed by value as we had before. Okay, so I've got 3 passed by reference functions and just a simple print vector function that displays a vector element by element. Passed by reference 1 expects a reference to an integer. Passed by reference 2, a reference to a string. Passed by reference 3, a reference to a vector. And then the print vector function expects a reference to a constant vector because I don't want to be able to change the vector from the print function. Now, I've implemented all of these functions, and basically the code hasn't changed from before. I set number to 1,000, I set the string to changed, and I clear all the elements out of there. Now, if you remember before, we printed a value, we called the function, we came back, and the old value was still there. Well, now it's totally different because we're passing an alias to the value. Okay, so let's go through these examples. Here in main, I've got num initialized to 10 and another num initialized to 20. So now what I'm doing is I'm calling pass by ref1 and I'm passing num into it. So before I call it, I expect this to display a 10. But then after I call it, I don't expect the 10 anymore because I've passed a reference. Instead, if you look at pass by ref1, num is 1,000. So I expect num to change. All right, so let me run this and then we'll walk through exactly what's going on. There you go. Before calling pass by ref1, we have a 10. After calling pass by ref1, we have 1,000. If you remember the way it was with call by value, we had 10 and 10. All right, so let's see what's really going on here. Let me scroll up just a little bit. There we go. Okay, so I'm in main, and I've got num is 10. And I'm displaying it right here, right? So that's going to display a 10 in that output statement right here. But then I'm calling pass by ref. So I'm going to call pass by ref 1 over here. And it has a variable. And if you remember what that variable was, let me scroll up. It's right here. It's also called num. Remember, this could be any other name. They just happen to be the same name in this case. So that's got a variable in there called num. And right here, what's happening is when I pass this num into it, then this num now becomes an alias to that num. Okay, and again, don't worry about the names. I'm going to use a different name next time, but it's common to many times use the same name, so don't let that confuse you. And then in here, I'm saying num equals, I believe it was 1,000. So what's happening is this is an alias to this number, so this guy's going to change to 1,000. Real different to call by value. Okay, so in this case, we are really passing in the location of the number behind the scenes. But we don't have to worry about it because syntactically it's the same as call by value. Let's take a look at another example here. I'll scroll down just a little bit, and here we've got the same call to pass by ref1, except we're passing in another number, right? In this case, another num is 20. So this will display a 20, and when I get back, it will have changed also. There it is, 10, 1,000. Now we've got another num was 20, and now it's 1,000. So you can see that we're passing that by reference, and the alias is actually referring to the actual parameter. That's the important part to really understand here. In this example, let's take a look at that. If you recall this one, let me scroll up just a little bit so you can see it. Right here, pass by ref2 expects a reference to a string, and it just assigns changed to that string. Okay, so let's walk through this one and see what we can expect. In this case, I've got this variable right here, name, which is Frank, and it's in main. And it's a string object, right? Then I call pass by ref2. So here's pass by ref2, and it has a variable over there called s. That's the formal parameter. And what we're doing here is we're passing by reference. So we're passing name over here, and this s will now be an alias to name. So it's really referring to the actual parameter. Remember, this right here is the actual parameter. So now when I change this to changed, nothing happens over here. It's actually happening over here. Okay, so this is gone. It's now changed. So when this function is done, my actual parameter has changed, in this case to changed. Okay, so let's run this example, and we'll be able to see that that string really does change. You see that right there? Name before calling pass by ref2 is Frank. Name after calling pass by ref2 is changed. Pretty easy. It's really up to you, and when you're designing, do you need the actual changed or not? If you do need it changed, you pass it by reference. If you don't need it changed, you do pass by value. Sometimes pass by value is very expensive, as I mentioned before, so you want to pass by reference and then qualify it to be constant. And that's what we'll do in the print function a little bit. But let's take a look at this one here. Okay, so this is the last example we'll look at right here. Remember, we're calling pass by ref3, and pass by ref3, all it does is clears out that vector. So it's going to remove all the vector elements. It's going to make the vector empty. Okay, so let's do that. All right, so we're here. This is Stooges. And again, Stooges is declared in main. So Stooges is basically 3 strings, Larry, Mo, and Curly. And they're in a vector. Okay, so now I'm going to print the vector, and I'm going to pass Stooges into print vector. Now the vector is also expecting a reference, in this case a constant reference, so I can't change anything. So what happens is when I call print, vector, there's a variable over there called v, and since I'm doing pass by reference, this refers to this. So whenever I do any operation on v, it's affecting the Stooges vector, right? That would be the case, but since this is const, this is read only. There's no changes allowed, but I avoid the whole copy issue, which is important. All right, so that takes care of print. Now, when I call pass by reference 3, I do exactly the same thing, right? So I call pass by reference 3. I've got my vector, and it's also pointing to Stooges. Now, when I say v.clear, I'm clearing this out now, right? So Stooges is empty now. When this function is done, it's gone, and my vector is empty. So when I print it out again right here, you'll see nothing print. If you recall in the pass by value, it printed out Larry, Mo, and Curly again, right? Here, nothing. So let's run this. And you could see right here, Stooges before calling pass by ref3, Larry, Mo, Curly. After calling it, empty. Why is it empty? Because pass by ref3 cleared out that vector. It deleted all the elements. And because I'm passing by reference, it's really affecting the actual object. If I didn't want this to happen, I would make this const, in which case this won't compile anymore because you're not allowing me to change the vector, which is what this is doing. You'll get a lot of chances to play with this in the challenge at the end of this section, but that's pass by reference. We can use it with simple primitive types, or we can use it with object types. It basically works the same way. Just think of it as an alias to the actual parameter. In this video, we'll learn a little bit more about C++'s scope rules. C++ uses scope rules to determine when and where an identifier can be used. It uses static or lexical scoping, which means that the scope is determined the same way you read a program. C++ has 2 main scopes, local scope and global scope. Local or block scope refers to the visibility of an identifier that's been declared in a block, that is, a set of open or closed curly braces. Function parameters also have block scope. These identifiers are visible within the block in which they're declared. I talked about this earlier in the course, but it's important to understand it in the context of functions. When a function is called, you can think of the function as being activated, and the function parameters are bound to storage. They become alive, and their lifetime is while the function is executing. Once the function completes, the function is deactivated, and these variables and parameters are no longer alive. That doesn't mean that they're somehow marked as unavailable. It simply means that the compiler doesn't recognize them any longer, and the storage they were bound to will likely be reused. That means that the values of local variables are not preserved between function calls. If we have nested blocks, then statements in the inner blocks can see identifiers declared in the outer blocks, but outer blocks cannot see variables defined in the inner blocks. However, there is one type of variable whose value is preserved between function calls. This is a static local variable. It's a variable whose lifetime is the lifetime of the program, but it's only visible to the statements in the function body. These variables can come in very handy when you need to know a previous value in a function without having to pass it in all the time. Static local variables are only initialized once. If no initializer is provided, they're set to 0. Identifiers with global scope are identifiers that are declared outside of any function or class. These identifiers are visible to all parts of the program following their declaration. Best practice with identifiers with global scope is that it's okay to use global constants, but global variables should be avoided. Let's see scope rules in action in the IDE. Okay, so now I'm in the CodeLite IDE, and I'm in the Section 11 workspace in the Scope Example project. And here I've got an example program that just exercises a few of the scope rules, and I'll walk through them. They're very straightforward. The nice thing about languages like C++ and other languages that use static scoping is that the scoping is lexical, so it's as you read the code. It's not something that's happening at runtime on the call stack. Languages that use dynamic scoping rules are a little harder to follow in this sense. So let's take a look at this example here. I've got my main, and I've got two local variables defined in main. They're local to main because they're defined inside those brackets. Okay, that's really important. So what's this scoping deal all about? Well, when I use a variable name, for example, I'm using num here. Which num am I talking about? That's what scope is all about. And the rule is really very simple. First, you look inside your own scope, inside your local scope. So here's num, I'm using it. Which one is it? Well, look inside your scope here, and you'll see it's this one right here, right? That's the closest one within the scope that you're in. So this is going to print 100. Now, block statements, just like we had here, block statements create a new level of scope. And we're going to see this again when we use classes. So every time that you create a block, you've got a new level of scope. So notice here I'm declaring num again. This is a different num now. I'm using the same name on purpose. So now when I use it here in the output statement, which num am I talking about? Am I talking about this one here on line 36, or am I talking about the one on line 42? Well, you look in your closest scope first, right? You look for a local variable. So this num here refers to this num right here. That's the variable. So this is going to display 200. What about this one here? Num1. The rule again that you follow, look inside here first. Do you see a num1 declared in here? No, you don't. Then you look out to your outer scope. There it is right here. So that's the one I'm using. And that'll display 500. Okay, hopefully that makes sense. Now, here we go. We're using num again. But now we've got two nums. We've got the num here on line 36, and we've got the num here on line 42. Which one do we use? Well, you look in your level of scope, your local variable. You can't look into another block. You notice how this block here could see out, so we could see num1. That's perfectly normal. First, you look in your local scope, then you look outwards. You don't look inwards. Okay, so this num refers to this guy right here on line 36. So this is going to display 100 as well. We'll go through a few more examples down here, but let's run this one first. We're expecting 100, 200, 500, and 100. So let me run this example. And here we go, 100, 200, 500, and 100. Just what we expected. When you read about scope in books and on websites and tutorials, it's really complicated when you first learn about it. You know, talking local, non-local, global, and all this stuff. But conceptually, it's pretty straightforward. First, you look local, then you look out, 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 as far as you need to go until you find it. If you don't find it, you have a compiler error for sure. All right, so let's look at this one here. I'm calling a function called local example, and I'm passing in a 10. And let me show you what that function looks like. It's right here. We expand it a little. So I'm calling this with a 10. So I'm passing in a 10 by value. So this x right here will be a 10, right? I'm going to copy the 10. I've got a num variable right here, and I'm initializing it to 1,000. So my output statement is using num. Which num am I using? Well, I've got two choices, right? I can use this one on line 20, or I can use this one on line 11. I always use the local variable. In this case, I'm going to use this one on line 20. So this is going to display 1,000. Then I'm setting num equal to x. Okay, x is 10. Which num am I talking about? I'm talking about this num again. Right? So I'm going to set this to 10. And I'm going to display num, which is again the 10. So this will display 1,010. Notice that I can't use num1 here. Okay, because it's not within the scope that was defined inside main. Okay, so if I run this, I expect 1,010, And let's try that out. And here you go, local num is 1,000, and then local num is 10. Suppose I call this again, but I pass in a 20 into it. Okay, what do you think is going to happen? Well, let's go back here again. In this case, I'm passing in a 20, so x is going to get the 20. I'm initializing this to 1,000. Every time I call this function, that num will be initialized to 1,000. So in this case, there's num. I'm using this one right here again, so this will display 1,000. Now I'm setting that same variable to 20, and then I'm displaying it right here. So this is going to display 1,020. Okay, so it's the same idea, and it's pretty straightforward. Let me run this. So we thought we saw 1,010. Now we're going to see 1,020. Okay, so now let's look at an example of a global variable. You'll notice that way up here at the top of the program, I want to scroll all the way up. Let me close that function and expand this one. This is what we've got right here. We've got a global variable called num right here on line 11. And I'm initializing that global variable to 300. How do I know it's a global variable? It's not declared inside any function. It's not declared inside any class. It's just sitting there all on its own, right? This is global to the entire program. So in this case, I'm calling global example. And which num do I use? Well, what's the first thing you do? You look in here. Is there a variable called num defined in here? No, there isn't. Then you look outward, and there it is. So this displays 300. Then I take num and I multiply it by 2. Okay, which num? Same one. So this will now become 600. And I'm going to display 600. Okay. Now, what if I call this function again? And I'll call it twice in the main. What if I call it again? Well, the next time I call it, this variable still has 600 in it. It's a global variable. So the next time I call it, we look at num. Num is 600, which I display. I multiply it by 2. Okay, so that's 1,200 now. And then I display it again. So it's 1,200 this time. Notice the global variable does not get reinitialized every time. It only gets initialized that one time when you're actually before main is even called, that's initialized. So here we're going to end up with 300, 600, and then 600 and 1,200. So let me uncomment that one line out so we can call this twice right here. And let's run that. And you can see here we've got 300, 600, and then 600, 1,200. Just what we would expect. All right, so let's look at one more example here is the static local example. And I'll scroll up. Let me close that down. Now, we mentioned what a static variable was. A static variable is a variable that is defined locally. In this case, this is a static local variable. So num is visible in here. But because we're using the static qualifier, what that means is that this num variable will be initialized to 5,000 the first time this function is called. After that, it retains its previous value. Real different from the example we saw in local value, which it got reinitialized every time. Right? So let's say I call static local example the first time. We're initializing num to 5,000. That only happens once. Then I'm using it. Which one? Again, I'm looking inside local scope first. So that's going to display 5,000 here. Then I'm incrementing num by 1,000. Okay. Now it's 6,000. And then I'm displaying it again. Well, now it's 6,000. Now, suppose I call static local again. Since this has already been initialized, it won't be initialized again. And it's going to retain its previous value. So it's 6,000 right now. Here it is. So if I display it, I'm going to get a 6,000. And then I'm going to increment it again by 1,000 and display it again. So I'm going to get 7,000. And when I run this a third time, I'll end up with the 7,000 I started with and the 8,000 that I end up with. So as you can see, it's pretty straightforward. This is a real useful concept, the concept of static local variables, because you've got a number, or a variable in this case, that behaves like a global variable, right? Because it's retaining its value, but its scope is local. So you don't have the same problems that you have with global variables, which means that they're visible throughout the program and any piece of code could change it. In this case, if this number variable right here gets a really strange value, the only place it could have gotten it from was inside this function, and you know exactly where to look. So that wraps up scope. It's a pretty simple concept, and it's, again, think Look local first, then look out, then look out, then look out until you hit global scope. If you don't find that variable there, then you've got a compiler error. So how do function calls work? Functions use an area in memory called the function call stack or program stack. A stack is analogous to a stack of books or a stack of dishes. If you place a book on top of the stack, then you must remove that book before removing any others. This is referred to as last in, first out, or LIFO. Stacks also use the terms push when you put an item on top of the stack and pop when you remove an item from the top of the stack. In the case of a C++ program, these items are called stack frames or activation records. All it is a collection of information that represents an active function. So this is where parameters are stored, local variables, the return address, and more. Each time a function is called, an activation record is created, and it's pushed onto the call stack. When the function terminates, we pop its activation record off the call stack, and now the top of the stack is the function that just called the one we just popped off. The call stack works in a very orderly manner. You can't jump into or out of the middle of the stack. You must follow the LIFO rules. Also remember that the call stack is finite in size. If you activate too many functions on the call stack, then it's possible to run out of stack space. This results in a stack overflow error, which is usually an unrecoverable error and your program will terminate. The best way to understand how function calls work is to show you visually. Let's do that now. In order to understand how function calls work, we really need to understand how memory is laid out. Here, let's say that this is the memory for our program. It's divided into segments. So here we've got the code area. This is where the code resides. Then we've got an area for static variables or for global variables. That's where they're stored right here. And here's the area for the stack. This is the function call stack. And this is what we're really concerned about in this video. So this is the area I'm going to concentrate on in this video. Then we've got another area in memory here called the heap or the free store. We'll talk a lot about this area when we talk about pointers and dynamic memory allocation. So in this video, keep in mind that what I'm talking about is this area right here. That's the function call stack. So when we call functions and they finish and they pop off the stack, this is what we're talking about, this area in memory right here. Okay, so I'm in the IDE and I'm in the section 11 workspace in the How Function Calls Work project. And I've got a real simple example here that I'm going to walk through in detail in a second. But before I do that, let's concentrate and look at what typically happens when one function calls another. So I've written it out here, and this is not the only way to achieve this. There's a lot of different ways to get to the same end. But this is what typically happens. So suppose I have a main, and that main calls a function called func1. That's what's happening here. I've got main, and it's calling func1. Okay. And what happens? Well, main pushes space on the stack. Remember, everything here is based on the stack for the return value. That function, func1, is going to return something to main. Main is the one that needs to get that result once that function is done. We need to push space for the parameters that are being passed in, if any. In this case, we've got two right here, x and y. And we need to push the return address. That's important because function 1 needs to know where to come back to. Then we transfer control over to function 1, which is basically an assembly language instruction called jump. You just jump over there and you're off and running, so control is transferred. Now on function 1 side, it pushes the address of the previous activation record. That's basically moving a stack pointer. That way you know where the top of the stack is. You push any register values that need to be restored. Then you perform the code in function 1. When the code is finished, you restore the register values. That way main is where it was before. You restore the previous activation record, right? You basically pop all this stuff off the stack. You store any function result where main wants it. You can see main gave you the address. And you transfer control back to main. So you jump back to that return address that main pushed. On main side now, remember, function 1 is now done. So main knows where the parameters are and it knows where the return values are. So it needs to pop that information off the stack to clear up the stack and also grab those values if it can. Okay, so this is the general flow. We're not going to cover all the details here. I'm more interested in the parameter side of it. So what I'm going to do is I'm going to walk through this example and I'll draw a function call stack over here, and we'll go through it in detail so you can see exactly what's going on from the parameter perspective. I'm not going to worry about stack pointers and static links and dynamic links and all the stuff that's on an activation record, but more generally, let's worry about the parameter passing so you can really understand what's going on, because it's important to understand this, especially when we learn about recursion later on. Okay, so let's walk through this example. Program execution starts at the main. So main is going to be activated. It's got a function activation record because it is a function. So let's assume here main is on the stack already, and main has an X, it's got a Y, and it's got a Z. So we need space for those local variables. You can see X is initialized to 10, Y is initialized to 20, and Z is 0 in this case. Okay, so now main is right here, and we're executing this piece of code. Z equals function1 with XY. So we're calling function1. So what happens is main stops what it's doing. It allocates space for XY, and I'm just going to do this conceptually so we don't waste a lot of time, diddling with the stack and pointers and things. But let's suppose that at this point we're going to push an activation record on here for function1. And this is a little different from the example I showed you that I just walked through, but it's a little easier to draw. So this is where we're at. So now we're at function 1. Function 1 is now on the stack, and we need space for A, B, and result. Okay, so let's say we've got A, we've got B, and we've got result. We're doing pass by value here. So what's going to happen is the X hooks up with the A, and the Y hooks up with the B, right? There's your actual formal correspondence here. So X is 10, and that goes copied into the A. Y is 20 in this case, so we're going to copy that to the B. Okay, so this is where we're at right now. Now, let me clear a little bit of this up. All right, so that's where we're at now. Now we start executing this function, function1. So it's going to add A and B. Okay, so that would be 20 plus 10. So this gives me a 30. And it's going to store that value into result right here. So now result gets a 30. Originally result was 0, right? Because I zeroed it out here. I didn't write it on here, but you get the idea here. Now we're going to call function 2. And we're going to pass in result, A and B. Okay, so again, let's stop what we're doing here. We need to come back and finish this code. So we're here, and now we're activating function 2. And all along, those stack pointers are moving along here. This is the part that I'm not going to worry about drawing here. Okay. So now we're in function 2. We need space for X, Y, and Z. But notice X is a reference parameter. Okay, so we'll have to deal with that. So we've got X, Y, and Z. All right, so let's do X, Y, and Z. All right, let's do Y and Z first. We're going to pass those by value. What is Y and Z? Well, we've got 3 here. We've got result, which is corresponding to X. A corresponds to Y, and B corresponds to Z, right? So Y gets the value of A. The value of A was 10, so Y is going to get 10. And Z gets the value of B. So B was 20, Z is going to be 20. Okay, now let's talk about that reference parameter. Remember when we talked about reference parameters, we said that there were aliases, right? So in this case, X is an alias for result right here. Okay. So X is an alias for result. So any changes I make to X, result will be updated, right? Because that's the whole idea. That's the whole point of pass by reference. Now we start executing this code. The code says X equals X plus Y plus Z. That's what that means right there. Okay, so we've got Y and Z here, which are 10 and 20. So this becomes 10 plus 20. And then what's X? Well, X is a reference to result. Result is 30. So we're going to grab the 30 and add those two together. That gives us 60. So now we're going to say X equals 60. Well, again, X is an alias for result. So what we're doing is we're updating that guy to 60 right here. Okay, now function 2 is done. So what happens? It gets popped off the stack. So let's do that. So function 2 is now gone from here. All that's gone. I'm back in function 1. Well, where did function 1 leave off? It left off right here. We're back from the function call now, so it needs to return result. What's result? 60. Where's it going to return result to? Right here. Remember, result right there is the result of that function call. So what I'm going to do here is I'm basically going to say z equals 60. Okay. So that's what's happening here. I'm popping off the stack now. So function 1 is done. All this is gone. I'm back to main, and all main has to do is that one output statement right here, which displays z, and z is now 60, and the program's done. Okay. So this gives you an idea of conceptually what's going on with function calling. Now, I skipped a lot of these steps here on purpose because there's a lot to draw and it gets really, really cluttered. But think about all this as function call overhead. You really don't have to worry about pushing registers and transferring control, and all that's done for you by the compiler. But there is a certain amount of function call overhead here. So let's run this program and see that we indeed get a 60. And there it is. There's the result. There's 60. Okay, so hopefully this works. We'll do this again when we talk about recursion. That's when a function calls a function calls a function calls itself. So it's really important to understand what's going on with the stack call frame, so we really know what's being passed and what's being returned. And you can see here that if we don't have a way to unwind to get back to where we were, we could just really run out of memory, right, and get a stack overflow error. As we saw in the previous video, function calls have a certain amount of overhead. We need to create an activation record, push it on the stack, deal with parameters, pop off the activation record when the function terminates, and deal with the return addresses and return values. Although all of this can happen very quickly and efficiently, it still happens. Sometimes we have a very simple function, and the function call overhead might be greater than the time spent executing the function. In cases such as these, we can suggest to the compiler that it generate inline code. Inline code is basically inline assembly code that avoids the function call overhead. Inline code is generally faster, but if you inline a function many times, then you're duplicating function code in many places, and it could lead to larger binaries. That said, compilers are so sophisticated now that they'll likely inline code even without your suggestion. Let's see what an inline function looks like. Here you can see the syntax for an inline function. We simply precede the function return type with the keyword inline. Inline functions are usually declared in header or .h files, since the definition must be available to every source file that uses it. As mentioned earlier, compilers are so good now that most will make short functions like this inline anyway, even if you don't provide the inline keyword. Don't worry too much about asking the compiler to inline your functions, but now you know what inline functions are in case you see them in C++ code out there. In this video, we'll learn about recursive functions and how to implement them in C++. A recursive function is a function that calls itself. The function can call itself directly or indirectly through another function. If we end up with 2 or more activation records on the stack for the same function, then we have recursion. Recursion is great for certain classes of problems. Recursive problem solving is something that most programmers have a little trouble doing when they first learn. That's normal. Eventually, you'll understand that recursive solutions make sense in certain cases. There are many types of recursive problems that lend themselves well to a recursive solution. In mathematics, we have factorial, Fibonacci numbers, fractals, and many more. In searching and sorting, we have binary searches, search trees, depth-first search, graphs, and also many more. There are also classic problems like the Towers of Hanoi that can really be hard to solve with a non-recursive solution. Let's see how we can calculate the factorial of a number using recursion. Here we see the definition for factorial as you would find in a math book. Factorial is defined in terms of itself. That's what recursion is all about. We have a base case. So in this case, factorial of 0 is 1 by definition. And we have the recursive case. Factorial of n, or n factorial, is equal to n times n minus 1 factorial. See the recursion there. Let's see how we can implement this in C++. So let's look at the code starting at main. We call factorial and pass in an 8 to the factorial function. When the factorial function returns, the value returned will be output to the console. In this case, we expect 40,320. Okay, so now let's look at the factorial function itself. First, we need to decide what types we'll accept and return. The factorial function can generate massively huge numbers. So in this case, I'm using unsigned long as the return type and the parameter type. This can hold very, very large positive integers, but we can still get an overflow even with such a big number. If you look at the code for the factorial function, it looks exactly like the mathematical definition of factorial. We check a base case. In this case, if n is equal to 0, we return 1. Remember, the return knocks you out of the function immediately. Otherwise, we return the result of calling the factorial function again with n minus 1. So in this case, it would be return n times call factorial with n minus 1. There's the recursion. The base case is super important since it's what stops the recursion. Otherwise, we would recurse indefinitely, and eventually we would run out of stack space and get a stack overflow error. In a bit, we'll head over to the IDE, and I'll walk you step by step in detail through an example call to factorial so you can see exactly what's happening on the stack. Let's look at calculating a Fibonacci number now. Here's the definition for a Fibonacci number. There are two base cases. Fibonacci of 0 is 0, and Fibonacci of 1 is 1. And the recursive case is Fibonacci of n is equal to Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Again, notice the recursive definition. Fibonacci is defined in terms of itself. I think you can see how to implement this in C++. Again, I've decided to use unsigned long since Fibonacci can also produce huge numbers. Notice in the main, I call Fibonacci, and the result I expect back is 832,040. Now let's look at the Fibonacci function. Notice the handling of the base cases. If n is less than or equal to 1, then we simply return n. So when n is 0, we return 0, and when n is 1, we return 1. That handles both base cases in one step. We could easily rewrite this condition to explicitly check n equals 0 and n equals 1, but this achieves the same result. This base case is what stops the recursion. If n is not 0 or 1, then we call Fibonacci again with both pieces of the problem definition. Eventually, the recursion will stop and the result will be returned to main. Notice how much the code looks like the mathematical definition of Fibonacci. This is by design. Let me give you a few thoughts on recursion. Remember, recursion is a form of iteration, so anything that can be done recursively can also be done with iteration and vice versa. Use recursion only when it makes sense. The problem must lend itself to a recursive solution. Don't use recursion to count from 1 to 10. Remember the base cases. They are what stops the recursion and are super important. Because of the call stack, recursion can be quite resource intensive, especially if you have very deep recursion. It's not uncommon when you're first learning recursion to recurse indefinitely and run out of stack space, resulting in a stack overflow error. That's perfectly fine. This is how you learn. I can't tell you how many times in my career I've seen recursive functions rewritten to iterative solutions because of resource issues. Generally, an iterative solution to a recursively defined problem is less elegant and more difficult to understand in code. But sometimes we have to meet non-functional requirements, and that's what it takes. Let's head over to the IDE and walk through a factorial example in detail. So I'm in the IDE. I'm in the Section 11 workspace, and there are two projects that are interesting here that both use recursive functions. One is the Fibonacci project, and the other is the factorial project. We'll walk through a detailed example of how factorial works recursively in a minute. But here's Fibonacci, and it's just like I wrote in the slides. So here in the main, I'm calculating the Fibonacci number for 5, 30, and 40. You can see the 40 is pretty large. If you try to do like a Fibonacci of 50 or something like that, it's going to take a while because there's a lot of recursion going on. I mean, it all depends on how fast your machine is. Even here, when I do a Fibonacci of 40, I'll run this and you'll see a little bit of a delay. You see that? It took just over a second delay there to actually calculate that Fibonacci number. And it's a pretty large number. But once you start getting to really large numbers here, for example, 45, 50, then the recursion is just tremendous. And it takes a while to solve those problems. Okay, so let me go back to factorial. That's the one I really want to go over here. So here's the factorial, just like we wrote it, the factorial of some number. And there's 4 examples here. You can see factorial 3 is 6, factorial of 8 is 4320, and so forth. You can see the factorial of 20 is a really big number. And as this number grows here, that number really grows big time. So let me run this, and you can see it's really fast here. But once you start really increasing that number there, it's going to slow down big time. Now what I want to do is I'm going to comment these out just for a minute, because I'm only interested in factorial of 3. I want to walk through a stack example of exactly what's going on when we call factorial with a 3. We could do a 4 or 5 or a 6. If we did that, we'd be here all day drawing stuff on the stack because of the recursion. 3 is an easy number. It'll be pretty easy to do on a stack, and it won't take so long. But you'll understand exactly what's happening, and whether you use 3 or 4 or 5, you'll understand. Okay, so let's do that now. Okay, so here's my stack, and my main is on the stack. And all main is doing is it's outputting the result of factorial with a 3. So I'm just going to use fact rather than write out the entire word factorial. So main is calling factorial with a 3. And the result it gets back is going to output, right? Okay, so that's simple enough. So what happens? Well, main calls that function factorial, right? So we're going to activate that function, and we'll put it on the stack. So main is going to call factorial with a 3. So here's the activation record for factorial from this call right here from main. Notice the factorial function right here has one local variable, n. So we need to allocate storage for it. And let's say that that's n right here. And what's the value for n? Well, in this case, it's 3, right? I'm passing 3 into this function. So n is going to get a 3. Okay, now I'm going to write the code right here in the stack. The code doesn't exist on the stack. It exists somewhere else. But here you'll be able to follow it easier, I think. So what do? We start executing the code. Is n equal to 0? No, n is equal to 3. So what do? I return, I'm just going to write n, which is 3, times factorial of n minus 1. Well, 3 minus 1 is 2. So we need to call that function. So what do? Again, we transfer control to the other function. What other function is it? It's the same one. We're just calling it recursively. So in this case, what am I doing? I'm calling factorial with a 2. Factorial has an n, so we need to allocate storage for an n. It's just another activation record. In this case, n is 2. Let's start executing. Is n equal to 0? No. So I want to return n, which is 2, times factorial of n minus 1. Well, 2 minus 1 is 1. So I'm going to do that. Okay. Now, notice what just happened. I've got 2 activation records on the stack for the same function. That's the definition of recursion. All right, so now what are we going to do? We're going to call factorial with a 1. And you can see the stack just growing, right? Well, factorial is the same function. It's got an n. In this case, I'm calling it with a 1. I'm passing the n by value, so there's the 1. And what does it do? Is n equal to 0? Nope. So it's going to return n, which is 1, times factorial of n minus 1, which in this case is 0. So what do? Again, I stop and I call factorial again, in this case with a 0. So let's do that. Well, here we're going to call factorial with a 0. N gets a 0. Now we're here. This is the base case. Finally, we're going to start unwinding. Is n equal to 0? Yes. So what do? I return 1. Return 1 to who? To whoever called me. Well, here's the call right here. So the value of that call will be 1. Okay? And now what we do is we start unwinding. So this gets popped off the stack. And now we're here. Well, this guy can now return as well, right? So it's going to return 1. It's going to return 1 times 1. 1 times 1 to who? To this guy right here. So 1 times 1 is 1. And we're going to pop off the stack. So this function now is gone. That activation record gets cleaned up. And we're here. Right? So hopefully everybody's with me. It's pretty straightforward. It's just a matter of keeping all your ducks in a row. So here we're going to return 2 times 1, which is 2. To who? To this function call. That's the value of that function call. That's the 2. And again, we're going to clean up the stack. It gets popped off. That activation record, all those areas in the stack that we allocated are gone. So now we're here. Finally, we can calculate this result, which is 3 times 2, which is 6. So we're going to return 6 to who? This guy is the one that called me. That's a 6 right there, right? The value of that function call is a 6. What are we going to do now? Pop off the stack. We're cleaning up finally. You see, that's called unwinding from a recursive call. So we're here. Now we've got a 6. And what do we do with the 6? We output it. And that's the final result of the call to factorial with a 3. Okay, so you can see it's pretty straightforward. It's a matter of your recursive calls get pushed on the stack, and then you start unwinding. The unwinding is starting right there. That's the critical piece, that base case. If you forget that base case or get it wrong, then this will just keep going, and eventually you're going to run out of stack space and get a stack overflow error. Okay, so there you go. Obviously, if you remember the Fibonacci function, it's more complicated than this, right? Because let me go back to it so you can see. The Fibonacci function, which was right here, has 2 pieces of recursion, right? So we're going to have to call recursive functions, calling itself, obviously, but it's calling it twice per call. So the amount of stack space that's used is larger. That's why Fibonacci takes longer than factorial to execute, especially with very large numbers. Okay, so hopefully this diagram helps. Recursion makes a lot of sense. Once you understand what's really going on the stack, I think it totally makes sense. All right, congratulations for making it through this section. We covered a lot of material in this section. Hopefully you have a pretty good grasp of C++ functions and how they work. Now you're ready for a challenge. This challenge won't be easy. Remember the challenge from section 9? In that challenge, we had a vector of integers, and we wrote a menu-driven system that allowed the user to display the numbers, add a number to the list, calculate the mean, the smallest, and the largest. That challenge was all about applying what you learned up to that point in the course and let you use control flow statements like loops and if statements. Well, for this challenge, we're going to solve that problem all over again. Except this time our solution will be modularized in terms of functions. You can start with your solution and refactor it so that it uses functions, or you can start with my solution, which is included in the challenge project in Workspace 11. Or you could start this challenge from scratch. It's really up to you. Let me give you a few hints and tips for this challenge. Remember, this is not an easy challenge, so if you get frustrated, take a break, come back to it later. Here are a few hints. Create functions for each of the major functions in the program. Keep the functions small. Remember the boss worker analogy. Keep the vector declaration in the main function and pass the vector object to any function that requires it. Don't be tempted to move that vector object outside the main and make it a global variable. That will really defeat the whole purpose of this exercise. Now you can start by defining a function that displays the menu. That's a real simple function. Call it display menu. And all it is a bunch of output statements. And then you can call that function whenever you need to display the menu. You can then define a function that reads the selection from the user and returns it in uppercase. That way we don't have to deal with checking lowercase and uppercase selections. Then create functions for each menu option. And then finally, create functions that display the list of numbers, function that calculates the mean, a function that looks for the smallest and the largest, and so forth. Take it one function at a time and take your time. Again, if you get frustrated, take a break. Finally, don't forget to use function prototypes. Use them. Let the compiler help you every step of the way. All right, good luck. I know you can do it. When you're finished, compare it to my solution, which is in the next video. Hello everyone, welcome back. This is the solution to the Section 11 challenge, and I'm in the Section 11 workspace in the Challenge Solution project. I'd like to go over one possible solution to this project. This is a solution that I've done, very modular. All the functions are there. They're all small. They do one thing and they do them well. So let's go through this. Let's look at our main first. Let's start there. Main defines numbers, which is the vector of integers, just like we've had before. And it's got a character variable called selection. That's where the user is going to type in their selection, their menu selection. And now we've got our do loop. Our do loop, now there's, I've folded the code here. There's obviously more code here in the switch statement, but I'm just going to show you the overall structure of this loop. So here we're doing do display the menu, Notice that now we're calling a function to display the menu. Then I'm going to get the selection from the user. So whatever they type in, I'm going to store in selection. But I'm not just going to store it in selection. I'm going to make it uppercase and then store it in selection. That way I don't have to check for lowercase and uppercase every time I check for a selection. And I want to do this loop while the selection is not equal to an uppercase Q. Okay, so that's pretty much it. Now let's take a look at our display menu function. And it's right down here. And I'll expand it right now. And you can see that that's the function display menu. And all it is the output statements, just like we had before inside the main. So in this case, whenever I need to display the menu, I can call this function, and I'm doing that exactly here. Okay, now let's take a look at the getSelection function. Here's the getSelection function. And you can see the name of the function is getSelection. It expects nothing, but it does return a character. So in this case, I'm defining another character variable in here. Remember, this variable here is local to this function. I'm simply reading from the keyboard their selection, and I'm converting it to uppercase and returning it. Okay, so that's that one. So at this point, I've displayed the menu, and remember, the menu has at the very bottom of the menu, enter your choice. So I don't really need to prompt the user for anything. It's already there. So I'm displaying the menu, I'm getting their selection, and selection will now contain an uppercase character. Okay, perfect. So now we're going to switch off of that character. And let me expand the switch statement here. So in this case, if the selection is a P, I'm going to call a function called handleDisplay, because remember, P is to print out all the integers in the vector. And I'm going to pass in the vector to that function. If it's an A, I'm going to do handleAdd. M is handleMean, S is handleSmallest, L is handleLargest, Q is handleQuit, and default, I'm just going to handle an unknown. So you can see now that the logic in main is exactly like it was before, except we're calling functions. We don't have all that code written in here. Also, this allows us to think modularly, right? Now I've got functions doing those defined tasks. So again, it's that boss worker analogy at work here. It's perfect for that. Let's take a look at handleDisplay. So in this case, so the user selects P. Notice I don't have to check uppercase and lowercase anymore because the getSelection function already made everything uppercase. So I'm going to call handleDisplay, and I'm going to pass in the vector to it because obviously it needs to display the vector. Let's come over here to handleDisplay, and you can see the function right here. Now notice handleDisplay, it expects a vector, and I'm passing that vector in by reference and const. Just as we've spoken about before, this display method really has no business changing that vector, so I'm not going to even take the chance that it will. I'm passing in it by reference, so I don't have to copy it, and const. So let's take a look at that. All right, so we've got our vector here. So I'm checking to see if the size of the vector is 0, in which case it's empty, and I'm displaying the list is empty. Otherwise, I'm calling a function called displayTheList, and I'm passing in that vector. The same vector I got, I'm passing to the function. I could have looped in here and displayed the list right in here, of course, but I decided to create another function because, we could tweak the behavior of what the display looks like, and I don't want all that code in here unnecessarily. So let's take a look at displayList. It's toward the bottom. I'm going to scroll down here. There's the displayList function right here. Again, it expects the same vector that was sent to the function prior. And now if you look at the code, it's going to print out a left bracket. Then it's going to loop through that vector and print out each number, just like before. But you can see that this list displays just the list. That's all it does. And whenever I need to display a list of integers, I can just send it right into this function. Okay, so that's displayList. I'll scroll back up. And let's talk about handleAdd. So now we're here, handleAdd. It's another function. Whenever the user presses A, they want to add a number to the list, right? So I want to call handleAdd, and I want to pass the list, the vector. So let's see the handleAdd method. I'll scroll down slightly and we'll see handleAdd is right here. Now notice that in this case, I'm still passing the vector by reference because I want to add an integer to it, right? So I need to have the reference to it, but not const because I need to change it. I need to ask the user for an integer and store it in the vector. So let's look for that code. We're doing everything right in here. We're saying there's an integer called num to add. Remember your scope rules here. That integer is local to this function. I'm asking the user to enter an integer to add to the list. I'm getting that integer from them from the keyboard. And then I'm simply calling the pushback method of the vector class with the number to add and displaying the message. That's it. Really, really easy. Okay, so let me go back up to the main and let's see handle mean. How does that work? Well, we'll go to the handle mean function, which is right here. Again, it expects a reference to a vector and it's constant. I don't want my handle mean modifying the vector. So what do? We check to see if the vector is empty. If it is, we just say unable to calculate the mean, the list is empty. Otherwise, we call calculate mean and we pass in the vector. It's going to return a double to me, which I'm going to display right in here. So it's going to say the mean is whatever number I get back. All right, so let's take a look at calculate mean. I'll scroll down here. There's calculate mean. Notice again, it's the same vector, same syntax here. By reference, constant. There's my total. I'm looping through those numbers, adding them all up to total, and then I'm casting one of these to a double and dividing by the size, exactly like we had before. It's pretty much the same code that we had in the prior challenge, the section 9 challenge, except we're breaking it up into modules here. So that's it. That's calculate mean. And I think you can see where we're going with the rest of this. Here is, let me close up handle mean. We've got handle smallest, handle largest, work exactly the same way. And then handle quit and handle unknown. We're really doing very little in there, but I decided to make them functions because you never know what you need to do in there. I mean, suppose you're working with files and the user quits and you want to, close up files and so forth. I'd like to do that in a function and not here in the main. I want to keep my main really, really simple, easy to read and straightforward. So my handle quit kind of looks like this. Right here, you can see handle quit. It's all it's saying is goodbye. And my handle unknown is saying unknown selection. I guess I should spell that right. Unknown selection, try again. Okay, so that's pretty much the solution. Let me scroll up to the top and I've got all the function prototypes at the top. So there are my function prototypes. Here are the prototypes for displaying the menu and getting the user selection. Display the menu, expects nothing, returns nothing. Get selection, expects nothing, returns a character. Then I've got my menu handling function prototypes. Notice that all of them expect a reference to the vector that's constant, except handle add, because handle add needs to change the vector, so it can't be constant. Then I've got handle quit, handle unknown, and then I've got the functions that actually do the work, right? The display list displays the list, calculate mean, give me the vector, I'll give you back the double, that's the mean. Get smallest, same idea. Get largest, same idea, except we're returning an integer. Okay, so what do we want to do? Let's modify this program a little bit. Let's add some functionality to it. Suppose the user wants to see if a specific integer is in the list or not. Okay, so how do we do that? Well, there's a couple of things we need to do. Obviously, we need to do some function prototyping here. So let's do that. Let's put it right under here, under handle largest. We'll say void. How about just handle find? We're going to find an integer in that vector, right? It's not going to change the vector, but I still need the vector. So I'm going to say const a vector of integers, and I want it by reference, and we'll use the v. Again, we don't have to use the parameter names in here, but I'm going to just use the v. So that's my handle find. Okay. Now, here we need to know, so here we need a function that's actually going to do the finding, right? And it's going to return a Boolean, true or false. I really don't want to know how many times it's there. You could certainly write a function like that, but let's just call it find. And what does it expect? Well, it expects that vector to look through, right? And again, it's a vector of integers, and it's by reference. And what else does it expect? Well, it expects the integer that you're looking for. So in this case, let's just call it target. That's the integer I'm looking for. So those are my prototypes. But before we even get to those prototypes, let's fix up the menu so that it displays that F, right? So I'm going to go down to display menu, and right after display largest, I'm just going to say cout, and we'll put an F in there, and we'll say find a number. All right, so that should display now. Now what do we do? Well, we need to handle that case in main, right? So we'll do it right after the largest, right here. So we'll say case F in this case, and we don't have to worry about the lowercase because it's going to be converted to an uppercase. And we'll say handle find. And we've got numbers. All right, perfect. So now what we need to do is we need to write these two functions that we prototyped. We need to write handle find, and we need to write the find function, these two. So let's do handle find first. Right? And we'll put it right at the bottom of the handle functions, right here, right after handle largest. And we could write a comment in here, but I'm not going to right now just to save time. So there's my handle find. Okay. Now what does the handle find function have to do? Well, it has to ask the user to enter the integer they want to find, right? So let's just call it target. And we'll initialize it to 0. And we'll just say something like cout, enter the number to find, or to search for, whatever you want to call it. And we'll read that into target. Okay. Now what do we do? Well, we've got that function we still need to write, the find function that returns a Boolean. So we're going to use that right now without even writing it because we know what it looks like. We wrote the prototype for it, right? So I'm going to say if find, and I'm going to pass into it the vector and the target. Let me get rid of some of those parens. That's it. So if find that target and this vector returns true, then the integer's in there. So we could just write something like target was found. Else target wasn't found. And I'll put some new lines at the end, some end lines. That pretty much handles that function. So what do we have left to implement? Well, we need to implement, let me scroll up a little bit here. We need to implement this function right here, the one that returns the true false value. And I'm going to put that all the way at the bottom with all my other good functions that are doing work. We'll do it right after get smallest right here. Let's write it right here. And there's the prototype, right? So what am I going to do here? Well, I'm going to loop through the vector and compare each element to the target. If it's there, I'm out. If it's not, I keep looping. And if I get to the end, I never found it, right? So we can do something like for, again, auto num, for each element through the loop will be called num. And there's my collection, the vector. And we'll just say if num is equal to my target, then I'm done. I found it. I'm going to return true. Now, if we get all the way to the end of the loop, we don't want to put this here. You want to put this here. We'll just simply say return false. Right? We never found it. So let's run this. Okay, we've got an error. It says number was not declared in this scope because it should be numbers. All right, hopefully you see that error right there. It was just a typo. And let's try it again. There's our run. Here you see the F in the menu now. So let's find a number. Let's find 100. Notice how it asks me for the number to find. Now the list is empty, right? So I should not find it. 100 was not found. Goodbye. What happened? That's an error, right? I should have never printed goodbye. Let's quit and see what's going on. Aha. Need a break statement. That's why we need to test our code. Forgot the break statement. Remember, with a switch, it goes to the next one. So handle quit fired. Let's try this one more time. Okay, so let's find 100. 100 was not found. We get the menu again. Let's add 100. And let's look for it again. So I'm pressing F for find. Let's find 100. Now it says 100 was found. And let's print the numbers. There you go, 100. So we've modularized our system into a series of functions. We easily added a new behavior to this, which is defined. And you can see now the code is longer for sure because you will also have a lot of comments in here. But you've got these really well-defined logical functions that are much easier to debug now. If there's something wrong, you can come in here and tweak it. You can also extend the behavior of the ad rather than having just one big main. And if you make any changes, you're going to put all your logic in there, and that main gets out of control very quickly. Okay, so hopefully your solution, it's probably going to be different from mine, and that's perfectly fine. Hopefully it worked out okay, and if you have any comments on it, please leave them in the course forum. Welcome to Pointers and References. In this section of the course, you'll learn how to use one of the most powerful elements in the C++ programming language, the pointer. Pointers give the programmer the power to work directly with the computer's memory, and that includes allocating and deallocating memory dynamically at runtime as it's required by the program. You might have heard horror stories from other programmers about pointers and how difficult they can be to use and the damage they can cause when used improperly. You may have also heard that Java and Python and other programming languages don't have pointers because they can cause so many issues. C++ pointers give you more power over your machine than you could ever achieve with languages like Java and Python. Now, that's not a knock on Java or Python. It all comes down to why the languages were created and what domains they're typically used in. C++ programs are used extensively to develop operating systems, system software, device drivers, embedded systems, and so forth. With these systems, we want to be in complete control over the hardware. We don't want a virtual machine handling memory or checking for everything that could go wrong. We just simply can't afford that extra overhead at runtime. With this power comes responsibility. Responsibility to understand how to use and release memory efficiently and correctly. And this is one of the main use cases for pointers. In this section, we'll learn about what a pointer is. Guess what? It's a variable. That was easy, right? My point is that pointers are not this mysterious concept that's virtually impossible to understand. Pointers are easy to understand and use. We just need to learn to use them correctly. The syntax around using pointers is the part that can be a little intimidating at first, but as usual, I'll use my handy drawing pad and walk you through it all in detail. We'll learn how to declare pointers, store addresses in pointers, and dereference pointers. That means getting what they're pointing to. Then we'll learn how to allocate memory dynamically from the heap or the free store. This opens up a new world of problem solving. Then we'll talk about pointer arithmetic and see how similar pointers and arrays are. We'll also learn to do pass by reference with pointers this time, and we'll also learn how the const qualifier applies to pointers. Finally, we'll talk about some of the pointer potential pitfalls. What can go wrong and what kind of things can happen when you use pointers incorrectly. Then we'll switch over and talk about references. We've already seen references when we talked about functions in the last section. Remember how references are aliases? In this section, we'll quickly review what we learned about references in the last section of the course, and we'll see a few more ways that we can use references. Finally, everything we learn in this section regarding pointers is using C++'s raw pointers. There's a ton of code out there that uses raw pointers, and it's important to understand them completely. But C++ also has smart pointers. These are pointers that eliminate many of the safety problems with raw pointers, but are still very efficient to use. While smart pointers are used more often with object orientation and are considered a more advanced C++ topic, I'll provide an overview in this section. So that's it, a lot to cover in this section, but it's all very focused and shouldn't take too long at all before you completely understand pointers and references. First, let's see exactly what a pointer is in the next video. Before we get into any C++ code that uses pointers, let's see what a pointer is. A pointer is a variable. Okay, we know all about variables. Variables have an address in memory where they're bound to. They also have a type such as int, double, string, vector, and so forth. And they have a value which they store. A pointer is a variable, and it stores the address of another variable or function. So if I initialize an integer variable named x to 10, then x is of type integer and it's bound to some memory location and it contains the value 10. That means that I can declare a pointer variable that stores the address of x. So a pointer is a variable. That means that the pointer has a memory location where it's bound to, it has a type, it has a value, and the value is an address. We'll see how to declare a pointer in C++ in the next video. Remember that a pointer points to a variable or to a function. To use the pointer, you must know the type of what it points to. Before we learn about how to use pointers, let's see why we use pointers in the first place. If a pointer points to a variable or a function, can't I just use the variable or the function directly? Sure, and if you can, you should. There is no sense in creating a pointer to something that you can use directly. But you can't always do that. For example, if you have some complex data that's defined outside a function, and you want to access that data from within the function, you can't because the variable name is out of scope. So you can pass the data to the function by value and make a copy of it, or you can use a reference or a pointer parameter to access that data from within the function. Also, pointers are often used to operate on arrays very efficiently. In fact, we'll see in this section just how interrelated pointers and arrays are. We can use pointers to allocate memory from the heap or the free store dynamically at runtime. That memory doesn't have a variable name associated with it, so the only way to use it is through a pointer. Finally, if you're working with embedded systems, device drivers, or other types of system software, sometimes you need to gain access to a specific memory address or a range of memory addresses. Pointers is the best way to do that. Okay, now that we know a little bit more about what a pointer is and why we would use one, let's see how we can declare a pointer variable in the next video. In this video, we'll look at the syntax for declaring pointer variables. You should now feel very comfortable declaring variables. We've been doing it throughout the course. Well, we declare pointer variables in exactly the same way, except that we add the asterisk prior to the variable name. In this context, the asterisk does not function as a mathematical operator. It serves to declare the pointer. The way you read these declarations is right to left. So the first example, int pointer is a pointer to an integer. Double pointer is a pointer to a double. Notice that in this declaration, I place the asterisk next to the type. Both styles are equivalent and the compiler doesn't care. But there's been a long-standing argument among C++ programmers about which is better. I always declare my pointers with the asterisk next to the name, and that's how I'll do it in this course. But I wanted to make you aware of the equivalent styles. Char pointer is a pointer to a character, and string pointer is a pointer to a C++ string object. Just like all variables, if we don't initialize our variables, they will contain garbage data. In this case, all the pointer variables declared contain garbage data. So let's see how we can initialize pointer variables. In C++, it's very important that you always initialize all pointer variables before you use them. If you don't initialize a pointer variable, it will have garbage data. In this case, that garbage data represents an address since that's what a pointer contains. So you can think of an uninitialized pointer as pointing anywhere. So if we use it, we could be accessing memory that we have no business messing around with. We don't even know what that memory is. Initializing pointer variables is just like initializing non-pointer variables. We can use an initializer list syntax. In these examples, we're initializing the pointer variables to 0. That's what null pointer represents. This means that we're initializing the pointers to point nowhere. That's very different from pointing anywhere. We can also initialize pointers to actually point to a variable, and we'll do that in the next video. Let's review what we just talked about since it's very, very important to understand. Always initialize all pointer variables. Uninitialized pointers contain garbage data and point anywhere. Null pointer was introduced in C++11, and it represents address 0, which means that the pointer is pointing nowhere. Use null pointer to initialize your pointers unless you initialize them to a variable or to a function. This nulls out the pointer. I know I've repeated myself several times in this short video. I'm doing that for a reason. After a long career programming with many languages that have pointer variables, I can tell you that one of the most common pointer-related errors that I've seen in code reviews is uninitialized pointers. Most of the time this didn't cause a problem, but the potential for trouble is there. So always initialize your pointers. In the next video, we'll see how we can access the address of the pointer and store addresses in pointer variables. In this video, we'll learn how to access the address or location in memory of any variable. We'll also learn how to initialize a pointer variable to point to another variable. In C++, we can use the address operator, which is the ampersand symbol to the left side of an operand. The address operator is a unary operator, and when used in an expression, it evaluates to the address of its operand. Of course, the operand must have an L value, so it can't be a constant or an expression that evaluates to temporary values. In the example code, we have a variable num, which is a simple integer variable that's been initialized to 10. If we display num, then we're displaying the contents of num, which is 10. If we display the size of num, then we're displaying how much storage is allocated by num. In other words, how much storage do we need on my machine to store an integer? In this case, it's 4 bytes. Finally, if we display the address of num using the address operator, we get a hexadecimal number that represents the location in memory of the variable num. A hexadecimal number is just a base 16 number. So far, so good. You can see that the address operator evaluates to exactly what we expect, the address of the variable num. Now let's see these same statements with pointer variables. In the first line, we declare p to be a pointer to an integer variable. So that means that p can hold values that are addresses of integers. Also notice that we didn't initialize the pointer p. In the first output statement, we're displaying the value of p. The value of p is the value that's stored in p. Since we didn't initialize p, we have garbage data in p, and you can see that address displayed. In the second output statement, we're displaying the address of the variable p, since we're using the address operator. And in the third statement, we display the size of p using the sizeOf operator. On my machine, this displays a 4, which means that p is 4 bytes of storage. Since p holds addresses, this also means that addresses on my machine can be stored in 4 bytes. On the next line, we assign null pointer to p. This sets p to 0, which means it's pointing nowhere. Since p is a variable, we can change its value. This seems obvious, but it's important since when we talk about references in a bit, you'll see that you can't change a reference once it's initialized. Finally, in the last output statement, we display the value of p again, and this time we get 0 because we zeroed it out. I know these examples seem pretty simple, but please try them out on your machine and be sure you understand these fundamental concepts since everything else builds on them. Here you can see that I'm defining 5 pointer variables, p1 through p5, and initializing them all to null pointer. Each pointer variable points to a different type, so each can hold addresses of variables of the type they point to. If we displayed the size of each of these pointer variables, what do you think would display? Would the size of p1 be less than the size of p4 because p1 points to an int and p4 to a vector object? If you said 4 for each pointer, you'd be right. Based on the previous example, all pointers in my program will hold values that can be represented in 4 bytes. An address of an integer and an address of a vector and the address of a string all have size of 4 on my machine. There's a big difference between the size of the pointer variable itself and the size of what it points to. Again, take your time and make sure you understand the difference between a pointer and what it points to. It's very common to think of a pointer as what it points to, and that's a mistake. A pointer is just a simple variable. What it points to could be simple or a very complex structure. When we declare pointers, as we've done so far, they're typed pointers. This means that we explicitly declare the pointer variable to point to a variable of a specific type. In this example, we're declaring an integer score and initializing it to 10, and a double high temp and initializing it to 100.7. Then we declare score pointer as a pointer to an integer. So far, so good. Now we assign the address of score to score pointer. The compiler is fine with that, since score pointer holds addresses of integers and score is an integer. But look at the last assignment statement. In this case, we're assigning the address of high temp to score pointer. The compiler won't let you do this. You'll get a compiler error. You told the compiler that score pointer holds addresses of integers, but you're asking it to store the address of a double. Both addresses are 4 bytes long, so the issue isn't that the size won't fit. The issue is that there's a type conflict. In C++, we can also have untyped void pointers. I'm not going to talk about those, but they aren't used that much in C++. They're more used in C. Great, so let's review a very simple concept, but a very important concept. Pointers are variables, so they can change. Pointers can be null, and pointers can be uninitialized. That's not usually a good idea, but it can happen. The example code shows all these options. First, we declare 2 double variables, high and low temp, and we initialize them. Then we declare temp pointer as a pointer to a double, and we don't initialize it, so it's pointing anywhere. Then we assign the address of high temp to temp pointer, and then we change temp pointer to point somewhere else by assigning the address of low temp. Finally, we null out temp pointer by assigning null pointer. We'll come back to these pointer properties later when we compare pointers and references, and we'll go over some guidelines as to when to use pointers versus reference. Let's head over to the IDE now and go over these examples in live code. And then in the next video, we'll learn how to follow a pointer and get to the data that it's pointing to. Okay, so I'm in the CodeLight IDE and I'm in the section 12 workspace in the Simple Pointers project. In this project, we're just going to go over some real simple examples of declaring pointers, looking at the size of pointers, looking at addresses, just so you get a really good feel about what's going on here. First thing you'll notice here is that we're declaring num to be an integer, and we're initializing to 10. That's just a plain old integer variable. There's no pointer involved here at all. So in this case, I've got a variable, it's called num, and it exists somewhere in memory. Let's say it's somewhere in memory here. Obviously, that memory has to have a location, right? We need an address. So let's just say that the address is 1,000. I'll use 1,000 in these examples. Obviously, it won't be 1,000 when we display it, but it's easier to understand this way. So right now, it's got a 10 in it because we've initialized it. So that's the value of num is 10. So in this case here, I print out the value of num is num, which will display a 10. Then I'll ask, what's the size of num? What is the size of an integer on my machine? This may be different on your machine, but on my machine, an integer is 4 bytes. And then at the end here, we'll say, what is the address of num? And this is where the address operator comes in, that ampersand right before the variable name. This evaluates to the location in memory or the address of that variable. In this case, it would be 1,000, so it would print the 1,000, but obviously it won't. It'll print something different when I actually run the program. So let's take a look at the output from here. Okay, so here's the output. I'll just put this side by side so we can read it. The value of num is 10. That's exactly what we expected. And I knew that the size of an integer on my machine is 4. On yours, it might be 8. It might be 4. And then the address of num is a hexadecimal number. So this is the way that addresses are represented in C++. A hex number is just a number to base 16. So that's the address of that integer variable. Okay, so hopefully this makes sense. This is the real foundation to understanding pointers and is understanding locations or addresses of variables. So hopefully this makes sense. So let me clear this out, and then let's do this next example here. Here's where we're actually declaring a pointer. And we're doing that right here on line 17. We're declaring p to be a pointer to an integer. Remember, you read these from right to left. So p is a pointer to an integer. What is p? It's a variable. So here's p. It's got storage associated with it. And it's got a location associated with it. Let's say that the address of p is 2,000 this time. What's in p right now? I never initialized it. So there's garbage in here. There's a random bit pattern here. And as far as C++ is concerned, that random bit pattern is an address, right? Because pointers hold addresses. So this guy right now is pointing somewhere. Who knows where? But it's definitely pointing somewhere. So what's the value of p? Whatever that bit pattern is, we're going to get garbage right here. And you can see the trouble or the danger of following that pointer and putting something in this address here. That could be something pretty important on your machine and you just wiped it out. Hopefully you'll get a crash and you can fix it. Okay, so what's the address of p? Well, the address of p is the location where this pointer is stored, in this case 2,000. And then what's the size of p? How big or how much storage do I need to represent a pointer on my machine? Well, on my machine, it happens to be 4 bytes. Again, yours, it could be different. So this will print out some garbage memory address, then it'll print out the address where this variable is stored, and then it should print out a 4. So let's give that a shot. And here you go. I'll move it over here as well. The value of p is, there's the hex address. That's the garbage address. Okay. Then the address of p is at this location right here, ending in 18. And the size of p is 4. Now, on line 22, I nulled out the pointer. I said p equals null pointer. Null pointer is basically address 0, so you're just zeroing out the pointer. So if I print out now the value of p, I should get back a 0, and I do. What we're doing here is we're making this pointer point nowhere, which is real important. Okay, so let's do a few more examples. In this case, I'm declaring 5 pointers, P1 through P5, just like I did in the slides. And all of these pointers are pointing to different types, okay? So, and they're all nulled out right now. So in the case of P1, P1 has stored in memory, obviously, right? We need to allocate storage for that variable. Right now, it's null. So it's basically pointing nowhere. P2 is also a pointer. And we're allocating space for it. It's pointing nowhere. Eventually, P1 will point to an integer. P2 will point to a double. P3 will point to unsigned long, and P4 to a vector, and P5 to a string. So what they're pointing to is very different from what they are. They're just pointer variables, real primitive types. In this case, what is the size of P1? How much storage do I need to represent the address of an integer? It turns out it's 4 bytes. What's the size of P2? How much storage do I need to represent the address of a double? Again, it's 4 bytes. On my machine, 4 bytes, and I can represent any address of any variable. So what you would expect here is to print 4 all the way down. Okay, now this is important. It's really important to understand the difference between the pointer and what it's pointing to. Let's say we've got P1. Eventually, P1 is going to point to an integer, right? That's the whole idea. And P2 will point to a double. So we'll have much more storage here. And let's say P4 is over here. P4 will eventually point to a vector of string objects. So it could be pointing to a vector of string objects where this could be Larry, Mo, and Curly, where these guys are all string objects. So you can see the pointer itself is simple. The pointer itself is simple. The pointer itself is simple. They're all really simple. What they point to could be very simple, or it could be pretty complex, as you see right here. Okay, so make sure you understand the difference between the pointer and what it points to. It's really critical. So in this example, if I run it, I expect to get 4 straight down the line. And there you go. Size of P1 is 4 all the way down the line, because all I need is 4 bytes to represent any address on my machine. Again, this is very machine specific. You might have 8 on your machine. Okay, so now let's go through one more little example here. All right, so let's walk through this before we even run it. In this case, what have I got? I've got score as an integer, and I'm initializing it to 10. Okay, let's do that over here. Here's score. It's an integer, and I've put a 10 in there. Let's assume that that address is 1,000. That's where score lives. Again, it'll be different on your machine, for sure. I'm just making that 1,000 up. Then I've got a double called high temperature. Obviously, I need more storage for double, right? And this is called high temp. And right now I have 100.7 in there. And let's say that this is an address 2000. Okay, so those are the addresses for those variables. Now here's my pointer. It's called score pointer. It's got storage associated with it. Right now, I've nulled it out, so it's pointing nowhere. So far, so good. Now, this is what I'm doing here. I'm saying score pointer is equal to the address of score. I'm initializing that pointer to point somewhere now. What's the address of score? It's right here, 1,000. So I'm going to put 1,000 in here. I'm not putting the 10 in here. I'm putting the 1,000 in here. That's my pointer. So now score pointer is pointing to an integer because it holds the address of an integer. So score pointer is pointing to score. That's what we're doing right here. So now let's display what's the value of score. Well, the value of score is 10, right here. So this should display a 10. What's the address of score? In this example, it's 1,000. And what's the value of the score pointer? 1,000. And so when we run this now, we're definitely going to get a 10 here, and we're going to get, obviously not 1,000 here, but what's important is that those two numbers will be the same. They have to be the same because score pointer is pointing to score, and score has an address, which is the one that's in score pointer. Okay, so when we run this, we're expecting, as I said, a 10 and then 2 memory addresses that are the same. So let's give that a try. And this is where we're at. The value of score is 10, and then the address of score is, you can see here, ending in F0. Value of score pointer F0. So these are the exact same address, which is exactly what we expected. And then this last little compiler error here, let me show you that so that you can see the compiler error and what it looks like in case you run into it. This is a pretty common mistake, actually. What happens here is we're saying score pointer right here points to an integer, right? It holds addresses of integers, but we're trying to put in here the address of high temp. High temp is a double. The compiler is going to say, sorry, I don't know what you're talking about. You're telling me that Score pointer holds addresses of integers, but now you're trying to put the address of a double in there. I can't do that. And let's compile this so you can see what the error looks like. And it makes sense, right? It says I cannot convert a pointer to a double to a pointer to an integer. Okay, so that gives you some insight. Play around with these examples, create some of your own, walk through them, draw like I did, so you really understand these connections between the pointer variable and what it points to. In this video, we'll learn how to access the data that a pointer is pointing to. In order to access the data that a pointer is pointing to, we need to follow the pointer to where it's pointing. This is called dereferencing the pointer. Let's say that score pointer is a pointer to an integer and it has a valid address. Then in order to access the integer that score pointer is pointing to, we use the dereferencing or indirection operator, which is the asterisk. I know what you're thinking. The asterisk, didn't we just use the asterisk to declare the pointer? Yes, and lots of people over the years have been critical of C++'s choice to use the asterisk to both declare and dereference a pointer. But it is what it is, and once we understand how all this works, it isn't confusing at all. Let's take a look at the example. First, we declare score to be an integer and initialize it to 100. Then we declare score pointer to be a pointer to an integer and initialize it to the address of score. Now, score pointer points to score. If we want to get to score via the pointer, then we must dereference the pointer. Notice that in the first output statement, we're using the dereference operator on score pointer. This follows the pointer and gives us what it points to. In this case, we display 100 since score pointer points to score. When we dereference a pointer on the left-hand side of an assignment statement, this results in an L value, or the address of what score pointer is pointing to, which in this case is score. So we store 200 in that address, which is the address of score. So now we just change the value of score indirectly via the pointer. Notice the syntax makes sense. We use the asterisk to declare the pointer, and then once the pointer is declared, the asterisk is used to dereference it. Let's see another example. In this example, we declare two doubles, high temp and low temp, and we initialize them to 100.7 and 37.4. We also declare temp pointer as a pointer to a double and initialize it to point to high temp. So if we have a pointer and we want what it points to, we dereference the pointer. That's exactly what we're doing in the first output statement. We're following or dereferencing temp pointer, which gives us what it points to, and in this case, we display 100.7. Now in the assignment statement, we're storing the address of low temp to temp pointer. So now temp pointer is pointing to low temp. And again, if we want the low temp, we dereference temp pointer, and that gets us to where it's pointing. So far, I've used instant doubles, but the data type can be anything. In this case, name is a C++ string object with the value Frank. And string pointer is a pointer to a string, and we initialize it to point to name. If we dereference string pointer, as in the first output statement, we display Frank. If name then changes to James, and we execute the same output statement, then we display James. Let's head over to the IDE and we'll see some more examples of dereferencing pointers in live code. Okay, so I'm in the IDE and I'm in the section 12 workspace in the dereference project. I'd like to go over some examples of dereferencing pointers so that you're really clear as to what's going on here. Let's start with a very simple example here. And again, we'll draw it out and we'll work through it before we run it. In this case, I've got an integer called score, and I'm initializing it to 1,000. So let's say that score is over here. It has storage, obviously. We have 100 in it. And let's say that it's at location 1,000 again. So that's my score variable. Now I've got another variable right here. Score pointer is a pointer to an integer. So here's score pointer. And it's a pointer to an integer. That means it can hold addresses of integers. And I'm initializing it to the address of score. The address of score is 1,000, so we're putting 1,000 in this variable, which means that that's my pointer. So if you want to follow the pointer and get to what it's pointing to, you need to dereference the pointer. That's exactly what I'm doing right here. I'm dereferencing score pointer. So it's going to follow the pointer to where it's pointing. And in this case, it's pointing to that memory address right here, which has 100. That's what displays. In this case, I'm dereferencing the pointer again, but it's on the left-hand side of an assignment statement. Remember, the left-hand side of an assignment statement is an address or a location. That's where we want to store things, right? After all, when we're assigning something, we're storing that value somewhere. In this case, I'm dereferencing score pointer. So if I dereference score pointer, I follow the pointer to this address right here. Right? So I'm putting 200 in here now. So now when I come back and display the dereferenced score pointer, it's going to go back over here, but this time it's going to see a 200. And if I just display score all on its own, since score is that variable, right? It's going to print 200 as well. Okay, so again, play with these and you can follow these pointers around and see what's happening. So let's run this, and we're expecting 100, 200, and 200. So let's give this a run. And there you go, 100, 200, and 200, exactly what we expected. All right, let's do a few more of these. I'm going to comment out this code and then we'll walk through it together, and I'll do some diagrams as well. Okay, so in this case, what do we have? We have two doubles. We have a double called high temp, and I'll draw it over here. So this double is called high temp, and its value is 100.7. And let's again say that this is at location 1000 in memory. Then I've got another double right here called low temp. And let's say that its location is at 2000 in memory. And its value right now is initialized to 37.4. Okay, pretty easy. Now here we've got a pointer called temperature pointer. So there's my temperature pointer. It's got storage associated with it. And we're initializing it to the address of high temperature, where the address of high temperature is 1000. And there's my pointer. Okay, and when we're doing this, we always have to be sure that we have our types correct. Temp pointer can point to a double. High temp is a double. So all looks good here. Now, if we dereference the pointer right here, we're going to follow that temperature pointer to where it's pointing. It happens to be pointing here to high temp, and we display 100.7. Now what we're doing here is we're changing where the pointer is pointing to. Okay? So we're saying temp pointer now holds the address of low temp. So what we're doing is we're changing that value right here. We're breaking this link right here, and we're now putting a 2000 in here, which is the value of low temp. So this now points to low temp. And when we dereference the pointer now, we follow the pointer to where it's pointing. It's not pointing here. So in this case, it'll print out 37.4. Okay, so let's give that a run. And we've got the 100.7 and the 37.4, just like we expected. All right, now let's do a couple more complicated examples. This example isn't more complicated, but it's a little bit different. In this case, we've got a string object right here called name. And a string object is an object, so I've got my object here, and it's got a frank string in it. So that's kind of what name looks like. Let's again say that it's at address 1000. That way it's easy to follow. Here I've got a string pointer. So here's my string pointer. Again, it's a variable that points to a string object. So in this case, my string pointer holds the address of name, which is 1000. And there's my pointer all set up. Now, if I want to follow the string pointer to where it's pointing to, I dereference it right there. So in this case, I'm following the pointer to where it's pointing to, and I'm printing out what's there. In this case, Frank right here. Okay, but what if we change name? Not through the pointer, but just name itself. We can certainly do that, right? In this case, we're changing name to James. So we're changing this right here to James. And now we're coming back here and dereferencing the pointer again. We never changed the pointer. The pointer is still pointing to the same name, right? The same memory address 1000. But this time, we're going to see James there. So it's going to print James instead of Frank. Okay. This really shows you the difference between the pointer and what it's pointing to. In this case, we never modified that pointer, but the area we were pointing to was modified. So let's give this a run, and we expect Frank and James to display. And there they are, Frank and James. Okay, so let's do one last example, and this one will really show you the difference between a pointer and what it's pointing to. And let's work through this one. what we've got here is and this is where it starts right here on line 41. We've got a vector of string objects called stooges, and it's initialized to Larry, Moe, and Curly. All right, so what does that look like? Well, let's put it over here. Let's say it's called stooges. It's at a location 1000 again. And stooges is a vector. So it's a vector of 3 items in this case. And each one of those items is a string. So here's Larry, here's Moe, and here's Curly. And these are strings. I won't put the quotes around them just to save a little writing time here. So that's my stooges vector. Now I've got a vector pointer. All right, so it's right here. It's called vector pointer. It's a variable. And I'm initializing that to null pointer. Right now it's pointing nowhere. And that's perfectly fine because pointers are variables. Here is where I'm initializing my vector pointer to point somewhere. So at this point, I'm saying vector pointer is the address of stooges. Well, the address of stooges is 1000. So I'm putting 1000 in here now. So it's no longer a null pointer. And I'm pointing there. So now, how do I work with that vector through the vector pointer? It's really straightforward as long as you've got your syntax correct. And the way it works is very, very logical. So suppose I want to print out Larry, just Larry, and I want to go through this pointer. I don't just want to say stooges. Obviously, I could say something like stooges.at0, right? That'll definitely print out Larry inside an output statement. That's basically what I want to do, but I want to do it through the vector pointer. So what do? Here's the syntax right here, and I'll go over it really carefully here. So I take my vector pointer, and I dereference it. That gives me the vector that I'm pointing to. I put some parens around it because I want the priority to be high here. That gives me the vector. So all I need to do now is say dot at 0. Remember, if I follow my vector pointer, what do I get? I get stooges. So that's effectively the same as doing that. So when I execute that code right there, it'll print out Larry. Okay, hopefully that makes sense. It may take a little bit to understand, and these parens are critical right here because we want to dereference that pointer before we use a dot because the dot has higher precedence than the dereference operator. So it's important that you put those parens around there. Okay. Suppose I want to print out all of the stooges through the vector pointer. Same idea. What we can do is we can use a range-based for loop. And what's the collection? Well, the collection is not vector pointer. It's what vector pointer is pointing to. So if I dereference vector pointer, then really what I'm getting in here is stooges, right? That's what I'm pointing to. And now you can see the syntax is really straightforward. For every stooge in stooges, print it out. So it's going to print out Larry, Moe, and Curly. Okay. Again, we're following that vector pointer. We get the vector, and then once we're at the vector, we can do whatever we want. So here's an example, again, of really distinguishing between the pointer and what it points to. Remember, pointers are simple. It's just a simple variable that holds addresses. What it points to can be super complicated. I mean, we can have vectors of vectors of vectors, and we can certainly get to them through the pointer by dereferencing the pointer. Once we have them, we can do whatever we want with them. Okay, so that finishes up this video. Okay, so now that we understand the basics of C++ pointers, let's talk about one of the main use cases for pointers, that is dynamic memory allocation. When we're developing software, we often have no idea how much storage we're going to need to model our data. For example, if I'm modeling the students in my class, how many students do I allocate storage for? If I'm using an array to model the students, then I need to know exactly how many students I have, since once I allocate an array, it's fixed in size. I know what you're thinking. Hey, didn't you tell us earlier that we should be using vectors instead of arrays? Yes, I did. And that's still true. However, it's important to understand how to allocate memory dynamically, not just for arrays, but for other data, including objects. Also, how do you think vectors work behind the scenes? They use techniques to allocate and deallocate memory from the heap. So we really need to understand how that works. In this video, I'll go over the basics of allocating memory dynamically from the heap. All memory that's allocated dynamically via a pointer comes from the heap or the free store. As I said, we'll use dynamic memory allocation again later in this course in the context of object-oriented objects. So how do you allocate storage at runtime? Let's see. We use the new keyword to allocate storage at runtime. In this example, we declare int pointer as a pointer to an integer. Rather than assigning the address of some integer variable, as we've done previously, why don't we create an integer at runtime that's on the heap and store that variable's address in int pointer? That's pretty cool. You can see how easy it is. Int pointer equals new int. That's it. That's all it takes. This allocates storage for an integer on the heap and stores its address in int pointer. Now we can use the pointer to access the integer. The first output statement displays the value of int pointer. This is the address of the newly created integer. If we want to get to that integer, we need to dereference the pointer. But notice what gets displayed, a really large integer value. That's because the integer that was allocated hasn't been initialized yet, and it contains garbage data. So in order to assign a value to that integer on the heap, we dereference the pointer to get to the integer, and then store 100 in it in this case. Now when we display the value of the integer, we get back 100. That's pretty cool. A couple of things to understand. When you allocate storage in this manner, the storage is on the heap. The allocated storage contains garbage data until you initialize it. The allocated storage does not have a name. The only way to get to that storage is via the pointer. If you lose the pointer because it goes out of scope or you reassign it, then you lost your only way to get to that storage and you have a memory leak. I'll talk more about that later. Finally, when you're done using the storage, then you must deallocate the storage so that it's again available to the rest of the program. Let's see how. Here you see that we again have declared int pointer as a pointer to an int. Then we assign new int to int pointer. This statement allocates storage for an integer on the heap and stores the address of that integer in int pointer, just like before. We can use the pointer as we wish, and then when we're done, we need to release or deallocate the storage that we allocated for that integer. We can do that easily using the delete keyword followed by the name of the pointer. Make sure that the address in the pointer is an address of storage that was allocated using new. We just saw an example of allocating a single integer dynamically. You can do the same with doubles, strings, vectors, and so forth. But in this slide, we'll do something a little more useful than allocating a single integer. How about we allocate an entire array of integers on the heap at runtime? In the sample code, we declare a pointer to an integer called array pointer and an integer named size. We ask the user how big they want the array to be. This could be the number of scores on an exam or the number of temperatures to read and so forth. Then we use the new operator with square brackets this time and the number of elements to allocate inside the brackets. This will attempt to allocate that many integers on the heap contiguously in memory. If the storage is successfully created, then the address of the first integer is stored in array pointer. That's pretty easy. Of course, when we're done with the memory, we need to release it or deallocate it. Let's see the syntax for that. Here's the same code example, but the last statement deletes the entire array that we allocated dynamically. Notice the square brackets between the delete and the name of the pointer. These brackets must be empty. Do not include anything inside the brackets. Okay, let's go to the IDE and create some storage dynamically. Okay, so I'm in the IDE. I'm in the Section 12 workspace in the Dynamic Memory project. What I want to do in this little example is allocate a single element on the heap. In this case, we'll do an integer and point to it from a pointer. Okay, and we're going to use the new keyword to do that. And then after that, we'll allocate storage for an array like we did with the slides. All right, so let's do this first. We need a pointer. We need a pointer to an integer. And you know what? Before we do that, let's talk about exactly what's going on here. If you remember when we talked about our memory model earlier, we've got our memory model here where we've got our code is down here. Then we had our global variables. And then we had our stack right here, right? And our stack is where the function calls happen. And this is push pop. So we're pushing and popping activation records on here, just like before. Well, we also have a part of memory called the heap. It's also called the free store. All dynamic allocation happens here. Okay, we can't really do dynamic allocation on the stack. It's already doing dynamic allocation when we push and pop activation records. but we can't really decide at runtime how big those things are going to be. We can to a point, but not really. The heap is a free-for-all. We've got a whole bunch of memory out there, and we can request that we get 1,000 integers, 2,000 integers, 15 objects, as much as we want. But we need to take care of that heap, and we need to release the storage when we're done. So that's the kind of thing we'll do here. Now, what I want to do is I want to create an integer pointer that's going to be in main, so it's going to be on the stack. And I want to allocate an integer on the heap. So I want to allocate an integer dynamically on the heap, and I want to point to it from that pointer. Okay, that's what I want to do first. Then what I want to do is I want to allocate an array of doubles, let's say, in this case, on the heap again. And how big is it going to be? I don't know. I'm going to ask the user how many doubles they need. And then what we'll have is we'll have a pointer to doubles in this case that's going to point to there. Okay, so that's what we're going to do. Let's start here. Let's do the integer first. We need a pointer to it. So we're going to have an integer, and we'll initialize it to null pointer. That's our best practice. So what we've done now is we've got a variable. Remember, it's a variable called int pointer that points to an integer. So it's going to hold addresses of integers. Right now, it's pointing nowhere. Okay. If we want to allocate this dynamically at runtime from the heap, we just say int pointer equals new, and then followed by the type that I want to allocate. In this case, int. Okay. Now what's going to happen is that storage for an integer is going to be allocated on the heap, and its address will be stored in int pointer. Okay, so we can just do something like display int pointer, and that will display the memory location where that integer is on the heap. Remember, that's the address that's stored in int pointer. Okay, so let's run that, and you can see that that hex address right there, that's where that integer lives on the heap, and our pointer is now pointing to it. It's important to understand that that integer that we just created on the heap has no name. There's no way to get to it except through this pointer. So if I lose the pointer, I've got something called a memory leak, which I'll talk a little bit about later. Okay. So at this point, we can use this integer however we like, and when we're done, we need to delete it. So the syntax for that is simply the keyword delete followed by the name of the pointer, which in this case is int pointer. That frees up the storage. Okay, so pretty easy. Now what we'll do is, let me clean up a little bit of this white space here. Now what we'll do is we'll create a whole contiguous block of memory on the heap. Okay, and we'll do doubles this time. So there's two things here. We don't know the size, so we have to ask the user, how many doubles do you need? And we also need a pointer to that area. So we declare both of those right now. The size, we'll declare it as a size type, and we'll just call it size. We'll initialize it to 0. And the pointer will be a pointer to doubles. And the name of the pointer, let's just say temp pointer. So it'll be like temperatures. And again, we'll initialize it to null. So we're good to go here. So let's ask the user. So we'll ask the user, we'll say how many temps, right? How many temperatures do they need? And we'll read that into size. So now we know how many temperatures to allocate. So if they typed in 50, 100, 200, 10,000, whatever they typed in, that's how much storage we're going to allocate. So what do? We use the pointer. We're going to say temp pointer equals new. What am I allocating? Well, I'm allocating doubles in this case. And how many? Size. This is where you put the size in the square brackets. That's going to allocate that chunk of memory, happens to be an array in this case because it's contiguous doubles in memory, and store the address of the first one into temp pointer. Okay, so at this point we can say cout. Let's say temp pointer. See what's in there. Obviously it's an address of that first double, right? And let's run that real quick, see what we get. So how many temps? Let's say 100 temperatures. And you can see right there, that's the area in the heap that contains the address of the first of those 100 doubles. Pretty easy. Now when we're done, what do? We always need to free up the space that we allocated. So we can say delete. In this case, we allocated an array right there. You've got the square brackets in the new call. So here you've got to put the square brackets in the delete. Nothing inside the square brackets. And then the name of the pointer, which was temperature pointer. That's it. That's the entire program, and you could see what's happening at this point, right? What we did was we had, and I'm not going to draw the whole stack again, but we had that temp pointer right here that was on the stack. We allocated, let's see, 100 doubles on the heap. Temp pointer is pointing to the first one. Okay, that's really what's happening. This is on the heap. And in this case, temp pointer was on the stack because it's local to main right here. Notice what happens if we lose this pointer. I mean, if we do something really silly like, I don't know, temp pointer equals null pointer, right? And we do that before we did this. And what just happened? Well, we just nulled out this pointer. So this is gone. We just lost our only way to get to that storage. And that's called the memory leak. Okay. What the delete call does is it frees up this storage again. Your pointer is still pointing to it. And that's important because if you try to use that pointer again after you've deleted the storage, you could have really, really unpredictable results. But in this case, you don't want to lose your pointer to dynamically allocated memory because then it's basically orphaned out there, and that's the memory leak. Okay, now let's see what happens if our call fails, our call to allocate the size here. Now I'll do something that you should never do, but I'm going to create an endless loop here. I'm just going to say while true, allocate that. So this is I'm going to ask the user, how many temperatures do you want to allocate? I'm going to type something like 10,000. And then what I'll do is I'll just keep looping, allocating, and creating memory leaks all over the place. Eventually, we're going to run out of memory in the heap. So eventually this will fail, and I should get an exception. So let's see what that looks like. How many temps? Let's say a lot. Now remember, it's going to be in an infinite loop doing this over and over and over. And there you go. That was pretty fast. You can see terminate called after throwing an instance of standard bad alloc. So basically what happened was the call to new failed. There was no more memory available. And this is the exception that's thrown. We'll talk about exception handling a little bit later in the class, but what you want to do is you want to catch that exception. You don't want your program to just stop like that. You want to catch the exception, and if you can deal with it somehow, maybe you've got memory and caches and temporary stuff that you can free up to free up some memory, and then you can reallocate this memory again, trying to call new again. So this is, again, I'm going to delete that. That's not a good idea. But that's basically it. In the next video, we'll talk about the relationship between arrays, which is really what's going on here, and a pointer. You can see they're really almost the same thing here in this case, and how we can actually use that array that's on the heap from our code. So I'll be right back. So at this point, you may be wondering how we can allocate an entire array of integers and store its address into a pointer to an integer. That's a good question, and it's critical that you understand the relationship between arrays and pointers in C++. Remember that the value of an array name is the location or the address of the first element of the array, and the value of a pointer is an address. So if a pointer points to the same type of data as the array elements, then the pointer and the array name are the same as far as C++ is concerned. The only difference is that the array name is not a variable, so you can't change it. But otherwise, all the calculations done to access array elements can be done with the array name or the pointer name. In this example, we have scores as an array of 3 integers. If you display scores, then the value of the array name is the address of the first element of the array. What if I dereference scores? Wait a minute, scores is an array. How can I dereference that? Sure, scores is the address of the first array element. So if I go to that address, which is what dereferencing is, I get the integer. So the output statement for dereferencing scores displays 100, the first array element. Now if I declare score pointer as a pointer to an integer, and I initialize it to scores, notice that the value of score pointer is the same as scores. So when I dereference score pointer, we get the same results, the value of the element at that location, which is 100 in this case. I know this can be a bit confusing, and when we head over to the IDE, I'll draw it out visually so you can see exactly what's happening. So if we can pretty much use an array name and a pointer name interchangeably, that means we should be able to use array subscripting on a pointer, right? And that's absolutely correct. If score pointer points to the first element of the scores array as it does in this example, then when we display score pointer sub 0, we get 100. Score pointer sub 1 is 95, and score pointer sub 2 is 89. That's weird, right? Well, not really if you understand that C++ doesn't really have true arrays, and that arrays are just the address of the first element in a chunk of memory. Then this makes sense. So does that mean that we can add the offset to the pointer variable? Then we can make it point to any array element? And again, yes, it does. Let me show you how. We're using the same example here. Notice that when we display score pointer, we get back an address. If we add 1 to score pointer, then you can see that the value of score pointer has increased by 4, not by 1. Why? Because we're not adding 1 to the pointer value. We're adding the size of one integer to the pointer value. The pointer doesn't hold integers. It holds addresses of integers. So when we add 1, we're adding the address of the next integer, which is 4 bytes away. If we add 2, we increment score pointer by 8, which is 2 integers away. This is the basis of pointer arithmetic, which we'll talk about in the next video. Once we have score pointer pointing to the integer that we want, we can simply dereference the pointer to get to the integer. Let me show you how that works. Here's the same example, except that I'm dereferencing the expression. Notice that how we follow the pointer and display the integer that we point to. In this case, we're moving along the array using the pointer. That's pretty cool. Let's see this all together so it makes more sense. This table shows the equivalence between arrays and pointers. Notice that we can access array elements using array subscript or pointer subscript notation, using either the name of the array or the name of the pointer. You can also see we can use array offset or pointer offset notation, also using either the array name or the pointer name. Take your time with this. I know it can be confusing, but when it clicks, you'll be able to easily understand more advanced memory allocation principles. Let's head over to the IDE and we'll go over some of the examples in this video. Okay, so I'm in the IDE. I'm in the section 12 workspace in the arrays and pointers project. I've gone ahead and written some code that uses array subscript notation, pointer subscript notation, pointer offset notation, and array offset notation, just so that we can walk through this and you can really understand the equivalence of pointers and arrays in C++. So let's get started here. First of all, I've created a scores array of integers right here. And I've initialized it to 195 and 89. And that's it over here in this little box over here. So this is 100, this is 95, and this is 89. And it's scores. And let's assume that this is at location 1000. Okay. So what that means is that this integer 100 is at location 1000. This integer 95 is at location 1004, assuming that we've got 4-byte integers, which I do on my machine. And this 89 is at location 1008 in memory. Okay, we know they're contiguous because it's an array. Perfect. So when we display scores here, the name of an array is the address of the first element in the array. So in this case, it's 1000. So we expect this to print 1000. Now, obviously, when I run this on my machine, I'm going to get a different value, but that's okay. Now I've created another variable right here called score pointer. Okay, so I'm going to put this guy, actually, I'm going to put him right here, score pointer. And score pointer, we're assigning to score pointer scores. Scores is the array name, which is the address of the first element in the array. So score pointer was have 1000 in it right now. And there's my pointer. Okay. There's no need to put the ampersand here, ampersand score, since score, the name of the array already is an address. So now we print out the value of score pointer. Well, it's 1000. So these two values will print the same because they are the same. The name of the array, and we just stored the name of the array, which is the address, into score pointer. Okay. So now let's do array subscript notation. This is what we've been doing all along. Scores is an array, so scores sub 0. Now look at what the compiler is doing here. The compiler is saying scores sub 0 is really 1000, right? That's what scores is, plus 0 integers away. So that's going to be 1000. So it's going to grab whatever is that location 1000 and display it, which is in this case 100. What about scores sub 1? So in the case of scores sub 1, it's going to have scores again, which is 1000. and it's going to go 1 away from that. And it's not going to be 1001. It's going to be 1 integer away from it because it knows that scores is an array of integers. So in this case, it's going to be 1004. So it's going to go to 1004. It sees the 95 and displays that. Then the same thing with score sub 2 will display the 89. Okay, that's using array subscript notation. Now, take a look at pointer subscript notation. It's exactly the same. The only difference is that I replaced scores with score pointer, right? Therefore, we've got pointer and subscript. So again, score pointer sub 0. What is score pointer? 1000 in this case, right? It's right here. Plus 0 away. So it's going to go to location 1000 and grab what's there, which is going to be 100. Remember, when we use subscript notation, we're basically grabbing what's at that address. Same thing with score pointer sub 1. It's going to go to 1000 plus 1 integer away, which is 1004. And there's the 95. And here's the 89. Okay, so hopefully that makes sense. Now, here we've got pointer offset notation. We don't have any square brackets, so we're using the offset. Now, let's start right here. What happens if I dereference score pointer? Follow the pointer to where it's pointing. Score pointer is 1000. I'm going to dereference it, which means I'm going to go to that location. Now I'm here. And what do? I display 100. Now, what about this line right here? Let's go with that one carefully. We're going to say score pointer plus 1. Now, notice the parentheses, and then we dereference. So what happens first? What's in the parentheses? What's score pointer? 1000. It hasn't changed. Plus 1 what? Plus 1 whatever score pointer is pointing to. Integer in this case. So 1004. I'm dereferencing 1004, which means I'm going to 1004 and getting what's there. That's the 95. Same thing here. I'm going to 1008 and getting what's there, which is the 89. Okay, so there's pointer offset. And then the last one is array offset. Notice here I'm using scores. Well, what is an array name? Well, an array name is the address of the first element in the array, right? So dereference scores is the same as saying scores sub 0 here. So in this case, scores is 1000. So go to 1000 and grab what's there. Display 100. Okay. Here we've got scores plus 1 dereferenced, right? What's scores? The name of the array is the value of the address of that first element right there, 1000, plus 4, right? And I'm dereferencing that again. So you can see it's exactly like what we did with pointer offset. So we've got 95 and 89. So the output from this program is going to be exactly the same. Array subscript, pointer offset, and array offset. They're equivalent as far as C++ is concerned. Now, why is this important? This is important because when we allocate arrays dynamically on the heap, we have to be able to walk them, right? Use them, display them, change them, do whatever we like with them. Well, we have a pointer to them, right? That's what we got back when we newed that storage. That pointer to that array, it's going to be a pointer. So we could use pointer subscript notation if we want. We could use pointer offset notation if we want, right? Either one we can use, and we're able to get to that array and those array elements really, really easily. All right, so let me run this, and we'll be sure that we get the correct values. And you can see here, this is the important piece. The value of scores is that hex address right there, and the value of score pointer is the same hex address. Makes sense, right? Because we assigned scores to the score pointer. And scores is the address of that first element in that array, 100. Then we go through array subscript notation. We print out 195, 89. You can see pointer, subscript, pointer offset, and array offset. It's all exactly the same thing. Okay. Take your time, understand this, walk through it, play around with it, change a few things if you like. It's really important. Once you understand the equivalence of arrays and pointers in C++, it really opens up the world of power. In this video, we'll learn about pointer arithmetic in C++. In C++, pointers can be used in assignment expressions, arithmetic expressions, and comparison expressions. C++ allows a subset of the arithmetic operators to work with pointer variables. Pointer arithmetic operators only make sense when you use them with raw arrays, but they're a very powerful way to manipulate them. Let's start by looking at the increment and decrement operators in the context of pointers. The increment operator increments the address stored in a pointer variable so that it points to the next element in contiguous memory. So, if integer pointer is currently pointing to address 1000, then integer pointer ++ will increment it by the size of whatever it's pointing to. In this case, an integer. It's 4 on my machine, so now we will point to 1004. In the case of a double, it would be larger. If a pointer is pointing to the address of a very large data type, then the increment operator would increment it by whatever the size of that large data type is. The decrement operator works exactly the same way, except that it decrements the values stored in the pointer variable. We can also use the addition and subtraction operators with pointers. The addition operator determines the operand on the right-hand side of the expression and multiplies that number by the size of the element, and that's what's being added to the pointer. So adding 2 to an integer pointer increments the pointer by 2 times the size of an integer. Obviously, pointer arithmetic is machine-specific since the size of C++ types vary from machine to machine. The subtraction operator works in the same way, except that we're decrementing the pointer's value. What do you think is the result of subtracting one pointer from another? Well, if both pointers point to the same data type, then the result will be the number of elements between the two pointers. If the pointers point to different data types, then you'll get a compiler error. Finally, let's see how we can compare pointers. We can compare pointers with the equality operators. If we want to compare two pointers, we can simply compare them using the equal or not equal operators. But be aware that this will compare the values of the pointer variables. So if the pointers are pointing to the same address, then they're considered equal. Otherwise, they're considered not equal. The data that they're pointing to is not considered when checking for equality. The sample code shows an example of comparing pointers. In this example, P1 and P2 point to different addresses, and P1 and P3 point to the same address. So you can see that if we compare P1 and P2, we get back false. And if we compare P1 and P3, we get back true. All three pointers point to strings with the value franc, but that's not considered when you want to compare pointers. So how do you compare what the pointers are pointing to? Simple. Just follow the pointers, dereference them, and then check what they're pointing to. I'll show you an example next. Here we have the same example, except that we're dereferencing the pointers before we're comparing them. So in this case, P1 and P2 point to different strings, but those strings both happen to be franc. So this will display true. P1 and P3 point to the same string, which is franc. So this will also display true. So that's an intro to pointer arithmetic. Let's head over to the IDE and I'll show you some more examples. Okay, so I'm in the IDE and I'm in the section 12 workspace in the pointer arithmetic project. So let's go over a couple of examples of pointer arithmetic. You can see here that I've got a scores array, which is an array of integers, and I've initialized it to 100, 95, 89, 68, and -1. I'm using the -1 as a sentinel because what I want to do is I want to loop through this array, and when I see -1, I want to stop. Okay, so I also have, and this is called scores. That's the name of this array here. Then I've got my score pointer, and I'm initializing two scores. So right now it's pointing right here. Let's say that this is address 1000, 1004, 1008, and we'll use decimal here, 1012, and 1016, assuming 4-byte integers here. Okay, perfect. So now let's loop through this array using the pointer. Okay, so what I'm doing here is I'm dereferencing score pointer. So follow the pointer to where it's pointing. And then I'm checking the value at that location to be -1. Okay. So I want to loop while it's not equal to -1. So I want to loop through this here. Once I see -1, I want to stop. Okay, so that's what's going to happen here. So score pointer right now is pointing to memory location 1000. I'm going to dereference that. I've got my 100. It's definitely not equal to -1. So what am I going to display? I'm not displaying score pointer because that would display 1000. I'm dereferencing score pointer, and that'll display the 100. Okay. Now we get into the pointer arithmetic. What we're saying is score pointer plus plus. In other words, increment the score pointer. Well, what do we increment it by? We're incrementing it by whatever it's pointing to. So in this case, by 4, because I've got 4 byte integers. So this will no longer point here. It'll now point here. We go back up to the loop. We check to see if we're pointing to -1. We're not. And we display our dereferenced pointer, which is now 95. Again, we point to the next one. Now we're pointing to 1008. It's not -1, so I'm going to display that 89. I'm going to increment my pointer again. Now I'm pointing to address 1012, which is again not equal to -1. I'm going to display the 68. And now I'm going to increment my pointer for the last time right here. I check to see that my pointer is not pointing to -1. Well, it is, in this case, my dereference pointer. So I stop. So this is the way you can loop through an array using a pointer and a sentinel value in this case. This is called a sentinel value. And this is commonly used. It's a terminator, basically. So you keep looping until you hit a terminator. Okay, so let me clear this and let's run this. And we should see those array elements display. And there they are, 195, 89, and 68. Those are our 4 array elements. We don't display -1 because that is our sentinel. Okay, so that's a simple example of pointer arithmetic. Now let me show you another way to do this that's commonly seen. Okay, so everything's exactly the same, except that you'll notice right here in the previous example, we had 2 lines of code. One dereferenced the pointer right here, and then the other one incremented the pointer to point to the next integer in the array. Here we're doing it all in one. So we've got this piece of code right here. So we're saying dereference score pointer and increment it. Okay, so there's a lot going on here, and it's important to understand what's going on. First of all, we have 2 operators. So the first thing we do is we look in the precedence chart to see which one has precedence. Well, they both have the same precedence. So in this case, what we do is we look at the associativity. The associativity is right to left. So what that means is that I'm incrementing score pointer. So I'm incrementing the pointer. I'm not incrementing what it's pointing to. If I had something like this, that's real different now, right? Because what I'm doing here is I'm dereferencing the pointer. So I'm getting the integer it's pointing to, and then I'm incrementing that integer. But that's not what we're doing here. In this case, what we're doing is we're dereferencing the pointer and we're incrementing the pointer after we use it. Well, the use is right here. The use is basically dereference the pointer and then increment the pointer. So it's exactly what we're doing here, right? We're doing dereference the pointer and then increment the pointer. But this you see a lot in C++ code, right? You dereference and an increment or a decrement if you want to go the other way. If we run this example, let me clear this real quick. If we run this example, you'll see that we get exactly the same output. 195, 89, 68, exactly the same thing. Okay, I just wanted to show you that style because you tend to see this sort of style a lot out there. Okay, so now let's do another example. Let me scroll up just a little bit and let's see how we can compare pointers in this example. So let's, right about here, I'm going to comment this code out, or I should say uncomment this code, and let's go through this. So here I've got 3 string objects, S1, S2, S3. So they're here, S1, S2, and S3. S1 points to a string Frank, S2 also a different string Frank. It's the same Frank, but in a different memory location. And S3 is James. Okay. Now, each one of these objects has a memory location associated with it, right? So let's say that this one is at 1,000, this one is at 2,000, and this one is at 3,000. That way, it's really easy to keep them straight. Perfect. Now, here we go. Now we've got P1 is a pointer to a string, so it can hold addresses of strings. Those guys right here are addresses of strings, so we can assign any of them. So let's do that. So what is S1? S1 is the string object right here. So we can assign the address of S1 to P1. So P1 now has 1,000 in it. And there's my pointer. Right? P2 is the address of string 2, which is 2,000. And there's my pointer to that one. And now P3, we're assigning the address of S1 again. So there's the 1,000. and P1, P3 goes around this way. Let me do it that way. It's pointing there. Okay. So now I'm using the bool alpha modifier, so we just print true and false. So let's do some comparisons here. Does P1 equal P2? Well, P1 is 1,000, P2 is 2,000, so no. Right? They both point to strings who are frank, but we're not considering what they're pointing to. We're only considering the value of P1 and the value of P2, which are definitely different. So we get back false. How about this? P1 and P3. Well, P1 is 1,000 and P3 is 1,000. So that's definitely true. Okay, so notice that we're checking the pointer's value, not what it's pointing to. Now, if we want to look to see if we're pointing to the same string, then what we do is we dereference the pointers here. Okay, so you can see here, this will output P1, right? Follow P1, so dereference P1. If I dereference P1, I get Frank. So this will say Frank compared to dereference P2, follow P2, I get Frank again. Frank is Frank. That's true, because now we're comparing the strings, not the pointers. Now over here, we've got P1 and P3. P1 and P3 both point to the same memory address, so obviously what they're pointing to is the same. And in this case, Frank is Frank also. But now let's say we change P3, and we change the pointer in P3 to point to S3, the address of this guy right here, 3,000. So this is now 3,000. We're pointing here, no longer pointing here. Now what we're doing is we're dereferencing P1, which points to Frank, and we're dereferencing P3, which points to James. So now what we're doing is we're comparing the string Frank and the string James, which we get back a false. Okay, I know it's a lot of pointers to follow, but it's pretty clear once you really take your time and walk through it. So let's clear this and give this one a run. And like I said, you can play with this code so you can see what's happening here. Right. This address and this address are not true, not the same. So obviously those pointers are not the same. In this case, it is the same address. So we have a true. And then we're comparing Frank and Frank, which is true, Frank and Frank, which is true, and Frank and James, which is false. In the bottom three examples here, we're actually comparing the strings, not the pointers. Okay, so let's do one more with subtraction so you can see what that looks like. And I'll uncomment all this out. And we'll walk through this example. This is a real simple example here. In this case, what have I got? I've got name, which is an array of characters, right? So I've got F, R, A, N, K, and the null character, because this is a C-style string. So I've got character pointer 1. So I've got character pointer 1. It's a pointer to a character, so it can point to any one of these guys here. And I'm initializing that to null pointer. And then I've got character pointer 2, both nulled out. Okay, so now what do? I'm saying character pointer 1 is pointing to the address of name sub 0. What's name sub 0? That F right there, the address of F. I could have just said name. It means exactly the same thing, but I wanted to do it a different way so you could see. So character pointer 1 is pointing here. And character pointer 2 is pointing to, remember, 0, 1, 2, 3, 4, 5 in this case, right? So it's pointing to the address of name sub 3, which is the N. Right. Now, assuming that characters are 1 byte, this would be 1,000. This one would be at 1,001, 1,002, and 1,003. Right. So this would be 1,003, and this would be 1,000. So when I subtract those two pointers, like I'm doing right here, it's subtracting 1,003 from 1,000. And that's what I'm getting back. There's 3 characters between those two pointers. And that's all the pointer subtraction means. Right. So let's give this a run. And the last example here says in the string Frank, N is 3 characters away from F. And that's exactly what we expected. Okay, so this gives you a little bit of a intro to pointer arithmetic. You can see it's pretty straightforward. Never think of adding 1 or adding 2 or adding 3. I always think about adding one of the type that I'm pointing to. It could be 4 bytes, 8 bytes, 100 bytes, depending on what I'm pointing to. In this short video, we'll see how the const qualifier affects pointers. We've already seen that the use of const with function reference parameters essentially makes them read-only. In C++, we can qualify a pointer in several ways. First, we don't have to use const at all. In this case, we have a pointer just as we've been using up to this point. We can change the data the pointer is pointing to, and we can change the pointer itself and make it point somewhere else. The const qualifier gives us more fine-grained control of what we allow to be changed. We can have pointers to constants, constant pointers, and constant pointers to constants. These will be very useful when we pass pointers to functions in the next video. Let's take a look at each one of them. In the case of pointers to constants, the data pointed to by the pointer is constant and can't be changed. However, the pointer itself can change and point elsewhere. Let's take a look at this example. We have two integers declared and initialized. These are high score and low score. But this time, when we declare the pointer, we use the const qualifier before the type that we point to. So, score pointer is a pointer to an integer constant, and we initialize it to point to high score. If we attempt to change the value of the pointed to data, in this case high score, we'll get a compiler error. However, we're free to assign another address to the pointer and have it point somewhere else, as we do in the last assignment statement. In the case of constant pointers, it's the pointer itself that's constant. So the data pointed to by the pointer can be changed via the pointer. However, the pointer itself cannot be changed and can't point to anything else. Notice that we still use the const qualifier. However, we use it before the asterisk in the pointer declaration. So we're declaring score pointer as a const pointer to integer. All right, let's look at the last case. In this case, it's a constant pointer to constants. We need to use the const qualifier twice in the pointer declaration. So the data pointed to by the pointer is constant and can't change, and the pointer itself is also constant and can't change. Notice the syntax. Score pointer is a constant pointer to an integer constant. In this case, if we try to modify either the data or the pointer, we get compiler errors. The const qualifier is very useful, and it's often used when passing pointers to functions. We'll see that in the next video. In this video, we'll see how we can do pass by reference using pointer parameters. In C++, we can use pointers and the dereference operator to achieve pass by reference. In this case, the function parameter is a pointer, and the actual parameter can be a pointer variable or the address of a variable. Let's see what this looks like syntactically. Here we're declaring a function prototype and then defining the function. The function is called double data, and it expects a pointer to an integer as a parameter. Notice it doesn't return anything. Instead, it will double the contents of the data the pointer points to. So in the body of the function, we simply dereference the pointer and multiply the value it points to by 2 and assign it right back. I've written this using a compound assignment statement, but I've also written out the long form of the assignment statement just in case the compound assignment is confusing. I also chose to multiply by 2 on purpose, since this uses the asterisk as the multiplication operator. Keep them straight. Don't let the syntax confuse you. In one case, the asterisk is multiplication, and in the other, it's indirection or dereference operator. Okay, so how do you call this function? Let's see that in the next slide. We know that since the function parameter is a pointer to an integer, that means it expects the address of an integer. Well, in this case, I have an integer named value, and it's initialized to 10. I can call double data with the address of that integer using the ampersand, which is the address of operator. When I return from the function, I now display value, which has doubled to 20. Let's head over to the IDE and see this and other examples of pass by reference with pointers. Okay, so I'm in the IDE, and you can see that I'm in the Section 12 workspace in the Passing Pointers 1 project. We'll go over a couple of different projects that do pass by reference using pointers a little bit differently from one another so you can see exactly what's happening, and I'll walk you through these in detail. You can see here that we've got the same function that we wrote in the slides right here, double data. It expects a pointer to an integer, and all it does is it doubles whatever it's pointing to, right? So whatever integer it's pointing to is just doubling it. And here's my main, which we're going to run. We're going to run main a couple of different ways. First, this part right here, and then the second part right here. This you'll see is using the address of a value, and this is using an actual pointer. So it's two different ways to pass really the same information in. Okay, so let's start running this. We've got our main and it's activated on the stack right here. You'll notice main has two local variables. It's got an integer value and it's got an integer pointer. So the value is on the stack and right now it's initialized to 10. And we also have an int pointer, which is a pointer to an integer, and right now it's null. And I'll just leave it blank. Let's say that value is at address 1000 and int pointer is at address 2000, just to keep things straight. Okay, so that's where we're at. Now we're here at line 16, output value. Well, what's value? Well, we just go to the variable and grab its contents, right? So we're going to display a 10 here, just like we have before. Now we call the function double data and we pass in the address of value. Okay, so main stops what it's doing and we transfer control over to this function up here. So we're going to call double data and we're going to pass in the address of value. You can see right here, what's the address of value? It's 1000. So we're going to pass in 1000 to this function. Okay, that 1000 will get copied into int pointer. So that function right here has a local variable called int pointer. And you can see that guy right there. Notice it's the same name as this variable. That's okay. We can use the same name for different variables. These are two different variables in two different scopes. Okay, so we're passing in 1000 to it. So that's what we're doing. There's our pointer. So now that int pointer is pointing to this value right here at address 1000. Right. So what do we do now? Well, we're going to double that value basically. So let me write this out longhand here. So we'll dereference int pointer on the left-hand side equals, again, dereference int pointer times 2. And that's what this compound assignment is doing. Notice that that asterisk right there is multiplication. These asterisks here, that's the dereference operator. Keep them straight. It doesn't matter that they're asterisks. Look at the context and it should be pretty clear. All right, so let's execute this. Dereference int pointer followed the pointer to where it's pointing. Right here, I got a 10. Multiply that by 2, gives me the 20, and we're assigning 20 into wherever int pointer is pointing. Well, int pointer is pointing to 1000. So we just changed that 10 to a 20. Okay. At this point, that function is done. So we're going to clean up the stack. This activation gets popped off the stack. So this is all gone now. There you go. Now we're back to main and we output the value. The value is now 20. And we're done with that function call. Okay, so now let's keep going. We're here now. We're going to output a bunch of lines, and then we're setting int pointer to the address of value. Well, int pointer was null before. Remember, we nulled it out right here. So at this point, int pointer now is the address of value. What's the address of value? It's 1000. So it's 1000. There's my pointer. I'm pointing to value. So what do I do now? I call double data again. So let's call double data. And what are we passing into it this time? Int pointer. Well, what's the value of int pointer? 1000. So we're calling this with 1000, which is the address of some integer. So we activate that on that activation record. And it's got that same local variable, right? Int pointer. That's this guy right up here. And we're copying 1000 in. There's the pointer, same as we had before. So what do we do now? We execute this code. It now changes this 20 to a 40. Okay, when the function is done, we clean up our stack. We pop that activation record off the stack. So this pointer is gone. And then we come right back to main and we say output the value. Well, the value is now 40. Okay, so there you go. This is how pass by reference with pointers works. It's really pretty straightforward. Let's execute this code now, and you'll see the result is, and I'll slide this over just a little bit. You can see value here was 10, then we doubled it to 20, then we called it again and doubled it again to 40. All right, perfect. So let's take a look at another example now. Okay, so here's another example. I'm in the same workspace, section 12. Now I'm in the passing pointers to project. And what I've done here is I've written a swap function that basically swaps two variables, two integer variables in this case. And here's my main that exercises it. So let's try this out. Here's my main, as usual. Here's the stack. Main has two local variables. It's got x and it's got y. X is initialized to 100 and y is initialized to 200. Let's assume that these are at addresses 1000 and 2000. So we've got some nice easy numbers to work with. Okay, so right here, we're outputting. What's X? We're putting a new line in front of X, but that's okay. What's X? Well, X is 100. So we're going to display 100 here. And now we're going to say, well, what's Y? We're going to output the value of Y, which is 200. Pretty easy. Now main stops what it's doing and we transfer control over to swap. Okay, so we're going to call swap. And you'll notice swap has 3 local variables. It's got an A, it's got a B, and it's got a temp. So we need to allocate storage for all of those on the activation record on the stack, right? So we've got A, we've got B, and we've got temp. In this case, A and B are both pointers to integers, and temp is just a regular integer. Okay, so we're going to call swap with the address of X and the address of Y. The address of X is 1000, and the address of Y is 2000. So that's what the call looks like, right? Now this X right here, right, gets mapped to that parameter A. So that's what we're doing. We're copying that value to A. So A is now going to be what X is right here, right? So A is going to get 1000 and B will get 2000. So here are your pointers. B is pointing right here and A is pointing right there. All right, so now let's start executing this code. Temp, we're assigning what A points to temp. Well, what does A point to? We know it points to an integer, right? Because this is an integer pointer. So we're going to take the integer that A points to. Let's follow A. It points to 100, and we're storing it in temp. Temp is an integer, not a pointer. Okay, so that's done. Now we're going to execute the second one, which says take what B is pointing to. All right, let's follow B. B is pointing to 200. And put it into where A was pointing. Okay, A was pointing here. So we're going to put the 200 here. So that's done. And then we'll take the temp, which was 100 right here, and we're going to put it into where B was pointing. So B was pointing to here. So we're going to put the 100 here. Notice those 2 integers got swapped now. Okay, so at this point, the function's done. What do? We clean up the stack. We pop off that activation record. All this is now gone. And we just clean these up as well. And that's where we're at right now. So we're back in main now. What's X? We print out the value of X is 200. And we display the value of Y right here, which is 100. Notice that we actually swap those variables. Okay, so that's really what's going on with pass by reference with pointers in this example. It's pretty straightforward. If you remember, we did this with references. References is probably what you'd want to do here, but I'll talk about using references versus pointers in the very last video in this section. That gives you some insight as to what to use when. But there you go. This is how you do it with pointers. Let's look at another example now. Okay, so I've switched over to the Passing Pointers 3 project in the Section 12 workspace. In this case, we're going to pass a pointer to a vector rather than using integers as we've done in the past. And there's a couple of examples in this main, and I'll leave this second example here that's commented out for after I do this one. So this is what I've got. I've got a real simple function here called display, and it expects a pointer to a vector of strings. So it expects the address of some vector that holds strings. Okay, and all it's doing is just looping through the vector and printing out all the strings in it. I'm not going to draw the stack out now. I think this is going to be pretty easy to follow now that I've gone over all those examples. So in this case, I've got a vector of string objects. It's called Stooges, and here's the 3 Stooges, Larry, Moe, and Curly. Okay. So what have I got? I've basically got a vector object, and it's got 3 strings, Larry, Moe, and Curly. It's called Stooges, and it exists at location 1000 on the stack there. Okay, in main's activation record. Then I'm just calling Stooges here. I'm calling display, and I'm passing in the address of Stooges. Perfect. So now, once I'm here in this display function that you see here on line 7, once I'm here, all I want to do is display all those strings that are in the vector. So I'm going to use a range-based for loop that just iterates through the vector and prints out the strings. Well, I have a pointer. Here's my V, right? And V has 1,000 in it. So this is V right here. It's pointing. V is not the vector again. V is just a simple pointer. So in order to get to what the pointer is pointing to, I dereference the pointer. That's what I need to do. So if I dereference V, I've got this Stooges vector right here. Right? And that's what's going on right there. Okay? So for auto, which is a string, right? So for every string in the collection, well, the collection is not V. V is the pointer to the collection. So if I dereference V, I get the collection. And this executes just like you would expect. Okay? Now, let me clear this out and I'll run it real quick so that we can test this. And there you see Larry, Moe, and Curly being displayed by this function right here. Now, in this case, we really don't want this display function to modify stuff, right? I mean, it's only displaying vector elements. We don't want it modifying anything. So we could get this to modify something. That's not what we want to do, but we certainly could. Do you remember that we could do the at method of the vector class? Well, we could simply do star v, right? Dereference this pointer. That gets me the vector. Then I could say dot at 0 equals funny. And what that will do is it'll change the first vector element, Larry, to funny. Okay. Notice the syntax. The syntax may be a little strange, but think about this. This is very logical, right? If I dereference the pointer, I get the vector. And then once I have the vector, I can do dot at, dot size, whatever else I need on it. So this sets that to funny. I could also come over here and do something like V, which is the pointer, right? Is null pointer. So now I'm not pointing anywhere. So if I do both of these, you can see that this will compile just fine and run. Now, if I move this to the top, right there, now I'm actually going to change that vector element. So when I run it, you'll see funny now instead of Larry. You see that right there? So this is not something you want to happen, right? It's a display function. It shouldn't be messing around with the vector that you're pointing to. So in this case, we could use the const qualifier here, right? That will prevent this from happening right there. So if I do this now, I'll get a compiler error right there. You can see the red arrow is saying, hey, you're telling me that that vector I'm pointing to is constant. You can't mess with it. You just tried to mess with it. So that won't be allowed. And if I put a const here, then this line 13 won't be allowed. I'll try to compile that. And there's the error. Because now you're telling me that the pointer is constant, but you just tried to change it here. Okay, so again, that's not what you want to do here. All right, so now it's a lot safer, this function. We can't change the vector and we can't change the pointer either. So let's look at one last quick example, and I'll clear this out. And what we've got now is, let me close this up. We've got another function called display because we're using a function overloading here. Remember, we can use the same name for two different functions. And let me comment this piece out and I'll uncomment this piece right here. Okay, so in this case, I have an array of scores, right? Which is an array of integers, and I've set them all to these scores, and I've got a -1 at the end. In this case, the -1 is a sentinel. This is where I want to stop processing. So what I'm doing in this display function here is I'm passing in the address of that first integer and the sentinel. Where do I want to stop? And you can see what this is doing. It's saying while what I'm pointing to right there is not equal to the sentinel, which in this case is -1, then process what I'm doing, right? So I'm going to basically dereference that array, display 100, and then increment the array, the pointer to the next element. So think about what's going on here. Here's the array, and let's just put a few numbers in here. 100, 98, 97, 79, 85, and -1. I might have missed one, but that's okay. So at this point, that's my scores array. This is scores. This is, let's say, address 1000, right? Perfect. So now I'm passing in scores. So now my array variable in the function points right there. And my sentinel is -1. All right, so am I pointing to -1? No, I'm not. I'm pointing to 100. All right, print out 100 and increment the pointer. Well, where's the pointer pointing to? Well, now the pointer is going to point here, not here. So now we're going to loop again and print out a 98. And we're going to keep doing that until we hit -1. So this is going to print 98, 97, 79, 85, and then it's going to stop. In this case, we could pass in constant for the array, right? We're pointing to these numbers. We don't want to change it, but we are actually updating the pointer here. So we can't have a constant pointer, right? We can have a pointer to constant integers, but not a constant pointers because we're actually changing the pointer. This is something in this example here that you can't do with references. You've really got to use pointers to do this kind of stuff. Okay, so that wraps up this video. There you see a couple of different examples of pass-by value with pointers. At this point, you might be thinking, do I use pointers? Do I use references? How do I do this? Stay tuned. In the last video in this section, I'll tell you exactly when you should use pointers and when you should use references. In this video, we'll learn how to return a pointer from a function. In C++, functions can return pointers, which is a super powerful feature. In order to do this, we need to provide the type of the pointer in the function definition and in the function prototype. All this means is that the function will return an address of whatever type we specified in the function declaration. Let's see an example. In this function, we're returning a pointer to an integer. In this case, it'll be the value of the parameter that points to the largest integer. It's okay to return a pointer to data that's being passed into a function since we know that data exists. So in this case, we compare the two integers that the two pointers are pointing to and return the pointer that points to the largest integer. Notice that we're not comparing the pointers themselves. We're comparing what they're pointing to by dereferencing them. Pretty straightforward, but how do you call this function? I'll show you in the next slide. Here we have a simple main that calls the largest int function that we just wrote. I have two integers a and b. B is the largest with 200. I call largest int and pass in the addresses of a and b. This is correct since it expects pointers to integers. The function returns a pointer which I assign to a variable named largest pointer, which is declared as a pointer to an integer. So now that variable largest pointer points to either a or to b, depending on which one was largest. In this case, it's b, so we dereference the pointer and it displays 200. Let's see an example where we allocate memory dynamically inside a function and return the address of that memory. Returning dynamically allocated memory from a function is a very common use case for returning a pointer from a function. In this example, we created a function called createArray, and it expects an unsigned integer that contains the size of the array to create and a default parameter called initValue, and that's the value we're going to initialize all the array elements to. The function returns a pointer to an integer. Now this represents the address of that first integer that we dynamically created. You can see the code is pretty standard. After we create the storage, we use a for loop and initialize all the array elements to initValue. Notice that I'm using pointer offset notation within the loop, but I could have used pointer subscript notation. Finally, we return new storage, which is the address of that first integer in the newly created array. So how do we use this function? I'll show you in the next slide. In this sample code, we call createArray and we pass in 120. That means I want 100 integers allocated dynamically on the heap, and I want to initialize all of them to 20. So this function allocates the space dynamically on the heap for those 100 integers, initializes them all to 20, and returns the address of that first integer, which I assign to my array. Now I can use my array however I like. But remember, since the storage is on the heap, you need to release it. So you have to remember to use delete with the square brackets on that pointer variable. Now let's see what not to do when returning pointers from a function. Here I have two functions. The first function is called don't do this, and the second function is called or this. They both return pointers to integers. The first function returns the address of size. This is a real problem. Size is a local variable to the function. This will compile just fine since the address of size is the address of an integer, and that's what the function returns. But what's the problem? Well, you can see it's a huge problem. We're returning the address of a local variable in the function. The variable's on the stack, and the function just terminated, so this variable is now past its lifetime. The next time the function is called, or any function is called, the stack area will be reused and the pointer will now be pointing into that new function's activation record. If you overwrite the data it's pointing to, you could trash the stack pointer, static links, all kinds of important information on the activation record. Hopefully the program crashes or you get a really strange error that you can fix, but if the program changes data that isn't currently being used, then the program may appear to work correctly for a while. These types of errors or bugs are very difficult to find. The second function has the same problem, except that it's assigned a pointer to size variable and returns it. In both cases, the address that's being returned is a stack variable or a function local variable. Very bad idea. Okay, that completes this video. You'll get a chance to work with functions that return pointers to dynamically allocated storage in the challenge exercise at the end of this section. But first, let's head over to the IDE and we'll go over some of these functions in live code. Okay, so I'm in the IDE. I'm in the section 12 workspace in the return pointer project. And I'd like to walk through this example when we created that create array function that dynamically allocates some storage on the heap. So let's walk through this example. Right here, we're in main, and you'll notice that main is activated when the program begins, and we've got three local variables in main. We've got myArray, which currently is just nulled out. We have size, which contains garbage right now, and we have init value, which is zeroed out at the moment. Okay, so what do? We ask the user, how many integers would you like to allocate? And we read that into size. Let's say that they want to allocate 10 integers. So we'll put a 10 in here. And then what value would you like them initialized to? How about we initialize them all to the 2? So now we've got those variables. And what we do now is we call create array and we pass in the size and the initial value. So we're here now. Here's the function create array. Notice create array has 1, 2, 3 local variables, right? It's got size. And let me call create array here. So I'm calling create array with the size, which is 10, and the initial value, which is 2. If I didn't supply an initial value, it would use 0. There's the default initializer here. But in this case, size is 10, initial value. And notice again, I'm using the same variable names. I'm doing that on purpose. Don't let that confuse you. 2. And then we've got new storage right here, which is a pointer to an integer. That's where we're going to allocate the memory from when we call new right here on the next line. And right now that's null. Okay, so now new storage equals new int size. How many integers do I want to allocate dynamically? However many integers were passed in this case 10. So 10 integers will be allocated dynamically on the heap, not on the stack. This is the stack. The heap is a different part of memory. It's way up here, let's say. And we're going to allocate 10 integers, 0 through 9, on the heap. Let's say that this is address 5000. That's the address of that very first integer right here. What's being returned and assigned to new storage is that first integer's address. So we're putting a 5000 in here. There's our pointer. Now this is real important. We've got a pointer on the stack that's pointing to storage on the heap. This is exactly what we want. We've got to be careful not to lose that pointer. If we lose that pointer, we've got a memory leak. Okay, great. So now we have that memory allocated and we want to initialize it. Remember, right now, all that is garbage data right in here. So what do? We just use a simple for loop. We're going from 0 less than size by 1. And we're initializing every element in this array to whatever was being passed in an initial value right here. In this case, we passed in a 2. So we're going to store 2 everywhere. And here I'm using pointer offset notation. I could have just said new storage sub I and used pointer array notation or pointer subscript notation. Either one is fine. So in this case, we're putting a 2 in all of these guys. All 10 of them will have 2s in them. And now this is the piece that's really important. We return new storage. Well, what's new storage? It's 5000. We return that value 5000, and notice in main, we're assigning it to my array. So we're putting a 5000 in here. So now this pointer is pointing to the same place. That's really important because this function is almost done. So when this function gets popped off the stack, we're going to lose this pointer right here. And we don't want to lose that pointer. So that's why we assign it to my array. So now we've got a copy of that pointer that we can use. Okay, good. So at this point, the function is now done. We start cleaning it up. So all this is gone now, right? So this pointer here is now gone. We lose all this and we're back to main. Now notice main has that pointer. So we didn't lose our memory out on the heap. That's really important to understand. Okay, so now let's display the data. So I'm calling this function right now display, and I'm passing in this case, my array. My array is 5,000. That's the value of that pointer, and the size, which was 10. Okay, so display now gets activated on the stack, and it's got one right here, variable, one local variable, another local variable, and it's got another variable right here, I. Okay, I'm not going to worry about I. You know all about I. It's just a looping variable. So it's going to have this variable, array, and it's going to have a size. Okay, so 5,000 gets copied to array. 10 gets copied to size. Notice that this is now pointing to that same place. Okay, but it's constant. We've got a constant pointer, and we're pointing to a constant array. So we can't mess with that array, either by accident or intentionally. And all we're doing is we're just looping through there and displaying out every element in the array. Notice that in this case, I'm using pointer subscript notation here, whereas over here I use pointer offset notation. Same exact thing. So this function now goes through there, displays all those 2s, 10 of them. When we're done, same as before, we basically start unwinding. So this is done after we do all the displaying. We're gone here. This is gone, and we're back to main. Now I've got this storage allocated on the heap. I'm done with it. I need to release it or free it up. And that's what's happening right here at line 34. Delete square brackets and the name of the pointer. You got to make sure that the value of that pointer is something that was newed. Okay, you just can't point to like a stack reference and then delete that. So in this case, this will now be freed up, and that memory will be ready to be used again. So let's clear this up and give it a run. So we'll build and run here. So let's say we want to allocate 10 integers, and we want to set all of them to 5. There you see, we're displaying all 10 integers. Each one is set to 5. Pretty easy. Let's run this again. And suppose we want to allocate 1,000 integers this time, and we want to set each one of them to, I don't know, 88. We run it, there we get 1,000 integers all set to 98. What's important to understand here is that it's all on the heap, which is pretty cool. Okay, so that finishes off this video. I hope this makes a lot of sense. If you have any questions, please let me know. Pointers are very powerful constructs in programming languages. However, there are some potential pitfalls that you should be aware of when using pointers. In this video, we'll go over some of those pitfalls. These include using uninitialized pointers, dangling or stray pointers, not checking if new allocated memory, and leaking memory. First, let's look at uninitialized pointers. We've seen these already, but let's talk about them one more time. Uninitialized pointers contain garbage, which means they could point anywhere. If we try to access or modify the data they're pointing to, we could run into some major problems. The pointer might be pointing to a very important area in memory, and we could wipe it out. Modern operating systems today are pretty good at protecting critical areas of system memory, but you could still trash an area important to your program that could cause your program to crash. Worst case scenario is that the program continues to work as expected for a long time since the memory accessed isn't used. Then an update to your program later on changes everything, and all of a sudden the program is crashing. You think it's because of the new change, but it's actually a bug that's been in the code for a long time. In the old days of computing, it wasn't uncommon to corrupt data on storage devices by using uninitialized pointers. Another potential problem with pointers is the dangling pointer, sometimes called wild or stray pointers. These are pointers that are pointing to memory that's no longer valid. If you try to use these pointers to access that data, you don't know what the results will be. The main reasons for dangling pointers are returning addresses of function local variables on the stack that are no longer valid since the function is terminated. Another common scenario is that you allocate storage dynamically and assign it to a pointer variable. Then you assign another pointer variable to point to that same storage. Now you have two pointers pointing to the same area on the heap. That's okay, and we do it all the time. The problem comes in when one of the pointers releases the memory, but the other pointer is still referencing to it and you use it. Again, unpredictable results can happen. Best case is your program crashes during development and you fix these errors. The next pointer pitfall is not checking to see if new failed. If new fails to allocate storage, an exception is thrown and your program terminates. We can use exception handling to get more fine-grained control over these exceptional situations. If you try to dereference a pointer which is pointing to null, your program would crash. This is good in testing, but not good in production. The last pointer pitfall we'll discuss is the memory leak. This is probably right up there with the uninitialized pointer as the most common type of pointer-related error. Memory leaks are easy to understand. When you allocate storage dynamically on the heap, this storage has no name. It's simply an area of memory that's returned to you and you store the value in the pointer. The only way to get to this memory is through the pointer. But what if you lose the pointer? Say you allocated the memory in a function and the pointer was declared in the function and the function terminates. Now you just lost your pointer. There's no way you can reference that allocated memory on the heap. This memory is still considered in use by C++, so this is called a memory leak. If you leak enough memory, you could run out of storage on the heap for future allocations. Memory leaks used to be much more problematic when memory was limited, but there's still an error and a sign of bad code. As you can see, the potential problems are well understood, and as you become more experienced with pointers, you become very aware of them, and you don't make these mistakes. Now that I've mentioned the pitfalls with using raw C++ pointers, C++ has smart pointers now that take care of many of these problems and are still very efficient. They're a more advanced topic, and it's something that you should learn as you become more proficient with C++. I'll revisit smart pointers in the context of object-oriented programming in the next section. Well, that wraps up C++ pointers. I hope I did a good job explaining them since they can be very intimidating. Please let me know if you have any questions. Practice with pointers, write simple programs, print out the values of the pointers so that you can understand how to work with them and with memory. Okay, now let's move on to references. In this video, we'll learn more about references. We've already seen how useful references can be when used as function parameters. We learned about that in the functions section of the course. Although a reference may sound similar to a pointer, they're actually very different. A reference is an alias for a variable, so whenever you use the reference, you're actually using the variable it refers to. References must always be initialized to a variable when you declare them, and they can never be null. Once you initialize a reference, you can't change it so that it's an alias for a different variable. As mentioned earlier, references are great to use as function parameters. When you first start out in C++, you might find it useful to think of a reference as a constant pointer that's automatically dereferenced when you use it. We've already seen using references as function parameters, so let's see some other uses. References are often used in range-based for loops to access collection elements inside each iteration. Here's an example of a range-based for loop that does not use references. In this case, we have a vector of C++ string objects named stooges, and it's initialized to Larry, Moe, and Curly. Then we use a range-based for loop to iterate through the vector. At each iteration, we assign funny to each vector element. Then we have another range-based for loop that displays the contents of the stooges vector. Notice the output. Nothing changed. We didn't change the vector at all, even though we assigned funny to each element in the loop. So what's going on? The problem is that the str variable name in the first loop is a copy for each of the vector elements as we loop through them. So we're setting the copy to funny, but we're never changing the actual elements in the vector. Now let's see how we can use references to actually change the vector elements. Here we have the same example, except that the str variable in the first loop is now a reference. In this case, a reference to each of the C++ string objects. Now str is an alias for those objects, and when we assign funny to str, we're actually changing the vector elements. You can see now that when we display the vector, the elements in the vector have all indeed changed to funny. Notice what happens if we add the const qualifier to the loop variable in the first loop. Now we're preventing any change to the data in the vector because the compiler marks it as read-only. So this code now gives us a compiler error. This is not what we want, since we really do want to modify the vector elements. But you can see that the compiler is doing exactly what you're asking it to do. It makes sense for us to use the const qualifier in the second loop, the loop that actually displays the vector elements. Also, by using a reference, we're not incurring the cost of copying each vector element in each loop iteration. So, in this case, it makes sense to use the const qualifier for the reference str in the loop when we're displaying the vector elements. So any attempt to change them would probably be a mistake, so we can have the compiler help us out by making the reference const. Now, any attempt to change the vector element results in a compiler error. Unless you have a specific reason to copy elements in range-based for loops, you should use reference variables to make your code more efficient. And if you aren't going to modify the collection elements, make the reference const. Rather than go over everything we already covered regarding using references as function parameters, please refer to the Section 11 videos and examples where I go over the use of reference parameters in functions in detail. We'll head over to the IDE now and see some of these examples in live code. Okay, so I'm in the IDE. I'm in the Section 12 workspace in the References project. And this is about as simple an example as I can come up with for references. So here, I've got an integer called num, and I'm initializing it to 100. And I've got a reference called ref that I'm initializing it to num. So ref is an alias to num. So if I display num, I'm going to get 100. If I display ref, I'm going to get 100. They're aliases, where in this case, the reference is an alias to the num. Okay, so notice no dereferencing, nothing. Just use it straight as is, and it's automatically going to be dereferenced. Behind the scenes, it's basically a pointer. That's how it's implemented behind the scenes, but all that's been abstracted away for you. So in this case, here I'm changing num to 200. So I'm going straight to the variable and changing it to 200. So when I display num, I'm going to get 200. And when I display the reference, it's an alias to the number. Again, I'm going to get 200. Here I'm changing num, but I'm changing it through the reference. So I'm setting it to 300. Again, they're aliases, so that's what you get. Hopefully that's pretty easy to understand, I think. Now let's do another example that's based on the example that I did on the slides. But before we do that, let's run this. So I'll build and run, and you can see 100, 100, 200, 200, 300, 300, just what we expected. Okay, so now let's do an example of using reference parameters inside range-based for loops, just like we did in the slides. So let me clear that. And I'll scroll up just a little bit and I'll uncomment out this code right here. Okay, this is the code that worked on the vector of strings. So here's where we're at. We've got a vector of string objects right here on line 29 called Stooges, and we're initializing it to Larry, Moe, and Curly. Okay. Then I've got a range-based for loop. Now remember, the auto lets the compiler figure out what the type of str is. In this case, the collection is Stooges, and it's a vector of strings, so str will be a string at each iteration. And then what we're doing is we're saying str is funny. So the idea is that, or what the programmer intended to do was to change Larry, Moe, and Curly to funny, funny, funny. Okay, but it doesn't work. The reason it doesn't work is because str is a copy. So each time in, we're making a copy of Larry, a copy of Moe, and a copy of Curly. So sure, we're changing the copy to funny, but we're not changing any of these actuals to funny. So what we can do is, and if you notice, we have a simple loop here that just displays them. And when we run this in a second, you'll see that this will display Larry, Moe, and Curly. Okay, so no changes at all, just like we saw in the slides. In this next example, what we're doing is we're using a reference here. You can see the ampersand. So at each iteration of the loop, str will be a reference to the actual. So now that str is going to be an alias for each one of these guys at each iteration of the loop. So when we say str is funny, now we're really replacing Larry, Moe, and Curly with funny, funny, funny. So when we come over here and display, we're going to see funny, funny, funny. Okay, so we'll run that in a second. But the other thing we wanted to say was, in this example here, I'm displaying those three string objects that are in the vector. But in this case, I'm making copies of them. There's no danger in changing them, right? Because I've got a copy of them. So if I do change them like I did here, I'm only changing the copy. But I'm making copies. So that's pretty inefficient. In this case, those string objects are, they're pretty efficient, but it could be some user-defined type where making a copy of it could be pretty expensive. You're allocating space and you're making a copy, let's say a couple hundred bytes, 1,000 bytes or something. So it could be a very, very expensive operation. In this case, we want to pass that in by reference like we're doing here. But the danger with that is that now we can change the elements, right? Which we don't want. So that's why we use the const. So this gives us the protection of making those elements read-only, but it also allows them not to be copied. In this case, we're just going to create aliases to them. So very efficient and pretty safe because we can't change them. Okay, so hopefully that makes sense. Let me run this real quick. And you could see the first time through, and I'll move this slightly over here, we've got Larry, Moe, and Curly. So we didn't change a thing. We expected funny, funny, funny. We got Larry, Moe, and Curly. Now when we're using a reference, we do indeed change the actuals. So now we see funny, funny, funny. Okay, so give that a try. Play around with these. Try to create a reference to a pointer and see if you can figure out how that works. All right, so that's pretty much it for references. Remember, I covered how to use reference parameters and how to pass references to functions in section 11. There's a whole section there on using reference parameters and when you use const and so forth. So I'll see you in the next video. Now that we know about references and how to use them, let's look at L values and R values. L values and R values are something you don't worry about too much when you're first learning C++, but as you learn more advanced features of the language, they become very important. It's important that the fundamentals make sense now, so that when we move on to topics like C++11's R value references and move semantics, they'll be much clearer. So in this video, we'll do a basic introduction to L values, R values, and L value references. So let's start with an L value. An L value is an object that occupies a location in memory and is addressable. So in these examples, X and name are L values. They have names and they're addressable. We know that they're addressable since we can use them on the left-hand side of an assignment statement. So what's not an L value? In these examples, 100 is not an L value because it's not addressable. It's a literal. In fact, the compiler generates a compiler error for the 100 equals X statement, saying that 100 is not an assignable L value. Similarly, in the assignment statement 1000 plus 20 equals X, 1000 plus 20 produces a temporary variable with the value 1020, but that variable is not addressable, so we can't use it as an L value. In the last assignment statement, Frank equals name. Well, Frank is not an L value since it's not addressable. So these examples are of non-L values. They're in fact called R values. Let's talk a bit about R values. We can define R values by exclusion. So anything that's not an L value is an R value. Usually R values on the right-hand side of an assignment expression. R values can also be temporary values that the C++ compiler creates. We saw some examples of R values in the previous slide. Let's see a few more here. In the first statement, 100 is an R value. In the second statement, X plus 200 will produce a temporary variable, and that variable is an R value since it's not addressable. The string literal Frank is also an R value, and max 2030 is an R value because it returns a result that's a temporary and not addressable. R values can be assigned to L values explicitly. So L values can appear both on the left and right sides of an assignment statement. In this example, we see the first assignment statement is using the R value 100 on the right-hand side of the assignment statement, and this will be assigned to the L value Y. In the second example, the temporary R value with the sum X plus Y will be assigned to the L value X. Now let's look at references from the perspective of L values and R values. The references we've used so far have all been L value references. That means that we're referring to L values. In the first reference declaration, we're declaring ref1 as a reference to X. Notice that X is an L value. This makes sense since we are an alias for X, and we can use ref1 on the left-hand side of an assignment statement since it refers to an L value. But what happens when we declare ref2 as a reference to 100? Well, 100 is an R value, so this isn't allowed and the compiler will generate an error. The same applies when we pass parameters by reference to functions. In this case, we define a function square that expects an integer by reference. We have an integer num initialized to 10, and then we call square and pass in num. This is fine because n is a reference to an L value and num is an L value. However, if we pass in the literal 5 to the function, we get a compiler error because 5 is not an L value, it's an R value. And we must reference L values. Don't worry if this is a bit confusing now. As you'll learn more about C++ semantics, it'll make more sense. But it's important going forward when we talk about move semantics. In this video, I'd like to go over the basics of using the CodeLight's IDE's debugger. All the IDEs have some sort of debugger built in, and they all work more or less the same. There are some differences between them, but they all have breakpoints, they all have watches, and they all let you see your local variables, which is really all we're interested in right now. So I'm in the Section 12 workspace, and I've got a project called Debugger that's got some source code that I want to debug. So what do? Well, the first thing you want to do is, rather than build, we're going to do debug. So we're going to press F5, but we're not going to do that quite yet. I want to set up this environment first because right now I'm on a single monitor system. And it's much nicer to work obviously with a dual monitor system so you can have your console in one area and the debugger in the other. But on a single monitor system, you need to make some room here. So what I'm going to do is I'm going to grab this and just move it over here so it fills up half the screen. Move it over here so it fills up half the screen. Okay. Then when I debug, I want the console window over here on the right, but I don't really want it to take up half the screen. I don't need it to take up half the screen. So I'm just going to move this guy over to about there. And that should allow me to see all the icons that we can use up top to control the debugger. Okay. Again, this is just a personal preference. You can do this whatever you like that works for you. The next thing we need to do is we need to set a breakpoint. You need to set a breakpoint for the debugger. Now I'm going to do that right in main. If you look right next to line 16 here, not in this little gray gutter area right here where the arrow is, but right to the left of that, you can click right in there and you see that little red stop sign comes up. That's a breakpoint. Okay. What's going to happen is the debugger is going to kick in and it's going to start executing your code. Then it's going to stop at that breakpoint. From there, you can go line by line. You can go into functions. You can look at watches. You can do all kinds of stuff, which is pretty cool. All right. So that's where we're at now. Now also notice up here in perspective, there's a debug layout. This is the layout that will automatically kick in when you start the debugger. So it may look different on your end than on what you're going to see on my end, but it's totally customizable. You do whatever you like, close windows, open windows, and when you're done, just go to perspective, save current layout as debug layout again. So next time you run, it'll be in that perspective. All right, so let's debug. We're going to come up to the debugger and start continue debugger, or you can press F5. Make sure you've got a breakpoint set before you do this, otherwise you're not going to see much. So we're going to go to the debugger and start it, build and debug. Now you'll see the console. Now what I'm going to do with the console is just move it over to the right so it fills up the rest of that space. There you go. So all the output I'm going to see over here on the right. Okay. You'll notice down here that I've got an output view and I've got a debugger view. I really don't care about this output view. I just want to look at my debugger view. So you can close this side if you like. You can just click that X right there. And now I've got only the debugger view. Okay. Now in the debugger view, there's a lot of stuff in here. All we're really interested in at this level right now are your local variables and any watches you might want. And I'll talk about watches in a second. Cool. Okay, so you can see here are my local variables, I, X, and Y. If you look at main, you'll see I, you'll see X, and you'll see Y, X and Y right here on line 22. You'll also see that little breakpoint right there, the red. There's a little green arrow in there. I'm not sure if you'll be able to see it on the video, but you will be able to see it in a minute when I start walking through the code. Basically, that's the line that's about to execute. Okay. You'll notice right now, I, X, and J have garbage in them. That's because line 16 hasn't executed yet. Okay, so the debug icons up here, you can see them. You can show the current line. You can step in, which is what we're going to use to go into a function, or you can just go to the next line. Don't worry about step out. These are the two main ones we're going to use. Step in, next, and if you want to stop your debugging session, you can press that little stop button right here. Okay, so let's do this. And again, how you may want to close your workspace view here if you don't have enough space on your monitor. But I've got plenty of space here. So let's start. Let's click on this button right here, next, and there's your debugger. You can also click next here. You can press F10, whatever it is on a Mac, I'm not sure, but you can toggle breakpoints. You've got a lot of different options here, but I'm just going to use these icons for now because it's easier to see what I'm doing. All right, so we're here on line 16. Let's press that button right here, next. Now, when I do that, you'll notice that little green arrow will go to the next line. That means that this line executes, and we should see I down here change to 5. Okay, so I'm going to do that. See, the green arrow is now on line 17. That's the instruction that will execute next. And also notice that I is now 5. Okay. Sometimes you have to refresh this view down here, especially when you're working with pointers. If you need to do that, you just click that little button right here, and it refreshes that view. Okay, so now we're in this code while I is greater than or equal to 0. We know I is 5, right? Sometimes it's pretty handy. You can just kind of select I right there and press Control. And you can see I is 5. It pops up in this little tooltip right here. Okay. Right now, if I look at X, X is garbage because I haven't gotten to that line yet. So that can be pretty handy sometimes. But most of that information you'll be able to see here. Okay, so that's my locals. Suppose I want to do a watch. I want to watch I greater than 0. So I can come over here and I can select the plus sign and type the entire expression I greater than 0 and press OK. You can see it's a Boolean, and right now it's true because 5 is greater than 0. So you could switch between these two. You can obviously pull this pane out and have it in a dual monitor system. But right now, let's just keep going. So now I is 5. And we'll keep clicking on the next. You can see I'm in the body of the loop now. Now we have an output statement, so we should see 5 display out here on the console. And there you can see the 5 just display. Now we're going to decrement I, so I should go down to 4 down here in my local variables view. And there it is, 4. And I'm just going to keep looping through here. All I'm doing is pressing next. You can see my code executing. It's very similar to what I was doing with my pencil and marker on the screen, but here you can see it actually happening live. So at this point now, I becomes 0, the loop will fail, and I'm out of it. Okay. Now I'm executing line 22. When I click next, those two variables, X and Y, will be initialized right down here. So I'll click next, and you can see that they're 100 and 200, exactly what I expected. Now I'll execute lines 23 and 24, so we should display X and Y to the console. There's X, there's Y. Okay, so far so good. Now I'm calling the swap function that we wrote in this section, and I'm passing in the address of X and the address of Y. If you just click next here, it'll just skip that and go right next to the next line. It'll call the function, but I want to go into that function. So you want to click this one right here called step in. So when I select that, now I go into the function. So I'm starting to execute that function. You can see the green arrow right here on line 9. Okay. And you can see A and B. Well, A and B are pointers, and they've already been set. You can see them right here. There's A, there's B. Those are the two addresses. And you can see their type, integer pointers. Temp is just a regular int. So if I expand A, it tells me what A is pointing to, which is 100. Expand B, B is pointing to 200. Okay, so now let's walk through the swap. The first line says, take what A is pointing to. Well, you know what A is pointing to right here, 100. And assign it to temp. So right now, temp has garbage. So let's do that. We'll click next. And now you see temp has 100 in it. Then we're taking what B is pointing to, which is 200, and putting it into where A was pointing. So now I'll go next. You see right here, you see how it didn't refresh? It doesn't do that with pointers sometimes. That's when you have to click this little refresh dial right there and then just re-expand them. And you can see that it did do that now. We'll do the next and refresh one more time. And you can see that they've been swapped, which is pretty cool. At this point, I click next. This function is done. Notice that my local variables now are A, B, and temp. That's because I'm in this function right here. Those are the local variables. Okay. My watch doesn't apply anymore, right? It's in the main. So here, I'll click next again. Now I'm back in main. I'm right here on line 28. And I'm going to display X and Y again. There's X200. There's Y100, and our program is done. Okay, so there's a lot of options that you can do. You can learn to play with the debugger. There's really, debuggers are awesome. The best advice I could give you with a debugger is that they're called debuggers for a purpose because they really help you debug your code. I wouldn't suggest that you start using a debugger as so much of a learning aid at this moment. I think it's better just to do it with paper and pencil at the beginning because the debugger itself has a bit of a learning curve. So you're learning C++ and you're learning the IDE, and now you're learning a debugger all at the same time. But in the context of what I just did here, it's very, very useful. Suppose you have a bug in your code, and the bug was that, it was greater than or equal to 0, or you had a less than there, and maybe you didn't see it when you're looking at your code. Well, when you run it through the debugger, bam, you'll see the error. You can fix it right away. Okay, so feel free to use the debugger. Feel free to use the debugger in the challenge exercise for this section. It might come in handy. Okay, so now that we know about pointers and references, let's talk about when we want to use pointers versus reference as function parameters. First, let's look at pass by value. Remember that pass by value is what C++ does by default. So you want to use pass by value parameters when the function does not modify the actual parameter and the parameters are small and efficient to copy. This is true of the primitive types like integers, doubles, characters, booleans, and others. Note that the collection types like strings and vectors and others have a certain amount of overhead involved when they're copied, so you want to think twice before you pass those by value. In the case of pass by reference with a regular pointer, in this case, we do want to modify the actual parameter from within the function, and the parameter is expensive to copy. And then the last criteria is that it's okay for the pointer to contain a null value. This is important because a lot of data structures rely on pointers becoming null at the end of lists or at the end of trees. So in those cases, you really want to pass pointers and not references because references can't be null. Let's take a look at pass by reference using a pointer to const. In this case, this is suitable when the function does not modify the actual parameter, but the actual parameter is expensive to copy. Also, remember that pointers can contain null values, and this is very useful in data structures. In this case, the pointer is allowed to contain a null value. In the case of pass by reference using a const pointer to const, in this case, it's very useful when the function does not modify the actual parameter and the parameter is expensive to copy. It's okay to have a null pointer, and also the function never modifies the pointer itself. So this is a good example of where you would pass something in and you're guaranteed that the pointer is not moving and the data it's pointing to is not going to change. Okay, so now let's look at references. In the case of pass by reference using a regular reference parameter, this is used when the function does modify the actual parameter and the parameter is expensive to copy. Of course, you can never have null values in the reference. So if you're working with data structures that rely on null values, you really should be using pointers and not references. And in the case of pass by reference using a constant reference, this is useful when the function doesn't modify the actual parameter, but the parameter is expensive to copy. And again, you can't have null references. So if you need null values, go with the pointers. Okay, there you go. Those are a few guidelines. These are just guidelines that can be used to make your program better and easier to modify and debug. That's the end of this section. This section can be difficult for many beginning programmers, but it's important that you go through the examples slowly and then make up your own examples. Pointers and references are two concepts that make C++ very different from other languages like Java, Python, Ruby, JavaScript, and so many more. Remember at the beginning, I talked about C++ programmers being in control of memory and hardware. Now you know how it works and have the foundation to move to OO programming in C++. That's coming up in the next section. But first, have a go at the section challenge, which will give you a little bit more practice with pointers. Welcome to the section challenge. This has been a long section and there was a lot to learn. Pointers can be tricky and intimidating, but here's a real nice challenge that'll help you understand pointers in dynamic memory allocation. So I've given you a bit of a start. I've written part of the main for you, and you just have to write two functions. You have to write a print function that should be pretty easy, and then you have to write an apply all function that I'll talk about in a second, and we'll walk right through this real quick. Okay, so let's go back up to the top of the challenge here. And what I'd like you to do is write those two functions. But the first one, let's talk about the first one. Write a C++ function named apply all. Now this function expects two arrays of integers and their sizes, and it dynamically allocates a new array of integers whose size is the size of one times the size of the other. And then what you want to do is you want to loop through the second array and multiply each element across each element of the other array. Sounds complicated. It's not. Let me walk you through exactly what I'm talking about. So here's the function. So it expects two arrays, array 1 and array 2. And it expects the sizes for those two arrays. So you can see right here, array 1, array 2, 5, and 3. Okay. So let's say that this is array 1. It's 1, 2, 3, 4, and 5. This is array 1. And then we've got array 2, which contains 10, 20, and 30. Okay, so we're passing these two pointers, basically, right, array names, into that function. And we're passing along 5, which is how many elements are in this array, and 3, which is how many elements are in this array. Now that function is going to dynamically allocate an array that's 15 big. 5 times 3, and those numbers could vary. So in this case, what we want to do is we want to take each element in array 2 and multiply it across all the elements of array 1. So 10 times 1 is 10. 10 times 2 is 20. 10 times 3 is 30. We got the 40, and we have a 50. Okay, then what we want to do is we want to go through here and now go to the next array element in array 2. So that's 20. So 20 times 1 is 20. 20 times 2 is 40. 20 times 3 is 60. 20 times 4 is 80. And finally, 20 times 5 is 100. Okay, then the last thing is go through that last number. So now we're at the 30. And we're going to go 30 times 1, which is 30. You get it. You get the idea. 60, 90, 120, 150. So this here is the newly created array that you're going to create dynamically on the heap. We want to return the address of this array, which is the address of this guy right here, from the function. That function returns the address, which we store right here in that pointer variable results. Then we pass results to the print function with a 15, and this is what we get from this example. Let me clear the screen real quick. So here's array 1. I call the print function, I pass array 1 into it, and it's going to display that. Then I output array 2, and then I call the print function, I pass in array 2 with a 3. I get that. I call this function, it dynamically creates that array, it does the multiplication, it stores all the values into the dynamically allocated array, and it returns the address of that array, and we store it in results. Then we pass results and 15, and that's what we get. Okay, so what you need to do, again, one more time, you need to write the apply all function and the print function. Now the apply all function expects array 1 and its size, array 2 and its size, and you could decide what the types are going to be. The print function expects an array and a size. Now obviously this guy returns a pointer to an integer. This guy doesn't return anything. So that's roughly your function prototypes here. You just have to decide what these types here are going to be. Okay, that's it. Test your code and have fun. If you need to use the debugger, go for it. Meet me on the other side of the challenge and I'll show you my solution. Welcome to the Section 12 Challenge Solution. I'm in the Section 12 workspace in the Challenge Solution project. And before I forget, we're going to write those two functions, but right here on line 108, don't forget to free up the storage. Okay? I was going to get into the functions, and I knew I was probably going to forget to mention this, but remember, that function that we're going to write, this function apply all, allocate storage from the heap. When we're finished with it, we need to release it. So we want to say delete square brackets results. All right, perfect. Now let's go write those functions. First thing we'll do is we'll write the print function. The print function is really easy to understand, and here it is right here. Okay, so what does print expect? And here you can see a call to print. Let me scroll up just a little bit so you can see it right there. Here you can see a call to print right here on line 97. You can see what's happening. I'm calling print, and I'm passing in an array, right? Which is the address of an integer in this case. That just happens to be the first integer in this array right here. And I'm passing in array1 size, which is a constant defined to 5. Now this function expects a constant pointer pointing to a constant. So I can't change the pointer, and I can't change what it's pointing to in this case. So any mistakes I make in here, I want caught, because I have no plans of changing anything here. I'm not modifying the pointer or what it points to. And I'm passing in the size. So what am I doing here? I'm just simply displaying that square bracket, and then I'm just using a real simple for loop. There's my I, that's my loop variable. I'm starting at 0, and I'm going again less than size. Size in this case is 5, so I'm going 0, 1, 2, 3, 4, and I stop, and that's exactly how that array is indexed. At each iteration, I'm just displaying ARR sub I. Now right here, I'm using pointer subscript notation. I could very easily have used pointer offset notation, right? Which becomes ARR plus I and dereference that guy. Exactly the same. They both mean exactly the same. So in either one you could use. Okay, so at this point, I'm looping through there. When I hit 5, I stop, and I've displayed all those values here. So this will display 1, 2, 3, 4, 5, and a square bracket, and then a new line at the end. And that'll be the output you see from here. Okay, so hopefully you got this function. It's a pretty simple function to write. Most likely, if you had any issues with this, it was probably right in here. Maybe you did an I less than or equal to size, and you had an off by 1 error, and maybe you printed some garbage. That's a very common error. If you use the debugger, that probably helped you out. Okay, so let me clear that. Now let's go and write the main function here, the apply all function. Now in this case, this is how I've defined this function. We know it returns a pointer to an integer, right? Because it needs to return the address of that newly allocated space on the heap. It expects array1, which is a pointer to an integer, and the size of that array, and array2, which is a pointer to the other array, and the size of that array. So that's what we're passing into this function. I've declared everything is const, all these pointers. That way I'm not messing with pointers, and I'm not messing with what they're pointing to. I've got no business changing those two arrays that are coming in. I'm just building a third array, which I'm returning. So here is the third array. It's called new array. Right now it's just a null pointer, and it's a pointer to an integer, right? An address of that first integer in that new array that I want to create. And this is me creating it right here. New int, and this is going to be 15 in this example because I'm passing in a 5 and a 3 right here. So I'm allocating 15 integers on the heap. Right now, that's been allocated. That all contains garbage right now. And they're indexed from 0 to 14. Okay? Now, I want to loop through those arrays that were passed into me so that I can start doing some of these calculations. So let's do that right now. First of all, I've got this variable called position. And position starts at 0, and it's going to go from 0 to 14. That's what I'm going to use to index into my new array here. But I've got those other two arrays. I've got ARR1, which was 1, 2, 3, 4, and 5 in this example. And I've got ARR2, which was 10, 20, and 30. Okay, so this is where we're at. And obviously we have the sizes that were passed in, the 5 and the 3 as well. So what do I want to do? Well, I want to loop through this array as the outer loop because I want this to loop slow. This is the one I want to loop fast because I want to stay at 10 and then go 1, 2, 3, 4, 5. Then I want to go to the 20 and go 1, 2, 3, 4, 5 and so forth, right? So my I looping variable is going to go from 0 to size 2, which is 0, 1, and 2, because that size 2 is 3. And I want to increment I by 1. And then I've got an inner loop, so I've got a nested loop here, where my looping variable is j, and it's going to go less than size 1. So we're dealing with 5 here. And I'm incrementing that by 1 at each time. So look what's happening in the body of the inner loop. Okay. I'm setting the value, and again, I'm using, right here, I'm using pointer subscript notation. I'm setting the value at new array position, right? Position right now is 0. We set it right up here. So I'm setting the value at new array position to be ARR sub j, right? At the beginning, this will be 0 times ARR sub I, which is also 0. So that's these two guys, right? 10 and 1. So when we first go through here, the second ARR2 is the one that's looping slower, right? So this guy's going to go 1, 2, 3, 4, 5. And this guy's going to go 10, 10, 10, 10, 10. He's not changing, right? So what we're doing is we're multiplying 10 times 1 and putting it here, right? Then we're incrementing position. So now position is 1. And then we're multiplying 10 times 2. We got our 20. And we're going all the way down to 50. And along the way, we're incrementing that position variable. This is the position variable right here. Okay. Now we're done with the inner loop. So we go back out to the outer loop. And now instead of a 10 here, we're going to grab the 20, right? So this guy now refers to 20. So we're going to do the same thing. We're going to go 1, 2, 3, 4, 5. And then 20, 20, 20, 20, and 20. And we're multiplying all of these, storing the product right in here. So we're going to get 20, 40, 60, 80, 100. And along the way, 5, 6, 7, 8, and 9, we're incrementing that position variable. Okay. Then obviously on the last iteration of the loop, we're dealing with 1, 2, 3, 4, and 5. And we're multiplying all of these guys by that 30 right here. So what we're doing here, and of course, this position is being bumped up each time. So that's what's pointing into the new array, right? So now here we've got what, 3, so we got 30, 60, 90, 120, and I ran out of space, but there's a 150 there at the end. At that point, that array now has been allocated on the heap, and all those values have been stored into the array. I'm going to clear this now. And then all I'm doing here is returning new array. So it's returning the address of that first element in the array. Okay, now I'm back here now in my main, and I just returned that address right here. So this pointer results is pointing to that array that I just erased, that big array of 15 integers from 0 to 14 on the heap. It's got no name, and the only way I get to it is through this results pointer. Okay, simple as that. Then I'm using a constant expression here to basically calculate this constant result size, which in this case is going to be 15. And I'm just passing results and 15 to the print function, and it's going to print all those values that we calculated. So let's give this guy a run. And there's the run. You could see array 1 is 1, 2, 3, 4, 5. Array 2 is 10, 20, 30. And then the resulting array is 15 elements big, and it's a function of applying that multiplication of one array to another array and putting the product in the third array. Okay, simple as that. The debugger might have helped you if you used it. If not, it's just really a matter of, the only tricky part here is this piece of code right here, the nested loop. And this is just one way to do this. You could have done this a lot of other different ways, but this is a really simple way to do it, because you keep that position, you just keep bumping it up, and it's going to go from 0 to 14, and it's as simple as that. All right, so I hope you guys were able to solve the challenge. If you did it a different way and you think it's more efficient or pretty clever, let us all know. That'd be awesome to learn. In this section, we'll get a first look at object-oriented, or OO programming. We've already done a bit of OO programming when we used the standard string and vector classes, but now we'll learn much more about OO programming, and especially how to create our own classes and objects. Before learning about C++'s object-oriented features, we'll learn what OO programming is and why it's so popular and useful. Then we'll learn exactly what classes and objects are and how they work in the world of OO. We'll see how to declare some simple classes and create objects from those classes. We'll then see how we can use the dot operator and the pointer operators so that we can get to the parts of an object that we want to access. Two of the main strengths of object orientation are encapsulation and information hiding. We'll define these concepts in this section and see how C++'s public and private access modifiers allow us to prevent access to parts of our code while still allowing access to the interface that will be used by other programmers. Then we'll turn our attention to the many ways that we can construct or initialize our objects. This is all done with constructors. These are methods that we write that give us control over exactly how our objects are created. There are lots of variations in constructors, and we'll look at the most common and understand their primary purpose. We'll learn about initializer lists, default, overloaded, copy, and move constructors, and we'll see when and how to implement them. Sometimes when we work with pointers inside classes, we have to be aware of whether the pointer or what the pointer is pointing to is being copied. This concept is called shallow versus deep copying. By default, C++ provides shallow copying, but sometimes we need to do more than that, and we'll learn how and why. We'll also discuss destructors. Sometimes when an object is destroyed, there can be things that we have to do to tidy up after them. This might include closing files, freeing allocated memory, writing log messages to files, and so forth. C++ provides destructors that are called automatically when objects are going to be destroyed. Then we'll learn about the this pointer, which many times confuses beginning C++ programmers, but don't worry, it's pretty simple once explained. Sometimes when we write OO programs, we want certain attributes to belong to the entire class and not to the objects themselves. That's exactly what the static class members allow you to do. Finally, we'll wrap up this section by understanding the difference between structs and classes and see how C++ classes can grant friendship privileges to other parts of the program so they can access private information in an easy but controlled manner. Once you complete this section, you'll have the basic fundamentals necessary to model your programs using real-world objects. This will not only help you think more abstractly, it'll also make your code more robust, easier to debug, and easier for others to modify. This sounds like a lot to learn, but we'll take it in small steps and build up our classes as we go. Let's get started with OO programming and C++. In this video, we'll talk a bit about what object-oriented programming is all about. But before we do that, let's review procedural programming and its limitations. Procedural programming is pretty much what we've been doing up to this point in the course. The focus of procedural programming is the function. We modularize our programs by creating many functions that each specify a process or action in the program. So procedural programs are basically a collection of functions. In procedural programming, we declare our data separate from the functions, and then wherever we need a function to process or use our data, we pass in the data to the function. If you recall our challenge from section 11, that's exactly what we did. There's absolutely nothing wrong with procedural programming, and in many cases you have to use it since not all languages support object-oriented features. Procedural programming is also fairly easy to learn since we're pretty good at breaking up a task into subtasks, which is exactly what procedural programming is all about. However, procedural programming has some limitations. One of the limitations with procedural programming is that the functions need to know about the structure of the data. This may not sound like a big deal, but suppose we have a program with hundreds of functions, and many of those functions expect a specific data structure as an argument. If the structure or format for that data structure being passed around changes, then this would affect many functions. These functions might even have to be modified to handle the new format of the data. This could have a ripple effect in the program, and the amount of effort needed to change and then test all of the updated functions could be substantial. I've worked on very large projects where the decision was made not to upgrade a data structure because the changes needed in the rest of the program would be too expensive in programmer and testing time. The real limitations to procedural programming really begin to show as programs become larger and more complex. As procedural programs get larger and larger, they become more difficult to understand since the number of connections in the program becomes very hard to trace by hand. This leads to problem maintaining the software, extending the program, and finding and fixing bugs. Also, reusing functions and data structures that we wrote for one program in another program becomes much more difficult, since after time we end up with code whose behavior isn't that easy to visualize. Finally, the code becomes more fragile and easier to break. That means that when we add new functionality or fix a bug, the chances of introducing another bug is high. This happens more often than you would think, and it happens more in large procedural programs than it happens in large object-oriented programs. Okay, so now let's talk about some of the principal features of object-oriented programming. So what is object-oriented programming all about? In this video, I'm focusing on object-oriented programming and its benefits. We can also have object-oriented analysis, object-oriented design, object-oriented testing, and so forth. Object-oriented is all about modeling your software in terms of classes and objects. There's some new jargon to learn along the way, but it's not so bad. Don't worry if it all doesn't click right away. We'll be using this new terminology a lot in the rest of the course. These classes and objects model real-world entities in your problem domain. So, if you're writing an application that allows users to store, edit, and manipulate images, like iPhoto on a Mac or Photos on a PC, then your classes might be album, photo, slideshow, location, and so forth. If you're modeling a student enrollment system, your classes might be student, course, professor. You get the idea. Why is this such a big deal, and how is it different from procedural programming? Well, first, let's talk about why it's such a big deal. It's all about abstraction. As our programs grow more and more complex, we need ways to deal with the complexity. Classes and objects are one way to do just that. Now, rather than thinking in terms of first name, last name, student ID, credit hours, and so forth, we can think in terms of student. And all that detail comes along with it. Not only that, but operations like register, drop course, add course, and so forth also come along with it. So if Frank is an object and it was created from the student class, I can send a message to Frank and ask Frank if he's registered this term. This is very different from procedural programming, where I would have a function that would tell me if the student is registered, and then I would have to pass a student to that function. You might ask, so what? It still works in procedural programming. And you'd be correct. But now the function needs to know how to determine if the student is currently registered. If this business logic changes, then we need to figure out everywhere in the program that knows this so we can update the code. In the object-oriented solution, only the student class knows this, so a precise change is all that's necessary. The fact that objects contain data and operations that work on that data is called encapsulation, and it's an extension of the abstract data type in computer science. Now the data and the operations are together in the class where they belong and not spread across many functions, each passing and receiving data. Encapsulation is another mechanism used by object-oriented programming to help us deal with complexity. We can take the idea of encapsulation even further with information hiding. Object-oriented programming allows us to hide implementation-specific logic in a class so that it's available only within the class. This is a super powerful concept since it allows us to provide a public interface to the class and hide everything else. Now we know that the user of the class can't mess with the implementation-specific code since they never knew about it in the first place. That's pretty cool. This makes the code easier to maintain, debug, and extend. Object-oriented programming is also all about reusability. Reusability is defined in terms of using something from this program in another program. Since classes are pretty much encapsulated units of data and operations, reusing them in other applications is much easier. And since the class has already been tested, we get that benefit as well. This leads to faster development and better quality software. Finally, you've probably heard about inheritance. Inheritance allows us to create a new class based on an existing class by only adding or modifying the elements that we need to be able to create our new class. For example, suppose we have an account class that models a basic bank account. So it has a balance and the regular withdraw and deposit methods. Now suppose we have the need for a special trust account class, and our business logic says that this type of account is limited to 3 withdrawals per year, and each withdrawal can't exceed 10% of the current account balance. We could add this logic to the account class that we already have and have an enumeration or some other kind of discriminant that determines what type of account we have and then execute the appropriate if-else logic. Sure, that works, but what if we expect lots of variations to that account class, like a money market account, a CD account, and so forth? And each one of them has its own business logic, not only for withdrawal, but also for deposit. And some accounts change fees and others produce interest income. You get the idea. This could quickly make that simple account class that we started out with a beast that no programmer wants to deal with. In this case, we can derive our new class from the existing account class and add the appropriate behavior in the new class without modifying the original class at all. This leads to reusability as well as polymorphic classes, since all the derived classes we created are in fact still accounts. We'll learn more about the power of polymorphism later in this section. So OO sounds pretty amazing, right? Well, while OO can certainly help us develop large programs that are easier to maintain, test, debug, and reuse components from, it's not a panacea. OO won't make bad code better. It will likely make it worse. Also, OO is not suitable for every application, and not everything decomposes into a class. There are sometimes non-functional requirements that horizontally cross-cut a system, and these tend to add tangled code within existing classes. Remember, if you have a small program that won't be around for any significant amount of time, maybe it's an internal program that you're using to automate something, then object-oriented programming might be overkill. A simple procedural or scripting program may be perfectly appropriate. Generally, object-oriented programming has a steeper learning curve than procedural programming. C++ in particular is considered one of the most difficult programming languages to learn. Also, there are many object-oriented languages out there, and while they all support classes and objects and so forth, the way that they support them can be quite different, not only syntactically, but also in behavior. As mentioned in the beginning of this video, it usually takes more upfront design time in order to write an object-oriented program. In fact, large object-oriented programs sometimes go through significant upfront design. Finally, object-oriented programs tend to be larger in size than non-object-oriented programs, and can sometimes be slower and more complex since there's so much more going on behind the scenes. This can be especially true with object-oriented languages that use a virtual machine. However, the great news is that among object-oriented languages, C++ is probably the most efficient language out there. In this video, we'll learn a little bit more about classes and objects. You can think of classes as blueprints from which objects are created. Classes are user-defined types, and one of the goals in object-oriented programming is to make the user-defined types feel like they're part of the programming language. So when we create our classes, we want to be able to use them just like we use integers, doubles, and so forth. Easy and simple. Classes have attributes, which are data, and they also have functions, which are called methods. As mentioned in the previous videos, classes can hide data and methods that are only used internally by the class. This is done using the private and public access modifiers. The goal of a class is to provide a well-defined public interface that the user of the class can easily use to solve their problem. Here are some example classes: account, employee, image, standard vector, and standard string. These are all classes that model real-world entities. Vector and string are part of the C++ standard library. Account, employee, and image might be classes that we would create in our applications. Okay, so now that we know what a class is, what's an object? Well, objects are created from classes and represent a specific instance of the class they're created from. So if I have an account class, I can create a Frank's account object that's a specific instance of an account that models Frank's account information. We can have as many objects as we need. If we were modeling a real banking application, we could have hundreds of thousands of account objects, each representing an individual instance of an account. Each object has its own identity, and each can use the methods defined in the class. Let's see an example. We know that ints and doubles are primitive types in C++. They're not classes, but this analogy will help make a point. In the first two lines, we define two integers, high score and low score. What does that tell us? Well, it tells us what the valid values are for those variables, and it also tells us the operations we can perform on those variables. For example, addition, subtraction, multiplication, and so forth. Again, integers are not classes, but just for a moment, think of int as the class and low score and high score as objects created from the int class. Notice that low score and high score are instances of integer. They each have a value and they each have an identity. Now look at the next two lines. Let's assume that we've already written the account class and it's a true C++ class. Notice the syntax and how similar it is to the syntax for the integers above. Account is a user-defined type, so Frank account and Jim account are instances of the account class. They are objects. Each of these objects has an identity and values associated with them, just like high and low score did. This should look familiar since we've already been using objects all along. The last two lines create a scores object that's an instance of a vector of integers and a name object that's an instance of string. Okay, so now that we know a little bit more about classes and objects, let's see how we can declare a class in C++ in the next video. In this video, we'll learn about constructor initialization lists, which are very useful for efficiently initializing our objects' data members. So far, we've written our code so that we initialize our data member values in the constructor body by assigning values to them. While this works, it technically isn't initialization, because by the time the constructor body is executed, these member attributes have already been created. So we're really just assigning values to already created attributes. I'll show you exactly what's happening when we head over to the IDE in just a bit. What we really want to do is have the member data values initialized to our values before the constructor body executes. This is much more efficient since it's true initialization. C++ allows us to do this using constructor initialization lists, which is basically just a list of initializers immediately following the constructor parameter list. It sounds complicated, but it's not. Let me show you. Here we have the same player class that we've been using in previous examples. It has 3 overloaded constructors, and if you recall from the previous videos, we implemented them using assignment statements in the constructor body. You can see in the top section of this slide how we previously implemented the noargs constructor. In the body of the constructor, we use 3 assignment statements to set the attributes to the values we want. While this works, it can be inefficient in many cases. For example, by the time that we get to the statement name equals none, the name string object has already been constructed and initialized to an empty string. So we're really just assigning a new string to it. In this case, to an existing object. That's very different from initialization. What we really want is to initialize the data members to our data values as they're created. That's what constructor initialization lists allow us to do. The bottom section of the slide shows how we could implement the same constructor in a more efficient way. Notice that immediately after the parameter list, we provide a colon followed by a list of initializers. In this case, we're telling the C++ compiler to initialize name to none, health and XP to 0. This happens before the body of the constructor is ever executed. One thing to keep in mind, the order in which the members are initialized is not necessarily the order we provide in the initialization list. The data members will be initialized in the order that they were declared in the class declaration. So let's implement the rest of the constructors using initialization lists. Here we're implementing the single string constructor. Notice the previous way on the top section of the slide and the better way using an initialization list below. In this case, we provide name value to initialize name and still use 0 for health and 0 for XP. You can probably guess how the 3args constructor will look. Here's the 3args constructor at the bottom using the initializer list. We're providing name val, health val, and XP val to the initializers. And the complete refactoring looks something like this. Notice how in the constructor there's no code in the constructor body. We could still write any code we want in the constructor body, but now we can be sure that our data members have been initialized to our own values before any code in the constructor body is executed. Let's head over to the IDE and we'll step through a few examples so you can see how much more efficient constructor initialization lists can be. Okay, so I'm in the IDE, And I'm in the section 13 workspace in the constructor initialization lists project. And I've just got a simple main here that has our player class, as I've discussed previously, with 3 overloaded constructors, no args, a single string, and the one that supplies the string and the 2 integers. Okay. And I've implemented the constructors the way we've done previously using these assignment statements inside the body of the constructor. I've got some breakpoints in here that we'll walk through so that we can see exactly what's going on. And then I'm creating 3 objects. I'm creating empty using no arguments. I'm creating Frank, which is they're all player objects. Frank with the single string, and then villain is going to use this constructor here with the 3 arguments. Okay, so let's walk through this, and we'll be real careful to look at that name attribute, because that's really the important one, because it's an object. So let's walk through this. And right now we are on line 41, right about here. And I'm going to step through this, and that will call the no args constructor. That's this one right up here on line 21, since we're providing no information for initialization. So I'm going to step through it, and you can see now the arrow here, the little green arrow is on line 22. That's where I'm at. Now we can't really see empty here because empty's out of scope. We're now within the scope of this constructor right here. And I'll talk about a variable called this a little bit later in the course, probably a few videos from now. This represents the current object, okay? So if I expand this, you can see that this is this current object that I'm building right here. And you'll notice something interesting. You'll notice that name is set to the empty string. What does that tell you? Well, that tells you that that was already initialized. In other words, that string object name, its constructor was already called with no information, and we initialized it to an empty string. So this line right here that says name equals none, that's really not initializing anything. All it's doing is assigning none to an already created object name right here. That's really not what we'd like. We'd like to initialize that object name immediately without having to initialize and then assign to it. Okay, that can be very inefficient. In the case of a very complex class, you might have to create some sort of default constructor for it, and it's setting a lot of fields. It may be allocating things, and then you're just going to deallocate all that stuff and assign to it again. It really doesn't make sense. Things become very inefficient. So you can see in this case, I'll keep walking through this, and now we're going to set name to none, health to 0. You can see I'm right here on line 24, and XP to 0. Then I come back down to main. At this point, my player object, I'll refresh over here, my empty player object is set to none 0 0, just like we expected. But now let's create the Frank object. So what do? We're going to call the constructor that expects a single string, which is this one right here on line 27, and I'm going to go to that. Now I'm here on line 28. Again, notice this represents the object that I'm creating right now, and an empty string again. So I just created another object. In this case, I'll step through it really quickly. And now I'm back here to player villain, which is going to call this constructor right here, the 3 args constructor. And I'll do that. And again, here's this, another object that was created. So we've just created 3 string objects and then get rid of basically the string, the empty string they pointed to, and replaced it with Frank, villain, and none. So really, really an inefficient thing to do. And what I'll do is I'll make one little change that hopefully will really help you understand this. Right now we're just using that empty string, but suppose that I initialize this here to some string that's really obvious, like a bunch of X's. Okay, and let's run this again, and we'll walk through it one more time. And hopefully this time it'll really be obvious what's going on. Okay, so again, I'm here on line 41. And I'm creating an empty player object, so it's going to call the no args constructor, this one here. So when I step through it, you can see I'm now on line 22. But if you look at the object, take a look at name right there. See all the X's? So that tells you that some constructor for that string class has already executed and initialized that string object. Again, that's not what we want to do. Okay, so hopefully this is really clear as to what's going on. What we want to do is we want to use the initializer lists for the constructors, and it's really simple to do. What you do is immediately after the parameter list right there, you just put a colon, and you can follow it by the initializer list, just like we did in the slides. Okay, so in this case, I'll do it on the next slide just so it's little clearer there. What we can do is we can tell it which attribute do we want to initialize. Well, in this case, I want to initialize name, and we provide the initializer, which is the initialization value, I should say, which is none. Health to 0. All of these would be comma separated, and XP also to 0. That's it. And then we don't need the body of the constructor anymore because we've already done the initialization. We could certainly write any code we need here, but we're sure that when we're in the body of the constructor, those 3 attributes have now been initialized correctly, not initialized and then assigned to, but initialized. Okay, so that takes care of that one. We can also do the same for these here, and I'll just do them really quickly. And let me just copy this bit here. And what we'll do here is we'll set name. In this case, we have the value to set it to. It's going to be name val. And we'll still keep health and XP at 0, and we'll get rid of the constructor body. We'll get rid of some of those breakpoints as well and clean up the code. And you can see when you do it this way, you end up with empty bodies for the constructors. And that's okay, because obviously we want to put something else in there once our variables are created. And this last one, again, I'll copy this one just to save a little time here. We'll get rid of that, and I'll indent that in. There's my initializer, name val. In this case, I've got health val, and I've got XP val. And that's pretty much it. I'll get rid of this. And there you go. That's the final refactoring. You can see now we're using the initializer lists to initialize our objects, which is exactly what we want to do. Let me get rid of that extra colon right there. And that should do it. Other thing is, I put the order in here as name, health, and XP. That order doesn't really matter. It's going to be initialized in this order. Name, health, XP. Whatever order you declare these guys in right here in your class, that's the order that the initialization will take place. It just happens to be the same order that I've written here, and that's pretty much best practice is to keep the order the same. But don't rely on order here. The order is going to be the order that you declared these things in. Okay, so there you go. That's initialization list. Now you will notice a few things. We're going to talk about delegating constructors soon so we can get rid of some of this extra code. Because if you think about this, this is really the same as this, it's the same as that, and it's the same as that. So we'll have a little bit even more efficient way of doing this. In this video, we'll learn the basic syntax for declaring a class in C++. The syntax is very simple. First, we use the reserved keyword class, followed by the name of the class we're declaring. Notice that it's best practice to capitalize class names for our user-defined classes. Then we have a block which are open and closed curly braces, and the class declaration is terminated with a semicolon. In the body of the class declaration, we can supply the declarations that define the structure and behavior of our class. Let's see an example. Here we're declaring a class named player as we might have in a game application. Notice the class keyword followed by the name of the class, in this case player. Then in the body of the class, we can define the class's attributes or instance variables and methods. In this case, the class has a string named name and 2 integers representing the player's health and XP. Since C++ supports encapsulation, that means we can also provide methods or functions in the class body that are specific to the player class. In this case, we have 2 methods, talk, which expects a standard string, and isDead, which returns a Boolean. Now that we've created the class, we can create objects that are instances of that class. So in this example, I'm creating Frank and Hero, which are player objects. Notice the syntax. It should feel familiar since it's the same way we create primitive types. We can also create pointers to objects. In the last example, I'm declaring enemy as a pointer to a player object, and I'm creating that object dynamically on the heap using new. When I'm finished using the enemy object, its storage has to be freed up using delete. Here's another example where we declare an account class. Notice that accounts have a name, which is a standard string, and a balance, which is a double. And in this example, we have a withdraw method that expects the amount to withdraw and returns a Boolean indicating success. We also have a deposit method that expects the amount to deposit and also returns a Boolean indicating success. We'll talk more about how we define class methods in a few videos, but notice how they're basically function prototypes in these examples. Now that we've declared the account class, we can create objects of that type. So Frank's account and Jim's account are objects or instances of the account class. In the last declaration, Mary's account is a pointer to an account object that again has been allocated dynamically on the heap and then freed up when we're done with it. Once we have objects, we can use them like any other variable in C++. For example, we can create an array of account objects and initialize the array to Frank's account and Jim's account. We can create a standard vector of account objects and initialize it to Frank's account and then push back Jim's account. You can see how easy and how readable our code looks. We're using our own user-defined types and we're using them intuitively like we've used other C++ types. In the next video, we'll see the syntax for accessing the attributes and methods in objects. But first, let's head over to the IDE and create these classes. Okay, so I'm in the IDE. I'm in the section 13 workspace, the Declare Class and Objects project. This is just an empty little project right now with an empty main. I've included IOStream, string, and vector, and I'm using namespace standard. Remember, you really don't want to use namespace standard all the time. You really want to be explicit and type out, std, scope resolution operator, and whatever you need. But I'm going to do it because it'll save me a lot of typing time. Otherwise, these videos could be pretty long with me making typos. So what do I want to do here? Let's create the player class, the account class, and we'll create some objects. The first question is, where do we create the player class? Let's do the player class first. I could do it right inside main. I could say class player and define that class right in here. That's really not what I want to do, because if I do that, then I'm defining that class inside the scope of main, which means that only main will have access to that class. And that's not really what I want. I want to create my player class so that the entire application has access to it. So I'm going to do it right up here. And then later on in this section, we'll learn how to do it in an even better way. We'll use separate files to do it. But for now, let's learn about classes and objects. So what I want to do is I want to say class player. Remember, the class name should be in uppercase, and you need a semicolon right here at the end of the class declaration. So what do we put inside this class declaration? Well, we saw in the slides that you can put attributes in here. That's typically data. And we can put methods in here, which are operations or functions. That's what encapsulation is all about, putting all these things together. Now, what do you put in here? Well, it depends. It depends on what a player is in the context of your application. It could have all kinds of stuff in here, or it could have a minimal amount of stuff in here. That's the whole point. You really don't want to model a player that could be used in any application in the world. You just want to model a player that's going to be used in your application that you can extend easily. Okay, so don't try to model like the best player object or class you could ever have. Just solve your problem. So in this case, let's assume that a player has a name which is a string, and the player has an integer which is their health, and let's say something like between 0 and 100. 0 health, you're dead. And XP, which is experience, and that could be 3 up to whatever. It doesn't really matter. It's all based on our application. So now what we're saying here is that the class player is going to be a blueprint to create player objects from, and every player object is going to have a string that represents their name, 2 integers, one representing their health, one representing their XP. Okay. Now, what methods can we have? We can have a ton of methods. Let's just create 2 of them really simply so you understand how this works. What you do here is you basically do everything we learned when we talked about functions. So I want to have a method called talk, and it expects a string. So whatever string you pass into the player will talk it right back out. And let's say we want to have is dead. This is a method that returns true or false based on whether the player is dead, and the player might be dead if their health is 0 or whatever other criteria we have for that. Okay. Again, notice that what these look like are basically function prototypes at this point. We could implement them right here, and we will in a couple of more videos. But for now, let's just think these are the attributes, these are the methods. Okay. Also, there's the concept of public and private, what we have access to. We'll get to all that really, really soon. But that's it. That's a minimal player class. Given this, I can create player objects. Now let's create two player objects right here in main. I'll say player Frank and player Hero. That's it. When these two lines execute, the system will create two player objects. One is called Frank, one is called Hero. Each one of them has a name, health, and XP. Each one of them can call these methods and talk and ask if it's dead or not. Okay, so hopefully that makes sense. Let's run this right now. We're going to run this in the debugger so you can see them. What I'm going to do is I'm going to save this, then I'm going to click right here in the gutter, and you get that little stop sign for the debugger. And then what I'm going to do is just go to debugger, start debugger, or you can just press F5. Okay. And I've got my debugger set up so that my local variables are over here, any watches that I want to look for are here, and then the call stack is here. The call stack is real simple. We're just in main right now. Okay. You can see I've got my two local variables. You can see them displayed right up here. I've got Frank and I've got Hero. Right now, they don't really exist because I haven't created them yet, but they're in the local variables pane here. So what I want to do is let's create Frank and Hero. I'll just hit the next arrow down here, and Frank is now active, and then Hero is now active. And if you expand these guys a little bit, you can see something of what's going on here. You can see Frank has a name, right? Of course, here it is. It's one of the attributes. Frank has health and Frank has XP. Notice it's garbage data, right? The only reason that the string is not garbage is because our C++ string class, our standard string class, has a default initializer, which initializes it to empty, which is pretty cool. But the rest of this stuff is junk, just garbage data. The same thing with health and the same thing with XP. This is the same sort of behavior we saw when we created regular variables. Okay, so we'll talk about initializing these objects in a couple of videos where we use constructors to do it, and that makes things much, much easier. Okay, so I'm going to stop this debugger, and we can also create objects on the heap, just like we could regular primitive types. So in this case, I'm going to say player enemy is a pointer to a player. Remember, you read these from right to left. And you know what? Let's set it to null pointer. I'm going to do this in two steps just so you can see this happening in the debugger. Then I'm going to say enemy equals new player. That's going to create the enemy on the heap, that enemy object, which is a player. And then I'm just going to say delete enemy when I'm done. Okay, so let me move that right to about there. And let's run this again in the debugger. Here you can see that right now there's garbage data in the value for enemy, right? So it exists, it's a pointer, it's got a value and it's junk right now. So when I execute the statement, I just nulled it out. Now you can see it's 0. That's the safe way to do things. Now I want to create this new player object on the heap. So right now, when I execute that statement, you expect that address to change, right? Because obviously I'm creating this on the heap and I'm storing the address of that object in enemy, which is a pointer. So let's step through it. Here we go. At this point, that enemy object is created. It's on the heap. It's a player, right? That's its type. And if I expand this, you can see that the name is empty, but health and XP contain garbage. Just what we would expect. And then when we're done with it, we can delete it. Okay, really, really straightforward. Let me add a few lines of code right in here, and we'll get rid of that breakpoint and we'll move it in a second. Once we have these objects, we can treat them like any variables, just like we've worked with integers and doubles and everything else. So in this case, suppose I want to create an array right here called players. And it's an array, and I want to set it to Frank and Hero. Right? Just like we've done with integers, it's the same idea. So let's read this together here. It says players is an array of player objects. Well, I've got two of them right here, so I can initialize that array to Frank and Hero. I'm going to save this, and let's put a breakpoint right there so we can look at it, and we'll run it. Okay, so you can see players is right here, and I'm going to step through it. So now player has been initialized here to those two objects. The first object and the second object. The first object is Frank. The second object is Hero. And you can tell, we don't have any strings for names now, but you can tell from the garbage values that they really are indeed those objects. Okay. So it's really as simple as that. This is very powerful stuff because we can create our own user-defined types, which is what player is, and then use it just like we can use any other variable. Okay. So last thing is, let's try to create, rather than an array here, let's do a vector. So let's create a vector. A vector of what? Well, we've done vectors of integers and vectors of strings. Well, why not a vector of player? Okay, and we'll just call it playervec. So again, what is this? This is a collection of player objects. Okay, so let's initialize this to Frank. That's a player object. And then what we can do is we can ask the playervec to push back. Remember, push back is a method in the vector class. And we can push back Hero. All right, so let's execute both these lines. And again, I'll put a breakpoint right there. And we'll go back to the debugger and run this. So right now we have playervec. So I'm going to step into it here so that I can create that vector. Okay, the vector is now created. It's called playervec. It's right here. If I expand it, you can see that right now there's one item in there. And that one item is Frank. If you look at Frank up here, you could see it's garbage data right here. Well, it's going to be the same garbage data right here because we just copied that object. Okay. Now, when I execute the next line, which I'm going to, just by clicking next here, that should add Hero to that vector. So let's do that. And now you can see, you notice here that it didn't really show up here, this playervec. What you can do when that happens is you need to refresh right here. So when I refresh, see right now this says there's only one item in there. We know there are two. So if you refresh and then expand playervec, there you go. Now you see both items. In this case, that's Frank. And in this case, that's Hero. Okay, so all this works exactly like it did with integers and doubles and so forth. All right, so let's create an account class now real quick. And we'll do it right below the player class. We'll create a class account. We'll create the body. And we'll put a semicolon on the end. Don't forget that semicolon. If you forget that semicolon, you're going to get compiler errors. And they're going to be strange compiler errors because the compiler is going to be lost trying to figure out where you are. Okay, so here we can have attributes. And what we'll say here is, again, we've got a string name, the name of an account, and we've got a double, which is called balance. And then here we can have methods. Again, as many methods as we want. Now you'll notice that over here, I just prototyped those two methods. I just declared them. I never defined them. So how in the world did this work? Well, this worked because I never called them. If I had called those methods, I'd have a linker error because the linker is going to say, I don't know where those things are. You told me they were there, but I don't know where they are. Okay, we'll implement all this stuff in the next few videos. So let's create a couple of methods. Bool deposit and a double, and bool withdraw a double. Those are my two method declarations. I want to deposit some amount, and I'm going to return true, false, whether it was successful or not. And I want to withdraw some amount. Again, it's a double, and I want to return true or false, depending on whether it was successful. Once I've got that class declared, I can now create account objects. So I could say Frank account. I could say Jim account, and so forth. Okay, and now I'll put a break right here. And let's check that out in the debugger. You can see right here is Frank account. So I'm going to go next and next again. That's created those two objects. So here Frank account has a name, it's empty, and it's got a garbage number for balance. And the same thing for Jim account. It's got a name and it's got a balance. Okay. Now something that's useful in C++11 and going forward is that you can actually initialize these guys right here. So let's just say that I wanted to initialize that to account, sorry. And I wanted to initialize balance to 0. I can do that. And I can also do this up here. So let's just say I wanted to initialize this to player. If you think about this, it's really odd that they're letting you do this at all because we're creating these initialization variables here. but we don't even have objects yet, right? I mean, this is just a class declaration. We don't have any objects, but they can come in handy. And I'll show you how to initialize these things using constructors and initializer lists in a little while. But let's say that XP is 3 and the health is 100. Okay, so let's run this again this time. And I'll stop the debugger and start it again. Oops, forgot my semicolon. And probably forgot some down here as well. So let's run that. Okay, so now you can see, let me scroll up a little bit. I'm right here on line 33. So I'm going to go next. I've just created those 2 accounts. And again, I'm going to go next. And I just created those 2 players, Frank and Hero. But now when I look at Frank, you can see Frank's name is player. Its health is 100. Its XP is 3. So basically any object is going to get these values right here. And as I said, we'll learn other ways to initialize. But this is pretty nice right now because we can actually see them in the debugger and you can see this working. Okay. And the same thing with the account. Frank account here says account with a balance of 0. And Jim's account is account with a balance of 0 as well. Okay. All right. Perfect. Now in the next video, what we'll learn to do is we'll learn how to actually access those class attributes and class methods using an object. Okay. So I'll see you in a little bit. In this video, we'll learn how we can access class attributes and methods. Of course, we want to create objects from our classes, but we also want to be able to use and modify the object's attributes and call methods for specific objects. There are 2 ways to access class members. We can use the dot operator, and we can use the member of pointer operator or the arrow operator. Remember that some class members may not be accessible since we can hide them. We'll see that in the next video. We've already seen how we can use the dot operator when we worked with standard vector and string. If we have an object, then we can use the dot operator followed by the class member that we want to reference. It's as easy as that. For example, if I have an account object named Frank's account, then I can access the balance attribute with frankaccount.balance. And I can deposit $1,000 into Frank account by writing frankaccount.deposit 1,000. In this case, we're accessing the deposit method. Notice that the object is to the left of the dot operator, so that method will be called on that specific object. In this case, the Frank account object. If we have a pointer to an object, then we need to dereference the pointer first in order to get to the object, and then we can apply the dot operator. There's 2 ways we can do that. Remember, in these examples, Frank account is not an account object. It is a pointer to an account object which has been dynamically allocated on the heap. The first way to do this is to explicitly dereference the pointer and then use the dot operator. In order to access the object's class members, we have to dereference the pointer using the asterisk and then use the dot operator to get the class member we want. But notice that we have to use parentheses here, since the dot operator has higher precedence than the pointer dereference operator, and we want to be sure that we dereference first. While this syntax is explicit, it can be a little tedious to read and write. So C++ provides an alternate operator called the member of pointer operator, which is often referred to as the arrow operator. It's a dash followed by a greater than sign, which looks like an arrow pointing to the right. This operator has the same effect as the first example above. It will dereference the pointer and then apply the dot operator. As you can see, this operator is very intuitive to read and use, and it's used very often. That's all there is to accessing class members. Let's head over to the IDE and we'll access some class members for the player and account classes. Okay, so I'm in the IDE and I'm in the section 13 workspace, the Accessing Class Members project. What we've got here is we've got the same player, class, and account class that we created in the last video with its attributes and methods, just like we did before. And what we'd like to do now is access some of these attributes and methods from within our main. And we want to access them for specific objects, obviously. Now, there's a couple of things we're going to do, and we'll discuss them in detail in a few videos from now. But by default, all of this information in a class is private, and we don't have access to it. So let's make it all public for this video. And in the next video, we'll talk about public and private. So this is what I'm going to do here is just say public colon for the account class and public colon for the player class. That says that everything after that access modifier is public, which means we've got access to it, no worries at all. Okay, and as I said, we'll talk about public and private in the next video. So what do I do? Well, let's create some objects. Let's create a player object, and let's call it Frank. And now what I want to do is I want to set Frank's name, health, and XP. Those are the attributes for the player class. Well, how do I get to them? This is where we use the dot operator. Frank is an object, so we can say Frank dot name, and we could just set it to Frank or anything else we like. We could say Frank dot health is 100, let's say. And finally, we can say Frank's XP is, let's say, 12. Okay, so it's really as simple as that. That sets those attributes, the values for those attributes. Now, obviously, if I wanted to print out those attributes, I could just do a cout frank.health, and that's it. And I'm going to get whatever was stored in there as a value. So let's take a look at this in the debugger and see what it looks like. So I'm going to put a breakpoint right here on line 33. And let's run this in the debugger so we can see what's going on. First of all, you can see over here that Frank is a player object. That's its type. And if I expand this, you can see it's all garbage right now, right? So this is all garbage, and let me hit next. And I just did. Let me refresh this one more time, and you'll see that the string is now empty for the name. Now what I'm doing here is I'm saying set the name attribute for the Frank object to the string Frank. Okay, and then I'm setting the health attribute for the Frank object and the XP attribute for the Frank object to 112. So I'll hit next a couple of times, 1, 2, 3 times. I'll execute those 3 lines of code. And what I'll do here is I'll refresh the screen so that we can see that now we've got Frank is the name, the health is 100, the XP is 12. Exactly what we expected. Okay, so that's a really easy way to do this. Now remember, this is all based on the fact that this is public. If this was private, you'd get a compiler error, and I'll discuss that in detail in the next video. Same idea holds for accounts, but how about these methods here? I haven't implemented those methods. So if I try to say something like frank.talk, and I pass in a string to say hi there, or something like that, this will compile just fine, but it won't link because I haven't implemented this method. How do we implement this method? There's a whole bunch of different ways to do it. Let's do it the simple way. And again, I'm going to do a whole video on methods and how to implement them. But for now, just to get this to work, let's put in a method block here. And just like we've always done, I'm going to say cout. What's my name? Well, my name is name. So I'm going to say name. I'm going to put another insertion operator, and I'll say says, followed by the text to say, which is being passed into me, followed by an end line. That's it. Now I've implemented that method. So now when this code executes right here, frank.talk hi there, it should say Frank says hi there. Okay, so let me stop this and let's run this again. And again, we'll run this in the debugger. And since we have some output, what I'm going to do is put that output window right over here so we can actually see what's going on in our output window. Okay, so let's do this again. I'm going to select next. I'm on line 34 now, line 35, line 36. Now I'm going to execute line 36. And at this point, my Frank object has a name Frank, health 100, XP is 12. Now what's going to happen is we're going to call the talk method for the Frank object. And control will be transferred right over here to this method we just wrote. We're passing in this string hi there. And it should say Frank says hi there. And it should display it right out here. So let's take a look. That's exactly what happens. Frank says hi there. Okay. So what's neat about this is that since I'm calling the talk method for the Frank object, these attributes are available to that method. Right? So I don't have to pass in the name of Frank because I've already got it. I can just simply say name. As far as this name is concerned. Remember, we talked about scope a while back. Well, we look for the definition of this variable inside the class first. If it's not there, then we go global. But we're going to look for it here. There it is. That's the one we're going to use. Okay, so there you go. That's a real simple example of calling some a member method. Really, really easy. Now, how about if we had a pointer? Let's try that. So let me stop this and we'll do the same kind of code and we'll write it with a pointer. And I'll leave this window a little bit smaller so we can see. So let's say we have a player and it's a pointer this time called enemy, which is a pointer to a player. And I'll just instantiate it right here. So I'll say it's a new player. Okay, so in order to get to that player object, I need to dereference the pointer, right? Remember, enemy is not a player object. Enemy is a pointer to a player object. So in this case, there's two ways to do it. We can dereference enemy. Okay, so what I just did was I dereferenced the pointer. So now I've got the object. And I can say enemy dot name is enemy. Simple as that. I could say enemy dot health is 100. And I could do the same thing for XP, but rather than use this syntax where we're explicitly dereferencing the pointer and then doing the dot operator, let's use the arrow operator here. So what we can say is enemy followed by the arrow operator, and then we can say XP is, let's say, 15. Right? Now, how do you call a method here? Same way. We could say enemy arrow. So what I'm going to do is I want to dereference that pointer and use the dot. And then I'm going to call talk and say, I will destroy you. Okay, so let's try this now. Let's walk through this one more time. So we'll debug this. I'll move this over here real quick. And let's step through the program. Right now we're on line 33. That's where we've got the breakpoint. So we're creating the Frank object. We're setting the name to Frank, the health to 100, and the XP to 12. And then we're going to call the talk method on the Frank object, which should display Frank says, hi there. And that's exactly what happens over here in the output. Now we're going to create this enemy, which is a pointer to a player. Now it's important that you see that. You can see the type here. The debugger is really helping you out here. You can see Frank is a player. Enemy is a pointer to a player. You can see that the debugger is really helping you out there with the type. Okay. So at this point right now, that enemy is garbage, right? We've got garbage data in the pointer. As soon as I execute line 39, now it will be pointing to a real player object. So I'm going to hit next. Now we've got enemy pointing to a player object. And if I come over here, you can see the name is junk, the health is junk, and the name is empty, the health is junk, and the XP is junk. Okay, so what do I do here? I want to dereference enemy and then get the name. So I want to follow the pointer and get the name. Okay. We can also use this area right here with the watches. So I can add a watch and you can put whatever expression you want. So I just want to see this expression right here. Dereference enemy. That's the object. So when I add that, you can see I'm seeing the same thing that I'm seeing here. Now, for some reason, this you need to refresh, this you don't. So it's kind of nice to have these here. So let's walk through this. Dereference enemy, that means go to the object that I'm pointing to and set the name to enemy. Okay, so let's execute that line of code. Notice how enemy shows up here. Doesn't show up here unless I refresh, but now it does. Then I want to set the health to 100, so I'll do that next. Now the health is 100. XP is 15, but now we're using the arrow operator, but it's all the same. XP is 15. And now I want to call the talk method for the enemy object, but I want to do it through the pointer. And when I run this, it should say enemy says, I will destroy you. So let's try that out. And that's exactly what it says. Enemy says, I will destroy you. Okay, so that gives you an idea of how some of this works. What we'll do next is let's update this a little bit. We'll do that quickly because this video is getting a little long now. And what we'll do is we'll do the account. Okay, same idea. Except here, I'm going to say something like, what do I want to do when the user passes in a number to deposit? Well, what I want to do is just say something like balance plus equals bal, right? Just something really, really simple like that. I want to increment the balance by whatever they passed into me. And for withdraw, I just want to say balance minus equals BAL. And while I'm at it, I want to also say cout, something like in deposit, just so I know that I'm in there, so we could see this being called. We'll do that, and we'll do the same thing for withdrawal. And again, just so we can see these things are being called. Now we're defining these methods right in here, right inside the class. As I said, there's other ways to do this, and I'll show you what those are in a couple of videos, but let me just change this so we can understand how to access this. That's it. So now let's create, right up here, let's create an account. So we'll say account, and we'll just say Frank account. Right? That creates an account object. Now I can set the name and the balance of that account. These are public attributes right now. So I could say Frank account, and I'll just say equals Frank's account. That could be any C++ string. And then I want to set the balance. So I'm going to say Frank's account dot balance. And let's say that there's $5,000 in there. Okay, that's it. Now, let's say I want to deposit $1,000 into that account. I could say, again, you need the object that you're working on has to be to the left of the dot operator. So it's going to be Frank account dot deposit, and I'm going to deposit 1,000. Okay, and then we'll say Frank account dot withdraw, and let's say we want to withdraw 500. And that's it. And I'm forgetting semicolons because I've been working with a programming language all day that doesn't need them. So I'll put them in there. Hopefully I didn't forget any other ones. Okay, so that's it. Let's put a breakpoint here and let's try running through this. So again, we'll go to the debugger. And Frank's account equals, oops, of course, Frank accounts dot name. I need to set that specific attribute. And Frank account dot withdraw 500. I have an extra paren right there. Okay, let's try that now. Okay, perfect. So let's put the output window over here on the side and let's walk through this. So I'm at line 33 right now. I'm creating Frank account. So I'm doing that right now. Now I'm setting Frank account's name to Frank's account. We'll do that, and the balance to 5,000. So let's take a look at Frank's account right here. We'll refresh. There's Frank's account, and the balance is 5,000. Now, when I call the deposit method, it's going to call this method right here for that Frank account object and increment the balance by 1,000. Okay, so let's do that. And we should also get an output statement printing out over here. There you go, in deposit. I'll refresh Frank account again. Notice I've got 6,000 in here now. When I call the withdraw method, this should go down to 5,500 and it should say in withdraw. So let's do that one more time and we'll refresh one more time. There's 5,500, exactly what we expected, and the in withdrawal kicked in. Okay, same idea here with a pointer that we did with the player object. I won't do that because the video is getting a little bit longer now, but I'll let you guys try that out. You can create Mary's account, which is a pointer to an account. And then you can access the attributes using this syntax or the arrow operator. Okay, so if you have any questions, please drop by the forum and let us know. In this video, we'll learn about using access modifiers to determine what will be hidden in a class and what parts of the program have access to this information. C++ has three basic class member access modifiers. These are public, private, and protected. Class members that are public are accessible everywhere. Private class members are only accessible by other members of the same class or by friends of the class. We'll talk about friends later in this section. Finally, protected members are used with inheritance, which we'll talk about later in the course. Using the class member access modifiers is super simple. In the body of the class, you specify the access modifier followed by a colon. Then everything you declare from that point forward will have that access modifier applied to it. In this example, we're using the public access modifier, and anything we declare after this will be public until we see a different access modifier. In this example, we're using the private modifier. By default, everything in a class will be private if no access modifier is specified. Protected works exactly the same way as private. For now, you can think of protected and private as being pretty much the same. The difference comes in when we use inheritance. Of course, we commonly use public, private, and protected all at the same time to tell the compiler what class members should not be available outside the class and what class members should be part of the public interface of the class. This is how C++ implements information hiding. In this example, the player's name, health, and XP are all private. This means that they're only accessible from the other members of this class and from friends of the class. The talk and isDead methods are publicly accessible. So, what happens if we try to access a private class member? Simple, you get a compiler error. Here are some examples. First, we create a player object named Frank. If we try to access the player object's name instance variable, then we get a compiler error because name is private and it's not accessible from outside the class. The same is true for health. Why would we want to make some class members private and others public? The idea is that you want to control access to certain data and methods by making them private. For example, you want to prevent users from directly setting Frank's health to 1,000 as in this example. Maybe the maximum health for the player is 100. In order to control this, you would create a public method in the class that sets this health property. And in the code for that method, it makes sure to max out the health at 100. Since that method is a class member, it would have access to the private health property. In the second example, we create a pointer named enemy to a player object. If we try to directly access the XP property, we get a compiler error because it's private. However, we can call the talk method with no error since it's public. Let's see another example. In this example, we have an account class, and the name of the account and the balance of the account are private. These properties cannot be accessed directly from outside the class. We also provide public withdraw and deposit methods that can be called from outside the class. Since these methods are member methods, they have access to the balance and can update its value based on whatever business logic we have for the class. Here are a few examples that use the account object. Frank account is an account object. If we try to access the object's balance property directly, we'll get a compiler error because balance is private. However, we can use the deposit method and provide the amount to deposit since deposit is public. The idea is that the deposit method would somehow verify that the $10 million that I want to deposit are indeed available before incrementing balance. If I try to directly access the account, I also get a compiler error for the same reason. The account name is private. The same behavior applies whether we access an object using the dot operator or via a pointer using the arrow operator. In the case of Mary's account, trying to access the balance or name directly results in a compiler error. But using the deposit method is fine since it's public. You can see how powerful this is. For example, if we have an object whose balance is $20 million, and we know that that must have been an error, then the only place where that error could have happened in this example is in the deposit method. There's no way that any other part of the program could have changed that value since the value is private. This makes testing and debugging code much, much easier. Okay, so I'm in the IDE. I'm in the Section 13 workspace in the Access Modifiers project. And in this project, we've got our player class that we've been using. And you'll notice I made a couple of changes to it. I made the attributes all private. So the name, the health, and the XP are all private. And I made the two methods, talk and isDead, public. Okay, so I want to show you the compiler errors that you'll get when you try to access those private data members. So in this case, I want to create a player object, and I'll call it Frank. And if I try to set Frank's name, so I can say frank.name equals anything. In this case, I'll just say Frank. Okay. And we'll try to compile. I'm going to build and run with Control F5. You see the error I'm getting. And you can see it here in the box as well. It says player's name is private within this context. Same thing we're seeing here. So you're trying to access a private attribute, which is name, from outside of the class. This is exactly the same error you'll get if you try to use health or XP. And it's not just a matter of trying to set that variable, it's trying to use that variable as well. Okay, so if I try to do something like cout frank.health, and I'll do an end line here, and we'll compile this as well, you'll see I get two errors now. Same idea. I don't have access to health. It's not just a matter of not allowing you to set it, it's not allowing you to access it. Okay? Now, these, I'm going to comment those two out for a moment. And let's initialize the name here just to player, just so we have something to see when we call the talk method. Okay, so now what I can do is I can say frank.talk, and I can pass in the string hello there. Now if I try to build and run, it says player says hello there. Okay, so we know it works in this case because we're accessing a publicly accessible method right here, talk. Same thing with isDead. We can't call isDead because we haven't implemented it yet, but we did implement talk right here. Okay, so that's really all there is to it. If you get these errors that are saying you don't have access to something, that's exactly why. Now, why do we do this? It's really good programming practice to hide certain parts of your class's declarations. The idea is you want to control that variable via some sort of public method. So they've got to go through the public method, and then the public method makes sure that the health is within some reasonable range. And as I mentioned in the slides, if we're doing this and we output some value of health that's 20,000 or something like that, that's really, really out of whack. If health is public, then anything could have changed that property. But if health is private, then I know that the changes that were wrong happened somewhere in here, right? Somewhere in the public interface. My methods made that mistake. And I can find and fix that error much, much easier. In this video, we'll learn about how to implement member methods in our C++ classes. You'll be glad to hear that class methods are implemented in a manner very similar to the way we implemented functions, but I'd say that they're generally less complex. This is because member methods have access to the class's member attributes, so we don't have to pass so many arguments around. C++ gives you many options regarding where to write code for member methods. You can define the member methods right inside the class declaration. If you do this, then the methods become implicitly inline. While this is okay for small and relatively simple methods, we tend to implement larger, more complex methods outside of the class declaration. In order to do so, we need to tell the compiler that we're implementing a method that belongs to a specific class. So we use the class name followed by the scope resolution operator and then the method name. This unambiguously tells the compiler that you're implementing a method for a specific class. In C++, it's also very common to separate a class's specification from its implementation. This makes the class much easier to manage. We usually create a header or include file that has a .h or .hpp extension for the class specification, and then a separate .cpp file for the class implementation. First, let's look at implementing methods inside the class declaration. In this example, we're declaring an account class. Notice that the account class has a private double named balance and two public methods, setBalance and getBalance. setBalance sets the balance to the value passed in by the user, and getBalance returns a copy of the account balance. These public methods are necessary to access the balance since the balance is private. Notice the syntax is exactly as it was for defining regular C++ functions. Also notice that the public methods have direct access to the private balance because they're members of the same class. Now let's see how we would implement these methods outside the class declaration. In this example, we're defining the setBalance and getBalance methods outside the class declaration. Inside the class declaration, we simply provide the method prototype or declaration. This tells the compiler the name of the methods, the parameters they expect, and the return type. The compiler can then type check the method implementation when it sees them. In order for the compiler to know that these methods belong to the account class, we have to prefix the method names with account followed by the scope resolution operator. Then we implement the method as we normally would. In this case, the compiler knows that the two method implementations are for the method declarations in the account class we provided. As our programs get larger, we really want to separate class specification and class implementation into different files. Let's see an example of how we can do that. In this example, we create a file named account.h. This is an include or header file that will #include in our .cpp files whenever we need to use the account class. Notice that in this file, we provide the specification for the account class. Before we can use or #include this account.h header file, we need to take care of a potential problem. If this file is included by more than one CPP file, then the compiler will see the declaration for the account class more than once and give us an error about duplicate declarations. In order to solve this, we can use what's called an include guard that ensures that the compiler will process this file only once, no matter how many times it's included. An include guard is just a series of preprocessor directives that guarantees the file will only be included once. The way it works is we wrap up our entire class declaration in this include guard. The first line is #if not defined _account _h_, all in uppercase. This checks to see if the preprocessor has a symbol named _account _h_. This symbol name can be anything you want, but best practice is to use some sort of combination of the file name in uppercase with preceding and ending underscores. Any name is fine as long as it's unique in the program. If the preprocessor has that name defined, then it skips the entire file and goes to the #endif at the end. In other words, it doesn't process the file since it's already seen it because the symbol has been defined. If the symbol has not been defined, then the symbol is set and the file is processed as usual. As you can see, it's pretty simple, but not very elegant compared to more modern programming languages. So now this is what the account.h file typically contains. You can see the include guard wrapping the class declaration. Now we can provide the implementation for the account class in a separate file named account.cpp. Many compilers also support the #pragma_once compiler directive. The effect of this directive is the same as the include guard. While many compilers support this directive, some don't, so check your compiler documentation to be sure. Now we can provide the implementation for the account class in a separate file named account.cpp. Let's take a look at that. This is the source code for the account.cpp file. Notice that we include account.h and it's in double quotes. Up to this point, our includes have used angle brackets with no extensions. There's an important difference between the two forms of include. Include with angle brackets, as in include IOStream, is used to include system header files, and the compiler knows where these are located. Includes with double quotes tell the compiler to include header files that are local to this project. The compiler also knows where those are. Notice that this file implements the two methods declared in the account.h header file. Now our account class is complete. The specification is in account.h and the implementation is in account.cpp. How do we use an account in our main CPP file though? Let's see in the next slide. Here's our main.cpp file. Notice how we include IOStream as well as account.h. It's important that you always include .h files, never include .cpp files. Then we just write our main as we normally would. When the program is compiled, both the main.cpp and the account.cpp files are compiled and then linked to produce the executable. Let's see how all this works in the IDE. Okay, so I'm in the IDE and I'm in the section 13 workspace in the Implementing Methods 1 project. What I'm going to do here is I'm going to implement these methods in this account class, and we'll implement some of them inside the class declaration and some of them outside the class declaration. Then we'll create another project, Implementing Methods 2, where we'll separate the specification from the implementation, and we'll create the account.h file and the account.cpp file. Okay, so let's start here. What we're doing here is we have our class account right here, and we've got two private attributes, name and balance, and then we've got the methods. And the methods are really what we're interested in here. Now, in this case, I've got 6 methods, all public, We've got a set balance and a get balance. And you can see that these methods have been implemented inline right inside the class declaration. This is easy to do, and this is okay to do when you've got methods like these that are really, really straightforward methods. They're done, they're implemented, and we're all set. Now we can also implement methods outside the class declaration. Notice these last four methods. I've got setName, getName, deposit, and withdraw. And what you see right here are basically the function prototypes or the method prototypes. They're not defined here. These are only declarations. What we want to do is we want to define them outside the class. And you'll notice the class begins here on line 8 and it ends right here on line 26. So what we want to do is define them outside the class. And let me show you how to do that. It's really straightforward. What we've got here is, so let me show you how easy it is. Here are the methods that have been implemented outside the class. We're starting on line 28 right here. The method is setName, which is this method right there. It's called setName. Now, it's not just good enough to say void setName. That would just define any method. We want to define the setName for the account class. So we need to prefix the name of the method setName with the name of the class followed by the scope resolution operator. Now when the compiler sees this, it knows, oh, okay, you're defining the setName method that you declared in the account class. So it's going to come up here and it'll be able to type check all of these things together and make sure that there's no mistakes. Okay, so you can see what's going on here. In this example, it's really straightforward. A string is being passed in, and the name is set to whatever string was passed in, which is n. Remember, name is one of the attributes of the class. It was private, and that's okay. This is a member method, so it has access to private information. GetName simply returns a copy of that string. Okay, and in this case, we've got our deposit and our withdraw. So you're going to pass in an amount to deposit. This method would somehow verify that that amount is indeed there so that you can deposit it. And all it does is it increments balance by whatever the amount is. And it returns true. Obviously, you would return false if it didn't verify. Okay. And then the last method that we'll implement is this account withdraw method. Again, it's the same idea. We prefix the name of the method with the name of the class because it's a class method. And here's the amount. And what do we do here? Well, we look at the balance and we subtract the amount from it. If that's greater than or equal to 0, then there is sufficient funds. We'll just decrement the balance by the amount and we'll return true. Okay, simple as that. If the funds aren't there, then we'll just return false. So let's see how we can use this in the main. And it's really, really straightforward. I've got some breakpoints in here that we'll follow in a second. So what I'm doing here is I'm creating an account called Frank Account. And I'm setting the name to Frank's account. Now, I can't say frankaccount.name because that's private. So I've got to go through this public method called setName. I'm doing the same thing for balance. frankaccount.setBalance to 1,000. I can't say frankaccount.balance equals 1,000 because balance is private. Okay, so at this point, I've got an account. It's got Frank's account is the name, 1,000 is the balance. And then I want to deposit $200 into that account. I'm going to call frankaccount.deposit 200. If that returns true, then the deposit was okay. And I'm going to just display that. If that returns false, then the deposit was not allowed for whatever reason. Now I'm going to call some withdraw methods here. I'm going to call the withdraw method on the Frank account with 500. So I'm going to check. I should have 1,000 in there, right? Actually, I should have 1,200 in there. So I just put $200 in there. So I'll check to see if 1,200 minus 500 is greater than or equal to 0, which it is, and the withdrawal should be okay. I should have $700 left after that. Then I try to do another withdrawal with 1,500, and that should fail. Okay, so let's run this through the debugger here. Right now I'm at line 53, and I'm going to set a watch to Frank account. That way I can see that as it changes real easily. And that's already set here. So what I'm going to do is I'm going to hit next. And remember, I'm right here on line 53. So at this point, I've just created the Frank account object. Now I want to set that name. Notice that the name is empty right now and the balance is garbage. I'm going to set the name to Frank's account. So when I select next, you can see that that's changed right here to Frank account. And now I want to set the balance to 1,000. So we should see that change here as well. Again, remember, these two attributes are private. That's why we're going through those public methods to change them. Now what we're going to do is we're going to deposit $200 into that account. So let's step through here. And what we're going to do now is we're going to jump to this method right here. I've got a breakpoint in there. That's where I'm at right now. Assuming there was some business logic here that would verify that deposit amount was there, I'm going to increase the balance by 200. So I should have 1,200 here when I finish, and return true. And I'm back now. You can see I've got 1,200 here, and I'm going to return true, and it should display deposit OK over here. And exactly what happens. Now we're going to withdraw 500. Well, I've got 1,200, so that should work. So let's try that. And you can see I'm right in here now. I've jumped to this function, this method right here. So balance is 1,200 minus 500 is greater than or equal to 0, so we should be good. In that case, I'm going to decrement the balance by the amount, and I'm going to return true. And I'm right back here now on line 63. Notice I've got 700 left in the account, and it should display withdrawal OK. The last example here is I'm going to withdraw 1,500. I don't have 1,500, so it should fail. So I'm going to go back up here. If balance amount is greater than or equal to 0, it's not. So it's going to go straight to false, which it's going to return. And then when I come back to my main, I'm right here on line 70, and it should display not sufficient funds. And that's exactly what it does. Okay, so there you go. This is a real simple example of implementing these class methods both inside the class declaration and outside the class declaration. Okay, what I'm going to do next is we'll create a new project called Implementing Methods 2. And what we'll do is we'll create the account.h and account.cpp, and then we'll have a main CPP that runs the whole thing. So I'll set that up and be right back. Okay, so I'm back. I'm still in the section 13 workspace, but I've just created a new project called Implementing Methods 2. And all it has in it is a main CPP file that you're looking at right here. What we're going to do here is we're going to create our account.h file, our account.cpp file, and then we'll use this main CPP file as a driver so that we can create some objects and so forth. Okay, so what do we do? Well, we need to create an account class. Every IDE has its way of creating a new class. CodeLite is no different. If you select the source directory and right-click, you'll have an option for new class. We'll select that, and then you get this pop-up dialog. And it's going to ask you, what's the class name? Well, the class name is account, again with a capital A. Don't worry about namespace. And then the block guard is what you saw with the include guard that I talked about. This is that pound define. So I'm just going to say underscore account underscore H underscore. You can really do anything you like. You can even leave it blank and it's going to use its own way of doing it. Okay, so that's it. There's some more advanced options here, which should all be off at this point. And you can choose to create a .hpp file instead of a .h file. I'm not going to. And you can also choose to use the pragma once command. Again, I'm not going to. I'm just going to use the block guard. You select OK. And what happens here on the left-hand side, you'll see that we've got two files that were created. We've got the account.h file and the account.cpp file. That's exactly what we want. Now we're going to start with the account.h file. Notice the wrapper. Okay, now I'm going to get rid of what it generated for me. And what I'm going to do is I'm going to copy and paste the account that we were working on. And I'm just going to copy and paste the declaration of the account. So let me do that right now, and I'll paste it right in here. It should be pretty familiar. There's the class account. Those are the two private attributes. Let's see what we've got here. Now we've got to do a couple of things. We're using a string here. So what we want to do is here we want to pound include string so that our account header file is complete. And we really don't want to use a namespace in here. So I'm just going to prefix this with standard. And let's see, I've got a string here as well. And I believe I've got one here as well. And I think that'll do it. So that's my account.h file. You can see it's exactly as we had before. There's my account declaration, and it's wrapped up in that guard. Okay, now let's go to the account CPP. Now you'll notice that it's generated the include for me. And also it's generated these two functions, these two member functions. We're going to get rid of those. This is a constructor and that's a destructor. We'll talk about those in a couple of videos. But for now, I just want to get rid of them. And what I want to do is I want to copy and paste those 4 methods that we wrote. Remember the ones we wrote outside the class. So I'm going to copy them right in here like that. There's my account. There's my, and again, I'm going to prefix this with standard wherever we're using strings. And I think that was the, oh, right here's the other one. That's it. Now what we'll do is we'll go to the main. And what we're going to do here is we're going to include account.h because we're going to need it in our main. And if you remember the code for the main, again, I'll copy and paste it because it's really straightforward. That was the code for the main where we created the Frank account, we set the name for the account, and so forth. Now, what we're going to do is I'm going to save this and we'll compile the whole thing. We'll just basically do build and run, Control F5. What's going to happen is the .cpp files will both be compiled and everything will be linked into an executable. Now, we may run into some errors here and we'll fix those as we go. So I'm going to hit Control F5. No errors. Everything worked great. You can see I run the file and I get deposit OK, withdrawal OK, not sufficient funds, exactly like we had before. We could run this through the debugger if we like, but it's really as simple as that. Throughout the course, this is the way we're going to start writing code now. We're going to have the specification here and the implementation in the .cpp file. And you can see again, let's do this one more time. You can see the account.h, the header or the include file. That is our declaration for the account class. We have to wrap that up so that the compiler only sees it once. We're including string here because we've got our string class that we're using right there. And we really don't want to use namespaces inside these header files because everything that includes them is going to get all that namespace stuff, which is really not necessary. So what we've got there is that we've got our private stuff, we've got our public stuff. We've defined these 2 methods right inside the class declaration. And then these other methods we've defined outside the class declaration in account CPP. Now, in order for the compiler to understand what you're talking about here, you have to include account.h. Once you include account.h, the compiler now knows what this is. Okay, once that's done, you go to your main and you can see the main is now pretty self-contained. You're just including account.h. It's really, really simple to do. The idea is just you're going to have a lot of header files and a lot of CPP files in your application, and everything gets compiled and linked into a single executable. In this video, we'll learn about constructors and destructors. Constructors are special member methods that are invoked during object creation. They're commonly used for initialization. Constructors are easy to recognize since they have the same name as the class. Constructors do not specify a return type, and like other methods, they can be overloaded. Let's see how we can declare constructors for the player class. In this slide, we have the player class that we've defined previously, but we want to concentrate specifically on the constructors. In this example, we have 3 overloaded constructors in the public section of the class declaration. Notice that the constructors have the same name as the class and they don't specify a return type. The first constructor is a no-args constructor and expects no arguments. The second constructor expects a single standard string object as an argument. And the third constructor expects 3 arguments, a standard string and 2 integers that represent health and XP. Overloading constructors is very common in C++ classes and really gives you a lot of flexibility when initializing objects. Now let's see some constructors for the account class. In this slide, we can see the declaration for the account class. Notice that we have 4 overloaded constructors in the public section of the class. The first constructor is the no-args constructor. The second constructor expects 2 arguments, a string representing the account name and a double representing the account balance. The third constructor expects just a string and the last constructor just a double. We'll get into much more detail about constructors in the next several videos, but let's see what a destructor is. Destructors are also special member methods that have the same name as the class. However, destructors have a tilde preceding their name. Destructors are invoked automatically by C++ when an object is destroyed, and it's a great place to release memory, close files, and free up any other resources. It makes no sense to allow overloaded destructors since the destructor is called automatically by C++. If there were multiple destructors, then C++ would have to determine which one to call, so that's not an option. So you can only specify one destructor per class, and that destructor has no return type and no parameters. Let's see how a destructor would be declared for the player class. Here is the declaration for the player class as we've seen before. Notice that the last declaration is the declaration for the class destructor. It has the same name as the class, and it's preceded by a tilde. It has no return type and no parameters. This destructor will be called automatically when a local object goes out of scope or when we delete a pointer to an object. As you would expect, the destructor for the account class is declared exactly the same way, except that the name is account. So, how and when are constructors and destructors called? Here's a very simple example. In the code block, we're creating 4 player objects. The first player object is called Slayer. Since no initialization information is provided, the noargs constructor is called. The second player object is called Frank, and we're providing a string and 2 integers during initialization. This means that the constructor that expects a string and 2 integers will be called. The third and fourth objects will be initialized using the overloaded constructor that expects a single string object. Note that all of these objects are local objects and they'll be created on the stack. We can use them as we would any object. But then when the block ends, these objects go out of scope and their destructors will be called automatically. So in this case, all 4 destructors will be called, and whatever code we provide in the destructors will be executed before the objects are destroyed. In the case of enemy, we have a pointer to a player object, and we use the constructor that expects a string and 2 integers to initialize it. We'll use it, then when we're done, we delete it. This will call the enemy object's destructor. If you provide no constructors and no destructor, C++ will automatically provide a default constructor and a default destructor that are empty. Okay, so I'm back in the IDE, and I'm in the Section 13 workspace in the Constructors and Destructors project. What I've done here is I've taken the player class, and I've written some constructors for it, just like we did in the slides, except I've implemented them. And they really don't do any initialization. We'll learn how to do that properly in the next few videos. They simply do an output statement that say which constructor is being called. So let me show you what I've got going on here. We've got the player class, just like we had before, and we've got these private attributes here, name, health, and XP, again, just like we had before. I've created a method right here called setName that simply sets the name of the player to whatever's being passed in here in nameval. The reason we're doing that is so that we can see which objects are being destroyed by name, and it'll be really easy to follow. Then we've got our 3 overloaded constructors here. You can see that they've got the same name as the class. That's their constructors. They're overloaded, so we've got 3 of them with 3 different signatures. This first one will be called when there is no information provided for initialization. And all it's going to do is just say no args constructor called. That's it. It's not going to do any initialization or anything. As I said, we'll learn how to do that in the next few videos. This constructor expects a single string, and it will just say string arg constructor called. And then the last constructor expects a string, a health, and an XP, and it will simply display 3 args constructor called. Okay, then when the object is destroyed, this destructor down here gets called. Notice it's the same name as the class with that tilde right in front. That's very important. No return type and nothing in here. And that's simply going to say destructor called for name. So it'll say destructor called for hero, for Frank, for Slayer, whatever the name of the object is. That way we can see the order in which this stuff is happening. Okay, so that's it. Pretty straightforward. And what I want to do now is I've got my main and I've got some breakpoints in here. I've established these blocks. Now, the idea behind these little blocks here is normally you wouldn't write code like this, but it's important because this Slayer object right here is within the scope of this block. So when it goes out of scope, the destructor will be called automatically. So I'm forcing that issue here so that you can see how this works. So what I'm doing is that I'm doing the Slayer, I'm creating some other players, and let's just debug this. We'll walk through it so you can see exactly what's happening. So I'll start the debugger, and I'll put the output window over here on the right so that we can see our output. Okay, perfect. So now we're on line 37, that's where we're starting. And what we're doing is we're creating Slayer. Slayer is a player object. It's local to this block. It's going to be created on the stack. So I'm going to select next. Notice that I'm creating it with no information, so what's going to happen here is the noargs constructor will be called, and that's what we expect to display up here. So let me scroll up a little bit here, and let's do that. Let's go next. You can see the noargs constructor just got called. That object has now been created. I want to set the name for that object to Slayer, so I'll execute that line. Now that object goes out of scope. We're done with this block. So the object needs to be destroyed since it's no longer needed. The way that happens is a destructor will be called right before the object is destroyed. So I expect this destructor right here to be called and say destructor called for Slayer. So let's see that exactly what happened. Destructor called for Slayer. Now we've got another block here, and what we're doing here is we're creating 3 player objects: Frank, Hero, and Villain. In the case of Frank, it's a noargs constructor, right? I'm not providing any information. In the case of Hero, it's a single string. And in the case of Villain, I've got the string and the 2 integers. So I expect this to say that the noargs constructor has been called, then the single string arg constructor has been called, and then the 3 arg constructor has been called. Okay? But what's interesting about this is not so much that. That's pretty intuitive. It's the way that the destructors are called. So let's walk through this little block here. So the first thing we expect is Frank to be created with noargs. And there it is, noargs constructor. I'm going to set the name to Frank. Hero will be called with a single string constructor. So you can see that that correct constructor is being called here. I've set the name to Hero, and now Villain with the 3 args constructor. Now, once I execute this set name method that sets the name for Villain, we're out of the block, right? So these objects are now out of scope. They need to be destroyed. What's interesting is, notice the order that we created them in. We created them as Frank, Hero, and Villain. And you'll see the order of destruction is the reverse order. So let's walk through this. We just called the destructor for Villain. Now we're going to call the destructor for Hero. And finally for Frank. So you can see that when objects go out of scope, the destructors are called in the order, reverse order in which they were created. Finally, down here, we've got some pointers to player objects. In this case, enemy is a new player. Again, I'm providing no initialization here, so it's going to call the noargs constructor. So let's do that real quick. Noargs constructor call, just like we expect. I'm going to set that name to enemy. Now here, I've got a level boss object, which is really, I've got a level boss pointer rather to an object, and I'm creating it using the 3 arg constructor right here, the string and the 2 integers. So that's the constructor that I expect to be called. And that's exactly what happens. 3 args constructor called. I'm going to set that name to level boss. Now I want to delete those objects that were created dynamically on the heap. In this case, I can explicitly delete them, and the destructors will be called. So in this case, we expect the enemy destructor to be called, and then the level boss destructor to be called. So that's it. In the next video, what we'll do is we'll learn about default constructors, and we'll learn how to really initialize things correctly and efficiently. In this video, we'll talk more about the default constructor. A default constructor is a constructor that doesn't expect any arguments. It's also called a noargs constructor. C++ has to have a way to construct and initialize objects if you don't provide any initialization information at all. So, if you don't provide any constructors at all, C++ will generate a default constructor automatically. This default constructor does nothing, but it's still generated by C++. When you create objects with no initialization information, this is the constructor that's called. Let's take a look at the account class again. In this account class, we've defined no constructors at all. So C++ will automatically generate a default constructor that allows us to create objects with no initialization information. Let's see a few examples. Here we're creating 2 local objects, Frank account and Jim account. The compiler provided default constructor will be used since we didn't provide any constructors at all. In the case of a pointer to an object, the same thing happens except that the object is created on the heap. Since the compiler generated default constructor does nothing, the class member attributes of the account class could contain garbage since they haven't been initialized. Of course, we're free to provide our own user-defined noargs constructor. In fact, it's best practice to do so. In this case, we're defining our own user-defined noargs constructor. This constructor will be called when no initialization information is provided, and in this constructor, we set the account name to none and the account balance to 0. So we're initializing the account member attributes to values we know about, not garbage data. Now let's see what happens when we define a constructor that expects arguments. In this case, we're defining a constructor that expects a string and a double, and we initialize our member attributes to the values passed into the constructor. This is very commonly done. However, once we define a constructor for our class, C++ will now not generate the noargs default constructor automatically. If we still need it, then we must explicitly define it ourselves. If you have code that creates objects with no initialization information, then that code will no longer compile since the default constructor is no longer generated by C++. So in this example, we can no longer create account objects with no arguments, again, since the default constructor is no longer automatically generated by the compiler. So we'll get 3 compiler errors when we try to create Frank, Jim, and Mary's account. However, we can still create account objects, but we have to use the constructor we provided that expects a string and a double. So we can create Bill's account since it provides the initialization information required by the constructor. Let's go through some of these examples in the IDE. Okay, so I'm in the IDE. I'm in the Section 13 workspace in the default constructor project. And what I've got here is the same player class that we've been using, where we've got the name, the health, and the XP for a player, which are private instance variables. And we've also got a couple of member methods here. Set name and get name, that's just the setter and the getter for that name attribute right there. What's important to understand here, and of course I would do the same thing for health or XP, but I don't want to clutter up the code. I just want to talk about the default constructors here. You'll notice that this player class has no constructor declared. C++ has to have a way to create objects. So if you don't provide any constructors, it will provide a system-generated noargs constructor that will allow you to create objects. So in this case, I don't have any constructors declared, but yet I'm able to create player objects with no problem. I could say Frank dot set name to, let's say, Frank, and I could output the value of Frank's name by using getName. Okay, something real simple like that. And what we'll do is we'll walk through this. We'll step through it using the debugger. So I'll put a breakpoint right here, and we can debug this real quickly. And we really don't care about the output. We just want to see that object. So you can see here that I'm on line 24, and I'm going to instantiate that Frank object, which is a player. There is no constructor. So behind the scenes, a default noargs constructor is generated that does nothing, but it does allow C++ to create that object. So I'm going to go next here. At this point, Frank is created. You can see the object right up here, and I executed the set name method, which set the attribute name to Frank. That's it. The next statement would obviously print it to the console. So you can see C++ has to have a way to create these objects. If you don't provide a way to initialize this using any kind of noargs constructor, you get one automatically by the compiler. That's great. Now, of course, I'm going to stop this. Of course, we can create our own noargs constructor. So let's do that. I'll do it down here so it's closer to the main. So what we can do is we can create our constructor. There it is. It's called player, same name as the class, noargs, and we'll implement it right here. Now, what's the default behavior I want when I don't provide any initialization information? Anything reasonable, whatever makes sense for your application. In this case, let's just say that the name is none. We'll say that the health is, let's say, 100. And let's say the XP is 3. That's it. That's my initializer. That's also my default initializer. That's what's important. This will now be called right here. And I'll put a breakpoint right in there so we can see it being called, and we'll debug this again. And here we go. What you can see happening is we're right here on line 30. And now when I step through this, notice how it transfers control to line 22. That's exactly what we expected. We didn't see that before because we didn't provide a default constructor, but now we're providing one. So ours will be called rather than the compiler created one. And this will just step through and it'll set the properties to name, 103. And now I'm back here on line 31, and you can see right here that we've got none, 103. And now I can change the none to Frank right here on this line. And I'll refresh this, and you can see here it's Frank. Right there, the string is Frank. Okay, so there you go. If you don't provide any constructors, you get a default constructor for free, if you will. And if you provide your own default constructor, that's the one that will be used. Now, let's do one more thing here. What happens if you create, let me comment this out right here. And suppose that I want to create a different constructor, an overloaded constructor. So I'm going to say player, and I want to provide the name. I want to provide all of those values. So this is my name val. I want health. And I want the XP as well. I want to provide all three of these values. And in the body of this constructor, I'm just going to say name equals name val, health equals health val, and XP equals XP val. Okay, so that's where we're at. Now, we have a bit of a problem now. In C++, and this is true of many object-oriented languages, including Java and others, you get that default constructor as long as you don't provide any other constructor. Well, what we just did here is we provided a constructor. In this case, this constructor expects 3 arguments. Now that compiler-generated noargs default constructor will no longer be generated. So this line of code right here on line 35 won't compile anymore. Let me run the debugger here. You'll see the error right here. It says no matching function call for the noargs constructor. This is perfectly normal. This is exactly the way it's supposed to work. The idea being that now you've provided a way to construct your object, so C++ will no longer provide a default way, right? Maybe you don't want a default way. So this won't compile. I'll comment that out, and I'll move the breakpoint down to here. So now the way we need to construct this object is to explicitly call that other constructor. So I'm going to say player Frank, and we'll initialize that to Frank 100, and let's say 13 or something. Okay, now what's going to happen is when this line executes, let me get rid of a few of those breakpoints. When this line executes on 36, what's going to happen is this constructor is going to be called, the one that I just created. So I'll put a breakpoint there so you can see that happening. Okay, so let's debug this again. We'll walk through it one more time. And here we are, we're on line 36. When I step through it, you'll see control will be transferred up to line 27 up here. So there we are, we're in the constructor now. So we're explicitly calling that 3arg constructor that we just created. Remember, once I create any kind of constructor, the default constructor that's automatically generated won't be generated anymore. We'll walk through this, and when we're done, we'll refresh this, and you can see Frank 113 has been created, just as we expected. Now, of course, we can create both of these, right? So now I can create, let's say, a hero object. So now what we've got is we've got 2 constructors that we provided. We provided a noargs constructor, and we provided this overloaded constructor that expects the 3 arguments. In this case, hero, we're not providing any initialization information. So the noargs constructor, this guy right here on line 21 will be called. And in the case of Frank, it'll be just like before, this one would be called. So let's step through that. And whoops, let me do that again. I'll put a breakpoint on hero. Let's try that one more time. And you can see what's happening here is I'm right here on line 35. So I'm going to construct that hero object. And you can see transfers control right up to here. So this noargs constructor is being called. That's what we expect. That's our constructor, right? That's not compiler generated because we wrote it ourselves. So that's going to execute. Now I come back to Frank, and this constructor will be called. So you'll see control will be transferred over here to 27. And we'll run through that. You can see it happening right here on line 29. That's where I'm at now. And at this point, we've got both those objects constructed, and we can see them right here. There's Frank, and there's hero. Hero uses none 103, and Frank is using Frank 113. You see them right here. Okay, so that's it. That's the behavior for default constructors in C++. We've already seen overloaded constructors in the IDE, but let's see a few more examples. Classes can have as many constructors as necessary. The only restriction is that they must each have a unique signature. The compiler has to be able to determine which to call based on the initialization information provided when creating the objects. If there's any ambiguity, the compiler won't guess, it will generate a compiler error. Remember, once you declare any constructor, then the compiler-generated default constructor will no longer be provided. Here's the player class again, and we've decided that we need 3 constructors. The first is a no-args constructor, the second only expects a single string object, and the third expects a string and 2 integers. Obviously, the signatures for these constructors are different, so the compiler can tell them apart. We could have more constructors depending on our class design. Now let's implement these constructors. In the first example, we're implementing the noargs constructor to initialize the object to name none, health 0, and XP 0. The values we initialize to are totally dependent on what we want our objects in the game to look like when no initialization information is provided. It's important that we initialize our objects to some state that we know. We don't want garbage data in any of the attributes after they're created. In the second constructor, we only have the name parameter provided. So we set the name attribute to nameVal and then the health and XP to 0. If we don't initialize health and XP, they'll contain garbage, and that leaves the object in an unknown state. Finally, the third constructor is given initialization values for all 3 attributes, so we initialize name to nameVal, health to healthVal, and XP to XPVal. Now we have 3 ways to create player objects. In this case, the empty object will be initialized by the noargs constructor, and it will contain none, 0, and 0. Hero and villain will be initialized with the constructor that expects a single string object, and they will be initialized to hero 00 and villain 00 respectively. The Frank object will be initialized by the 3args constructor, and it will contain Frank 104. And finally, the enemy object will be created dynamically on the heap and initialized by the 3args constructor to enemy 1000. As you can see, overloading constructors is a super powerful way to provide many useful initialization options for your classes. Also, best practice is to initialize all class attributes so that created objects do not contain any garbage data.